Welcome everybody, good morning. We are privileged to have distinguished guest speakers from India, from Mexico, from the United Kingdom, not of course forgetting our Finnish colleagues. I'd like to very shortly introduce the organizers of the Scientific Models and a Comprehensive Picture of Reality event we are starting. So, the Finnish Society for Natural Philosophy promotes studies on the philosophical aspects of science, of natural sciences, and encourages discussion between different branches of sciences with emphasis on the linkage between philosophy and physics. The society was founded by Professor Laurikainen as a continuation of his very popular Thursday seminars on natural philosophy at the Department of High Energy Physics in the University of Helsinki. As you can notice here, this year we are celebrating the 100th anniversary of Laurikainen's birth. We can say that Laurikainen's heritage to the societies has culminated in openness and broad-mindedness. He saw that unsolved problems are not solved by hiding or denying the problems, or by a conviction of being right. So that natural philosophy knows the difference between reality and a description of reality. So that even the best theory can only give a description of reality. The better is the description, the better is the theory. But we can't see that it's question or false or truth. We succeed in better with our theories, or probably not that well. Always there is place for improvement. The Physics Foundation Society is dedicated to the search for deeper understanding of physical reality. Society was founded informally almost 20 years ago as a registered association in 2008 by Professor Ari Lehto, Dr. Heikki Sipilä, Dr. Tarja Kallio-Tamminen, and myself. Today's program is mainly focused on cosmology and a general picture of reality. And then tomorrow's program complements the package with more philosophical aspects. As some practical points, during the coffee breaks and lunch breaks, there are books published by the organizing societies available in the lobby, so you can make a look at the tables on the lobby. Coffee is served at the second floor, just to the right, behind the main door here. And lunch is available at Tiedekahvila, Science Cafe in English, at the lobby floor on the left-hand side in the lobby. We have 1.5 hour lunch break, so it's also possible to have lunch in some of the neighboring restaurants here. And today, after the scientific program, we have a reception served by the University of Helsinki. And it's worthwhile noting the reception starts at 6:30 or 18:30. Our host will be Professor Esko Ukkonen, who serves as the Vice Dean of the Faculty of Science in the University of Helsinki. So please observe that we have to enter the university building from Fabianinkatu, so not from the big square facade, but the other side of the building. So once we come to the building, we need to take the elevator up to the 4th floor, where the reception is served. Okay, so our chairman today will be Professor Ari Lehto, and I wish you an interesting workshop. Ari. So let's switch the view here. I have to switch this one here. And we start with this.
Yes. Good morning, everybody. Yes. I have the great pleasure to introduce to you distinguished Professor Jayant Narlikar. He is director of the Inter-University Center for Astronomy and Astrophysics, and he was invited to establish this center in 1988. He got his BSc degree in 1957 at Banaras Hindu University. Cambridge degrees in mathematics, BA 1960 and Doctor 1963, and worked with Fred Hoyle in Cambridge until 1972. He is professor at Tata Institute of Fundamental Research, TIFR, from 1972 till 1989. He is the president of the Cosmology Commission of the International Astronomical Union from 1994 to 1997. Together with Sir Fred Hoyle, Professor Narlikar developed the conformal gravity theory, commonly known as Hoyle-Narlikar theory, and I think everybody in this room who is interested in cosmology knows this. It synthesizes Albert Einstein's theory of relativity and Mach's principle. It proposes that the inertial mass of a particle is a function of the masses of all other mass in the universe or other particles, multiplied by a coupling constant, which is a function of cosmic epoch. So let's welcome Professor Narlikar, please. Yes, or this one, or this one. Yeah, this one.
That is
Yeah. Onko tämä päällä?
that I got.
Yeah.
Yes.
Nyt se käynnistyy.
If you like to use laser, you can push the center here.
Okay.
And also here you can move the slides forward, backward.
Friends, first of all, I would like to thank my host, Finnish Society for Natural Philosophy, for a very comfortable visit and stay here. I am enjoying my first visit to your country, and the weather looks beautiful, and probably taking this as a sample, one would say that you always have this kind of weather. But today I will share with you some ideas on models of the universe. In general, when you model something, that something is a finite quantity, finite object. But the universe is infinite or boundless, and it does not have multiplicity. That is, there is only one universe that you have, and you have to keep that in mind when you make a model. So I want to tell you something about previous attempts to do this work. And one of the interesting ideas was the Pythagorean model of the Earth and the Sun. The basic assumption was that the Earth goes around not the Sun, but around a central fire. And people began to ask, how did, let's see, the people began to ask, why don't we see the central fire? So the Pythagoreans had to think of a way of explaining this non-observability of central fire, which they did by saying that you have a counter Earth, which also goes around the central fire, just in such a way as to hide the fire from you. So this was the what you would call explanation, or one could say in new terms, a new parameter put into the model. So people began to ask further questions, again of an awkward nature. Why don't we see this counter Earth, which is going round? If it is going round with us, we should see it. So to avoid such questions, the Pythagoreans said that Greece is on this side, opposite to the central fire, opposite to the counter Earth, and therefore you don't see the counter Earth. So you see, you introduce one parameter and then that causes problems, so you introduce another parameter. And this is an example of a theory which is perhaps on the wrong track, where you have to produce more and more new assumptions to make it work, or to save the theory. So one also had this kind of problem later with the epicyclic theory of the Greeks, where you see, instead of, they wanted everything to be around a fixed Earth. And the planets which go around, supposedly go around the Earth, cannot go around in a simple circular orbit. That was another assumption they were forced to make. Aristotle's idea was that everything natural should be in circles. So you could have more circles, but you cannot go into other curves. That was the restriction. And so here you see an example of a circle, smaller circle, whose center is going on a bigger circle, which is centered somewhere around the Earth. The Earth itself was not exactly at the center, but off-center. But all this was done in order to understand or explain the motion of planets. So these, when this model didn't work, they had to put another epicycle. These little circles were called epicycles. So you had one or more epicycles to understand what is going on. So at this stage, I would like to introduce what I feel one should take as an example of path to follow. This was Karl Popper's restriction on what kind of theories are allowed. So Karl Popper's criterion was that a scientific model must survive all scientific tests in order to be judged non-trivial and significant. If, however, it fails any particular test, it must be abandoned. So what this theory is, that it's never right. It's always on a kind of test. And you keep on creating new and new scientific tests in order to see whether the predictions of the model work. If they work, that means the model survives, but does not mean that it is right. And when it survives, then you can ask, what about another test? So you go on doing this until a stage might come when it has to be abandoned because it failed that particular test. We will be coming across such models. So one could say that Popper's rule is very strict. It can be relaxed by allowing a parameter space. So what the Pythagoreans were doing was relaxing the parameter space. And what you could do, for example, by saying, if it fails, I will add an extra parameter and make it survive. But I don't want to reject it right away. So, however, if you are on the wrong track, a wrong model cannot be so corrected as was found in the epicycles of Greek astronomers, geometers. I just now showed one example. So, we can now go to a more sophisticated theory, Newtonian gravitation. One could say that it worked very successfully over 2 centuries, but had to be abandoned as required by Popper's criterion. Why it had to be abandoned? Because there were certain tests, especially in the solar system, which the model did not agree with. So, what were its successes? Successes, one can count the cometary motion. The motions of comets were explained and understood. The discovery of planet Neptune was made because of the use of Newtonian gravitation. It was, in fact, the first successful prediction of a astronomical object, the existence of astronomical object by theory. Stellar models are another example, that is models of the sun and so forth. But apparently small discrepancies, like the motion of Mercury and bending of light, etc., led to the replacement of the Newtonian model by general relativity. So one could argue in this sense that a model like Newton's, which turned out to have made so many successful predictions, still had this particular vulnerability. So I want to come to give you one example of stellar models. This was, one could say, the first attempt was wrong, turned out to be wrong. This was the Kelvin-Helmholtz models. They assumed that the sun or any particular star is in equilibrium. That's all right. But where is it getting its energy? Its energy is coming basically from its gravitational reservoir. So if you take Newtonian gravitation, G is a gravitational constant, m is the mass of the planet, of the star, then gm square over r is the radius. It is of that order, that is the gravitational potential energy. And the idea was that as the sun shrinks, it releases gravitational energy which makes it shine. So the lifetime of a star, if you estimate by this method, was no more than 20 million years. Although 20 million sounds very long time scale, but in terms of the Earth's age itself, it was, and the geophysical estimates of various objects on the Earth, it made it impossible to sustain this particular idea. 20 million was not large enough. One has to go into something like 4 to 5 billion. So the right approach came through the Perrin-Eddington models. The nuclear fusion energy, was the source of energy in this case. And it gave, the idea, as you know, was four nuclei of hydrogen combined together to make one nucleus of helium, in the process losing some mass, which is compensated by the release of energy, and that energy is the one which the sun is using for emission. So Perrin-Eddington models gave nuclear fusion energy the correct lifetime of the order of 12 billion years. So we had here a good example, or the right example of model, along with the wrong example which preceded it. Now, one could ask, how do you test these stellar models? So they can be judged by the measurement of mass and luminosity of stars. So what one could argue that if you have a star like the sun, whose mass you know very well, you can estimate using the Eddington model, you can estimate the luminosity of the sun from its mass. So that gives you one example which tests correctly. But you can also have other masses, and you can argue that different masses will give different luminosity, and what you see here is a mass-luminosity relation, which is mass here and something like luminosity there, and you have stars lying along it, and it shows that there are different stars of different masses, and they are all agreeing with the theory. So the example of stellar models is showing us the power of prediction and theorizing based on known physics. It also tells you the kind of restriction one has to follow using tests. So the extension to models of the universe, when we come to the more ambitious tests of cosmology, one has to acknowledge the following weaknesses that exist. First of all, there is only one universe. Now recently it has become more fashionable to talk of multiverse or many universes. Now I personally keep a more conservative point of view that there is only one universe, and whatever we observe should belong to or should tell us about that one universe. So that is one point. The laws of physics may have changed over periods as long as 10 billion years. When you are applying physics to cosmology, you must be sure that the physics you are applying is a well-tested, well-known, well-understood physics. Now, it could happen that when you are talking about ages as long as 10 billion years, has your physics remained the same all through? How do you know that it has, if it has changed, how do you know that it has changed in a particular fashion? So one has to be aware that there is a shortcoming in our way of approaching the universe. Then the next one is that the observational checks are far fewer. That means there are not that many observational tests that you can make with many universes. As you saw in the case of the star, I showed you a whole range of masses which gave different luminosity. You cannot have, likewise, saying that universe can have, there can be many kind of universes and each one can be tested in this fashion. So we are already running into problems if we apply this criteria for validity of a model. So here, now I want to describe briefly the steady state theory, which was produced in 1948 by these three cosmologists or mathematicians, whatever you call them. So you have here Tommy Gold, then Herman Bondi and Fred Hoyle. So they were keen to offer an alternative theory to the Big Bang, which was the theory which was indicated from Einstein's equations of gravitation. So Bondi and Gold had one approach to the steady-state theory and Hoyle had another. As you know, they wrote separate papers which appeared in the monthly notices in the same year, although slightly at different dates. So although there were two approaches to this model, Bondi used to stress the fact that the approach based on the perfect cosmological principle was fully as per the Karl Popper rule. So Bondi and Gold had not gone to a field theory to describe cosmology, steady-state cosmology. Instead, they said they will have a overall principle, which they called the perfect cosmological principle. And the argument was that if you are not sure about the laws of physics remaining the same in your model, you cannot test cosmology. So if you really want to test your model and do cosmology in the Karl Popper's way, then you have to make sure that the laws of physics are the same, were the same at all times. And they argue that this can be done if we say that the universe is unchanging over long time scales. So if the universe is unchanged, then the laws which are part of the universe will also remain unchanged. So this was the basis of perfect cosmological principle. Like the universe is homogeneous in space-wise sense, they added an extra homogeneity in time so that over all times the universe would be under the same regime of physical laws. And then they said you can test any idea using this particular hypothesis. So, and he was also particular that if you find that your theory doesn't work, doesn't stand up to certain tests, then you reject it as in Karl Popper's way. So as I said, the perfect cosmological principle guaranteed that the basic laws were unchanged and the distant universe was the same as the neighborhood of the observer. This made it easy to test and possibly disprove the steady-state model. However, it also happened that a wrong interpretation of data led to incorrect conclusions against the theory. So one has to be sure when one applies a Popper type of argument that you better be sure that your tests are without any observational error. So this happened in the case of steady-state theory, as I show you by some examples. There are 4 examples that I can give you. One is the Stebbins-Whitford effect. It's a kind of somewhat technical aspect, but when you look at a distant galaxy, you see a spectrum of its light which is redshifted. So you cannot compare its spectrum with the spectrum of a nearby galaxy before making a correction for this redshift. This was not done in the observations produced, which claim to disprove steady-state theory, but when the correction was properly put in, that discrepancy disappeared. There were radio source counts, which was also the an example that in I think around 1956 or so, radio astronomy in Cambridge was sufficiently developed for the radio astronomers to do a test of cosmology, counting radio sources at different flux levels. So that would tell you whether the count proceeds according to the prediction of a cosmological theory. So what happened was that they found if you had a Euclidean universe which is not expanding, then you will get the slope of log n against log s. Log n is the number of sources brighter than s is the flux density. So you plot flux density against the number, and log n log s according to Euclidean geometry should give a slope of minus 1.5. What Ryle and his colleagues found were the slope much steeper than this, closer to 3. And they claimed that this shows that certainly the universe is evolving, it is not in a Euclidean geometry. And they also used the result of steady-state theory, which gave a slope of 1.5 to start with, and then it became less and less in magnitude to 1.4, 1.3, etc., instead of steepening as they had found. And so they said that this has disproved the steady-state theory. About 2 years later, they redid this test, and this time they claimed that the same conclusion held, but the slope had come down to something like 2 to 2.5 or something like that. Then another 2-3 years later, they did this test again, each time improving the error sources and so on. And they found this slope had come down still, but it was 1.8, minus 1.8. So at that time, there was a big kind of publicity to this result, showing that the steady-state theory was disproved. I remember being present at the Royal Astronomical Society meeting where this result was presented, and the steady-staters were asked to reply to this comment. At that time, Bondi was very much present in the meeting. So when he was asked, he said that, look, in 1955 or so, the slope was 3, then it became 2.4, now it is 1.8. So I am willing to wait for another few years before it comes down to 1.5. So this kind of comment did not go down well with the radio astronomers, who naturally felt that their work was being derided. However, Hoyle had worked on an alternative model. He had asked me to work with him on this. And it so happened that day he was present. He was not present at the RAS meeting. And he asked me to express what we had found. So what we had found was that if the universe had inhomogeneity on a large scale of the order of 50 megaparsecs, then there will be a fluctuation in the observation of log n log s. And what we showed was that it was possible to get among the fluctuation a slope of 1.8 as Ryle had found. So this was the overall situation, which shows that it is not very easy to draw unequivocal conclusions from so-called cosmological tests. Then the next one that I want to draw attention to was the accelerating universe. Now, there have been tests conducted by Alan Sandage, for example, in the 60s and 70s. He was the pioneering optical astronomer for measuring redshift against magnitude, and Hubble's, what is called a Hubble relation. And there used to be curves predicted by Sandage on the which were very much advertised as disproof of steady-state theory. So what it showed was that the redshift magnitude relation satisfied the requirement of many of the Friedmann models, the Big Bang models, which said that the universe is decelerating. That is, the universe is expanding all right, but this rate of expansion is slowing down. And this is what was supposedly confirmed by Sandage's observations. Whereas the steady-state theory showed an accelerating universe. And therefore, it was sort of shown to be inconsistent with observation. Now, that was in the 60s and 70s. In the 90s, there was a rethink and a reassessment of the redshift magnitude relation for using supernovae. And it showed that the universe is accelerating. So you are coming back to the steady-state model, but by then people had forgotten that such a thing has been, prediction had been made by steady-state model, and people simply said, how can we make the universe accelerate consistently with Big Bang? And they put in the lambda term, and when the constant lambda term of Einstein did not work, they put a variable lambda term. So parameter putting exercise began, and people have still been at it to understand the accelerating universe. And the fourth thing was the cosmic microwave background. And here I want to tell you one story which Hoyle used to tell, how Bondi, Gould, and he himself missed the boat. So what happened was, in 1955, Bondi, Gould, and Hoyle, the three steady-staters, did the following calculation. If all the helium in the universe were made in stars, per gram of hydrogen, the energy created would be 6 times 10 to the 18 ergs. This is from stellar and nuclear physics. The observed density of helium in the universe was about 7.5 into 10 to the minus 32 gram. So if so much helium has been made, what was the amount of radiation produced in this process? So they worked it out. The calculation is very simple. You can do it yourself. The product of these numbers, which comes out to be 4.5 into the 10 to the minus 13 erg per cubic centimeter. That was the radiation that would come out. Now, if this energy were thermalized, the resulting temperature would be around 2.7 at K. So when they got this result, Gould wanted to publish a paper to predict a background temperature of this magnitude. But he was overruled by Bondi and Hoyle since they did not know how to thermalize this radiation. So their idea was that until we know how to thermalize that radiation, we cannot say that it was thermalized. On the other hand, Gould said that if any radiation has been around long enough time, the second law of thermodynamics will take care that it will degenerate into a black body radiation. And so it will be thermalized. So why worry about not knowing the specific process? So they did not write a paper predicting this 2.78 K. But if they had done it, it could have probably changed the perception of cosmologists towards the steady state theory. So I come now to the credibility of a model. The model, I'm talking of cosmological models. The model should make a clear prediction which is later verified by experiment and observation. So, for example, Friedmann models which predicted expanding universe, later found by Hubble. Incidentally, there is a question, was Hubble anticipated by Lemaitre? Because when I went to Liège, the Institut d'Astrophysique, they showed me, they had put the paper by Lemaitre on display, where he not only gets, this was in 1927, 2 years before Hubble, he not only gets the fact that the galaxies are having redshift proportional to distance, he works out the rate of expansion, the so-called Hubble constant before Hubble had said it, and he gets almost the right answer that people got at that time. Anyway, this is the point that Friedmann models did predict expansion of the universe, and that was found. So one can ask similarly, what about any other predictions that standard cosmology made which turned out to be right? So in addition to Friedmann and Lemaitre, the following two predictions may be noted. One was the Gamow's idea on primordial nucleosynthesis, although Gamow's ideas were much more what I would call widespread, in the sense of he wanted to produce all the chemical elements in the early hot universe. This turned out to be impossible. On the other hand, light nuclei could be made in the early universe, and these were not easy, or there is still no way of doing this in stars. And the second was the prediction by Alpher and Hermann, who were co-workers with Gamow, of the cosmic microwave background radiation. They did not have a temperature to predict, but they guessed what you call, is of 5 degree Kelvin. So this is what I just now said, that Gamow's expectation that all chemical elements will be made primordially did not work out. Only a few light nuclei are so made. But here is the second point, which we will come back to. Even there, the deuterium cannot be made if baryon density of the universe is more than a critical value. So we will return to this issue later. But you can see here the light nuclear abundances for different densities, and this drop, sharp drop, is the abundance of, is the production of deuterium, and you find that it drops to almost negligible quantity, provided you move further and further right in the in this particular curve, in the graph, which suggests that you cannot have baryon density more than a certain value. So this is a prediction which comes from Gamow's work. We will come back to this later. The CMBR had already been discovered observationally by Mackellar in 1941. This is not very well known. This work was published in an observatory journal and in Canada, and at the height of war, this was 41, and was not well known. So the journal did not have much circulation, and in any case, during the wartime, scientists were not so up to date with what had been done. So this was the problem, that CMBR, although could be predicted, was predicted, but the observation had already been there, but people were unaware of it. And about the CMBR temperature, it is recognized that there is no calculation that gives the standard cosmology, that one gives in standard cosmology for the expected temperature of CMBR at the present epoch. So this 2.7 that we find in this particular case has to be a given quantity for working out details of the model. So now I come to the models of the very early universe. So because of these three successes that I just now encountered, enumerated, people were more keen to work out closer and closer to the Big Bang what is the nature of physics and astrophysics. So you see here that time-temperature relationship coming out of Big Bang cosmology. So this is obtained by combining flat space-time statistical mechanics with cosmology of the expanding universe. The justification of it rests on validity of a principle of equivalence. Now you can see that you are going to very high temperatures. The temperature is measured here in GeV. GeV meaning you take KT, K is a Boltzmann constant, K times T, and express it in GeV, MEV, etc. So what you are seeing is the fact that at very high temperature, the time is related to, time of expansion is related in this fashion. Now you can ask, how do we know that this physics of statistical mechanics with large number of particles interacting, is it valid at such points where the curvature of space-time was very large? So the answer is that would depend on your validity of principle of equivalence. So what you argue is the following. Take a curved space, and to give you an analogy, supposing you want to build a house on the earth. Now somebody tells you the earth is spherical, so your house will not be stable. It will sort of go this way, that way. So you say, no, I am confident I can make it locally flat, because the size of my house is not that big, and over that size I can ignore the curvature of the earth. So in the same way, the principle of equivalence comes in to tell you that locally you have a flat space-time, and in that flat space-time you can apply statistical mechanics and do all these calculations. So you have this situation, is the principle of equivalence valid and in the very early universe? So one goes in this way. At time t, the local radius of curvature is around ct. C is the speed of light. And the size of a locally flat region will be L equal to alpha ct, where alpha is less than 1. So for principle of equivalence to be valid, you want locally flat. So the curvature should be less than the local curvature of the model. So we now ask how many particles in thermal equilibrium at temperature T will be found in the locally flat region above. So this is a calculation you can make using the statistical mechanics in this cosmological model. And the answer comes out to be less than 1. That means you take the volume in which you want to do statistical mechanics, the number of particles that you have to deal with will turn out to be less than 1. So you cannot do statistical mechanics with such small numbers. And therefore, one has to either do a curved space-time statistical mechanics, which nobody has done, or one has to somehow justify this particular result. So what I will do is refer to this last problem I mentioned of the standard model, the model that we have taken, and as small number problem. That means we are doing statistical mechanics with very small numbers. So we list below many of the problems of this standard model. Starting with the small number problem, we also have horizon problem, flatness problem, monopole problem, which have been discussed in the rest of the first one has not been discussed much, but 2, 3, 4 have been discussed a lot. Then deuterium abundance, I will come to that. Let me say something about the monopole problem. The monopole problem comes from the assumption that your model is valid at the time when the physical interaction was going through grand unification. That means you are going really to very, very small and very high, very hot times. Now, if you do this assumption of very small universe, the size of the universe is very small, and you then find that as a result of grand unification, the result is that there is monopole created. Pairs of monopole, no, not pairs. Monopoles are created instead of pairs of opposite poles. And the monopoles have a certain density, which if you work out today how many monopoles are there, you will get a very, very large number of monopoles, which are certainly not there. Their density will be much more than the cosmological density which is claimed to be present. So people did not know how to get rid of these monopoles, which had come out of grand unification. And then inflation came into the red. Inflation inflates the whole thing away, so the density drops to 0 or almost 0. So this was how monopole problem was solved. Now here I want to give you a comparison with the Pythagorean counter-earth. First, you don't know what physics existed, but if you take some extrapolation, it tells you that there should be monopoles present. So monopoles present, you ask where are the monopoles? If you don't see the monopoles, you have to find some way of getting rid of them. So you say there was inflation which produced the monopole. So you could again ask what is the proof of inflation? That is another matter. But here is one example which runs parallel to the Pythagorean counter-earth. Now we come to another one, the deuterium abundance. When you find, as I mentioned in the Gamo's work and other people who work further on it, the deuterium abundance falls to almost 0 if you exceed a certain baryon density. So if you exceed that, then what's happening is that your cosmological model cannot produce the deuterium, which is claimed to be one of the successes of Big Bang. So the model must produce deuterium. At the same time, you have to be consistent with that density falling 0. Now when dark matter was found, people felt that dark matter could be of this kind, which if you allow it to be baryonic, you take the first natural conclusion is that anything that is not visible is similar to that, except that it doesn't have much light, but nothing strange about it. So if they are baryonic, then you will not be able to get deuterium. So you want the high density, but you cannot have baryonic, so you make it non-baryonic. So you say there is a non-baryonic density of much more magnitude, greater magnitude than the actual visible matter. And that is how you are, in a sense, forced to assume that there is a non-baryonic matter present, which has not been found in the lab or by astronomers independently. Then there is the question that, which is still not explained, how do you get the photon to baryon ratio? Then there is the age-related problem, that is the ages. You are with improved astronomical observations, you are beginning to get galaxies of very high redshift, which are well developed. So they have therefore a age which is much more than would have been expected from the model. Then there is the dark matter problem and the dark energy problem, which dark matter problem is the non-baryonic dark matter, which I mentioned, whereas how can we prove that it is non-baryonic and how do we explain it? And then dark energy has come in, as I mentioned earlier, accelerating universe was the reason for bringing dark energy problem. So back to Popper's regime, any of the above problem is sufficient to reject the theory, if you were following Popper's criterion. But like the Pythagoreans, modifications are sought in order to save the theory. For example, the deduction of dark matter being non-baryonic is made to negate the restriction of deuterium production. Inflation is another way out against some of the above problems. However, it also suffers from several defects. For example, it is put in ad hoc rather than deduced as a consequence of some grand unification program. The parameters that determine the slow rollover followed by rapid descent, that is part of the way this inflation operates, so these numbers are all put in by hand to make it work. As yet, there is no unique model of inflation. So these people use different backgrounds. So there is also considerable confusion between event and particle horizons. In fact, no such horizons exist in the actual cosmology, and only the length scale of large scale structure exists, but it is not an exact situation. So contrary to the practice of relativists, many conclusions are drawn without any exact solution. So if you take inflation, inflation is suggesting that you have got an expanding, rapidly expanding de Sitter universe, and inside there is a Friedmann model. Now this kind of matching of solution inside and outside has been very important in classical general relativity. Any solution has a validity provided you have matched all the boundary conditions. But this has never worried the cosmologists who use inflation. There is no such exact solution known so far. So if you look at this present picture of the Big Bang, which I have drawn, this is a standard picture, you find that most of it is speculative. That is, you can neither see it observationally, nor can you use physics that is known in the laboratory or observation. So you see here the situation that beyond this, the astronomer cannot observe because there is too much scattering of light. And physicists cannot tell us what theory should be used because the grand unification program is still not completed. So you have these problems. So in the preceding picture, how much is directly observed and how much is confirmed by laboratory physics, that is the question one should ask. So if you look at this present cosmological model which I have been describing, what do we expect and what do we get? So you have the Friedmann-Robertson-Walker model as the first stage. Then you have a lambda term added as an epicycle. Then I have n-body simulations which add further epicycles. Then you have got dark matter problem which produces how much dark matter you allow as non-baryonic and so on. Then the next type epicycle is biasing. Where is the dark matter in relation to the normal matter? Then comes inflation that happened very early, and as I said, this has also been put in by hand, and one needs to understand how it is related to the grand unification program. And then there are quantum fluctuations. When you go very close to the Big Bang, you say that gravities cannot be dealt with classically. We need quantum gravity, which nobody has honestly yet got the answer how to do quantized gravity. But people talk about quantum fluctuations in a way as if it's a well-established idea. So I'm sometimes worried whether too much is not assumed in terms of what is right and what is wrong. So I could have gone on describing these problems. My main idea here was to show that the model of the universe that we are expecting to deliver has fallen short in many ways, and one could think of an alternative cosmology. So I would very briefly mention the cosmology proposed by Hoyle, Burbidge, and myself. That is the quasi-steady state cosmology. And the broad features are matter creation through a negative energy scalar field, matter creation large in strong gravitational field, so you've got preferential creation of matter, the expansion of the universe driven by multiple mini creation events, and the cosmology explains all the observed features of the universe that one can show eventually by looking at all the present observations. So how to distinguish from the standard models? So some distinguishing features are, they exist because, as you see, Popper's principle says that do tests and then decide whether to accept or reject. So the existence of blue shifted distant galaxies would be difficult to explain in terms of standard cosmology. And the existence of very old stars, say 20 giga-year-old, would be hard to explain. And one could also compare gravitational radiation background with in this alternative cosmology with what inflation has predicted. So one has therefore a number of ways of testing between these two theories. Finally, I want to end with a comment which Fred Hoyle made, which some of you may have seen across. This was in 1970 at the Vatican Conference. I think it is very unlikely that a creature evolving on this planet, the human being, is likely to possess a brain that is fully capable of understanding physics in its totality. I think this is inherently improbable in the first place, but even if it should be so, it is surely wildly improbable that this situation should just have been reached in the year 1970. Now what happened was, in this Vatican conference, the Big Bang cosmologists had come to the conclusion saying that the universe is of this kind, it is very well understood, and there is no great problem left to solve. So he made this particular statement to counter it. And you remember now, going back, 1970 was prior to any of these ideas which are in part of the Big Bang today, namely inflation, grand unified theory, non-baryonic dark matter, lambda, or dark energy, CMBR anisotropies. All these things were not known, but the people assumed that the model is perfect and has solved every problem. So I think one has to be a little more careful in making assumptions about, especially cosmological models, where there is only one universe, and we need to be that much more careful. I think I will stop. Thank you. If there are any questions, I can.
Thank you, Professor Narlikar, for a very interesting and inspiring talk. I'm sure it raised quite a lot of questions, and we still have time for several questions. So, let's take the first one here. Professor Aliseda.
Thank you. Professor Narlikar, thank you very much for such a, I think, clear conference, and also for your interest in philosophy, where I come from. Especially, I liked and would like to ask you a question about the role of Popper in all of this. So let me go a bit further. As you mentioned, according to him, of course, scientific theories should be somehow testable, but they should also be falsifiable. And Popper actually made up this requirement for what was called his demarcation problem. He wanted to have a criterion to distinguish what was scientific from what was not scientific. And when theory was not falsifiable, he would say that is not science, really. So my question now comes in your mentioning, or rather comparison, of the Big Bang theory with the steady state theory. And more in particular, when you spoke about the example of the radio source count, then you mentioned that in this respect, the Big Bang theory is not falsifiable, whereas the steady state it is. So would you say that at least with respect to this example, there's a sign or a symptom, so to speak, that then the Big Bang theory is not so scientific after all?
This was about radio source count. Can you, I think I did not get it full.
Okay. So in fact, there were several points that Professor Aliseda was taking up, but I think the very key of the question is that if you look Big Bang theory as a scientific theory, how well does it fill the criteria of scientific theory? Is that the key of it?
Yeah.
And in particular, since it's not falsifiable in some respects, it may not be so scientific after all.
Yeah.
From the point of view of Popper, of course.
You see, when you develop a particular theory, it goes through stages of sophistication. So in the primitive stages, in the early stages, the Big Bang theory did well in predicting the expansion of the universe, and then it also predicted the production of light nuclei, and in the early hot epoch, and the production and the microwave background radiation. So these were plus points. But any scientific theory should not rest there. It should go on making further predictions and more sophisticated situations. And that, I was showing, has not happened. All the developments in Big Bang since then have produced more speculative arguments rather than a clear-cut proof that this is so, so this is right. That is my criticism.
Next questions. Professor Barbour.
I just wonder whether you aren't asking for too much. Let me remind you of that wonderful comment of Einstein, I think in 1935, when he was trying to have a beautiful unified theory in which geometry is everything. He described the left-hand side of his field equations, the Einstein tensor, as fine marble, I think it was, and on the right-hand side, the energy momentum tensor as rough timber. And the fact of the matter is we are still desperately trying to understand what the matter content of the universe is. And maybe a lot of discussion is premature until that problem has been solved. I mean, the Standard Model is a huge success in one way, but it has all those parameters that are undetermined, and there may be more. So perhaps it's just too early to say that we have a theory. I'd like you to comment on that.
Can it be reinterpreted?
Yeah. Actually, we could ask, could you, Professor Barbour, a little bit focus your question? That was a...
It's premature, perhaps, to test the Big Bang theory because we have as yet an incomplete theory of matter. General relativity is not one theory; it is many theories. I'll expand on it. General relativity is many theories. First of all, it leaves open the question of what the spatial topology of the universe is, and secondly, it says nothing about what the matter content of the universe is, what fields are present in the universe, and therefore it seems to be, it may be premature to judge the Big Bang theory for that reason.
Yeah. So that I think the very key point is that is it premature to judge the Big Bang theory based on the today available observational data and conclusions? Is that the very key?
Because we don't yet, because general relativity, which underlies the Big Bang theory,
Yes, yeah.
does not predict what the structure of the universe is.
Yeah.
Topology can be
Yeah.
closed or open, and it says nothing whatever about what the matter content is. We have no knowledge of what the matter content is.
So that he stresses the fact that general relativity doesn't predict the shape and size of the universe, neither the amount or mass. So that in fact the density, average density of the universe is a parameter in the model, which then completely determines how the development is going on. So what do you...
Well,
You can use that.
yes, I agree that there is a lot of theoretical work that needs to be done to understand further about the cosmological issue. What my problem or criticism is that it is already assumed that this is the right answer, and therefore we don't need to go further in this particular direction. So I feel this is being a bit over-complacent about the state. So certainly further research is needed in terms of Machian ideas and other issues that bring in non-gravitational forces also. So I feel that as I said in the last transparency with Fred Hoyle's quotation, that the understanding of physics is not yet perfect for us to be able to confidently say what the universe is like.
I certainly agree that there's too much complacency.
Okay. So any other questions?
Maybe I can speak up here. Your talk was in many ways very inspiring. What I would like to hear is your comment about what's the difference between a model and a theory, or do you see that there would be any difference?
Yes.
Can you comment the difference between the model and the theory?
Between?
So that when a model becomes a theory, or what is the...
Well, I don't know how to draw the comparison, but when you make a model, you need a background theory from which you make that particular model. So both things can happen, that the background theory may be imperfect and your model therefore will suffer. Or the background theory is okay, but your model is not deep enough to get the right answer. It might be both ways. Yeah.
Yes, it works.
My question concerns the microwave background radiation and the prediction of that based on the creation of helium. How was the energy treated? Was the energy assumed to be conserved, or was it assumed to be somehow diluted by the redshift of the universe?
So in background radiation is the energy conserved?
Well, I assume you are asking about the expanding universe models of.
Yes.
Yeah, the answer is that so long as you are deriving them from Einstein's gravitational equations, the conservation of energy is guaranteed. You could argue that the expansion itself has certain energy, and the frequency of light emitted as it comes to us loses energy. So that energy may be going towards the expansion. Something like that one can argue.
Maybe I can add on that according to the existing theory, the power density of background radiation is diluted in the fourth power of expansion of space. At the same time, the volume increases relative to the third power of the expansion, which means that in fact we are losing energy in expanding space due to the model, I would say. So that either we accept the model of the background radiation in the Big Bang model, and reject conservation of energy, or we accept conservation of energy, and then we can't accept the explanation of background radiation as it is today. You agree with that? Yeah.
Okay, next question, please. We still have a couple of minutes time before the coffee break. Well, then I may ask one question.
Yeah, Ari still have one question.
Professor Narlikar, do you think that the natural constants may have changed over time?
Which natural constants have changed during the expansion epoch or any epoch? Which or in general?
I think people generally prefer constants which are constant rather than constants which vary, because if they vary, then you have to give some explanation of how and why they vary. So gravitational constant or velocity of light or fine structure constant, people have toyed with the idea, but not in a very convincing way, I would say.
Okay,
So the
thank
question
you.
is partly open.
Open air, sure, very much.
Okay, if there are no more questions, then let's go to enjoy our coffee break. And we'll be back here at 11 o'clock. Thank you. Our next speaker is Dr. Heikki Sipilä, who obtained his doctoral degree from the Technical University of Helsinki in the physics department 1978. He is vice president of Outokumpu Electronics, vice president of Metorex International, chairman of board of HS Foils Company, founder and co-founder of Baltic Scientific Instruments, Metorex International and HS Foils Company. Sipilä's special expertise is in radiation detectors and in X-ray and gamma spectroscopy. Sipilä's team has designed and delivered X-ray detectors for 10 scientific satellites for the USA, Japan, India, Italy, and ESA, European Space Agency missions. Heikki, please.
Let's look first at this content of my presentation. I will tell you starting point and background of this, and then a few words about the Mach principle, and then what I mean here, what is this zero energy principle, and I tell you how Mach principle is explained by Dr. Suntola's model. And then I give literature study how this zero energy principle is presented by different authors. This is very much personal review, so that I cannot say so that it is complete, but this is the way what I have gone. And then I will give one examples of this zero energy principle and this model, this implication in our solar systems, and few words about current situation in physics. So let's start off this Mach principle and inertia. So Ernst Mach proposed that inertia of the mass is caused by all other masses in the space. So he criticized Isaac Newton because Isaac Newton defined absolute frame of reference for motion. And this Mach's explanation for inertia, this motivated Albert Einstein in his development of general theory of relativity. Even he could not incorporate the Mach principle in his theory. And what I read from history showed that Ernst Mach never accepted Einstein theory of relativity. And so this was this conflict in this time. And this quantitative explanation of Mach principle, this has been problematic, and this has been studied, of course, by many authors. In this talk, this zero energy principle, I mean here, so that this means so that total energy of universe is zero. So I have known Dr. Suntola a very long time, since 1960, and we studied at the same time in the university, Technical University of Helsinki. And I knew very well so that Dr. Suntola is very well known in material research. And for example, he developed so-called atomic layer epitaxial coating technology. And this is now widely used in microelectronics, so that practically I think everybody you have in the pockets the results from Dr. Suntola's work. So I was invited to listen his presentation. I was not aware, so that he is interested in basic fundamentals in physics. And he presented in his model explanation for the Mach principle. And on the basis of his model, one basis of his model is this zero energy principle of the universe. And I had not heard this hypothesis earlier. So this basic postulates of Suntola's dynamic universe model, they are so that space is described as a three-dimensional surface or four-dimensional sphere. And this dynamic of space is determined by zero energy balance of energies of motion and gravitation in this structure. So why I got interested to study this model? So I found, because I was invited to listen this presentation, I found so that physicists mostly misunderstood the whole idea. And I had not heard this zero energy principle earlier. Neither many physicists, they had not. They believe, I heard comments so that this may be just accidental. But I am a physicist, but my field has been X-ray detectors for space research and of course for industry. So I decided so that I have to start myself to do some studies, so if this model is real, and because I have been curious about Mach's principle, I wanted to see if this model really explains Mach's principle. So I have this slide. I have not very well documented my work because those were not made for publication, and you see this is already 17 years old calculation. I don't go this through, but I explain shortly what this means. So from Suntola's theory, there is this formula. This is Suntola presented what is the work, what is needed to change velocity from 0 to value v in space. And this work is done against gravitation of whole universe. This is this formula. And from this formula, it was easy to differentiate Newton's formula. I come directly to the end, so that I have here force, and this is this mass, and this is acceleration. F is equal to m multiplied by acceleration. But we have here some additional terms. Here is the gravitational constant, this is mass of the universe, and this is this radius of this universe, and this is velocity of light to the square. So, and if you put those values, known values to this formula, you see so that this gravitational constant multiplied by mass divided by this R and divided by c to second potential, so this is equal to 1. So, in any case, this is interesting because you see so that this Newton's formula really depends on those constants which are dependent on properties of the universum. So I think this is like tells you something about mass principle. Okay, let's go ahead. So, any case, so from those my simple calculations, I concluded so that from this zero energy principle follows mass principle, and vice versa. From mass principle follows zero energy principle. Okay, those and so, but there is one now fundamental issue in this zero energy principle. So this is written here, so that the left side, this is this mass energy of whole universum, and the right side is gravitational energy, and those should be equal. So how those can be equal? So if this radius will increase, if space is expanding, so this seems to be constant, and this will be smaller and smaller. So, so this is this paradox. So after those, my initial calculation or parallel with this, I started to look literature because I guessed so that there must be somebody else has written about this zero energy principle. Suntola invented this completely independently. And so looking literature, I started to find something. So my first hit was autobiography of Georg Gamow. He is well known. Actually, he was lived first in, of course, Russia and then in Soviet Union, and then finally working conditions became rather bad there, and he decided to escape to the West. And I think I remember, so it was one conference in Paris, and he decided not to go back. And then he moved to United States. His autobiography is very nice reading. So if you find so that I recommend to read it. Lot of good stories there. Georg Gamow, he continued cosmology research in United States, so he is very known in this field. So in this book, he told a nice story. So he was walking on the street with Einstein, going over the street with Einstein in Princeton. And he mentioned to Einstein so that Pascal Jordan in Europe, Germany, is proposing a theory so that everything is created from nothingness. And so that and the total energy of universe is zero. So he told so that Einstein stopped in the middle on the street and was close to be driven over. So, but this gave to me hint so that Pascal Jordan he has done something, so that probably first one to look this zero energy principle. So I tried to find out some writings of Pascal Jordan. So Pascal Jordan is a German physicist, and he is very well known on his role in the development of quantum field theory. I think more famous on this than in his work on gravitation. So he was one of those great German physicists, and some writers have said so that he couldn't have ever Nobel Prize because before the war he joined the Nazi party, and so it may be he made the same reason than many scientists in Soviet Union, so that this was only way to advance in a career. But any case, this is tarnished a little bit his reputation. Okay, but this is his personal history. So Pascal Jordan, he tried to develop a cosmology model based on variable gravitational constant. And I don't know if there are several of those theories or are other people developing same, but very well known in scientific literature is Jordan-Brans-Dicke theory. I think it has not been very successful because this gravitational constant does not seem to be variable. And I checked literature and found so that current upper limit is pretty small. So next person I found from literature is Dennis Sciama. He worked in UK, and Dennis Sciama, he published 1952 an article on the origin of inertia. He was only 23 years old, and he was not yet got a doctor degree. And in the end of this paper, he presented thanks for discussion to Gold and Bondi. And then Sciama, he made his PhD thesis next year on the Mach principle and inertia, and his supervisor was Paul Dirac. So I think he worked in very good environment so that he had possibility to discuss about the difficult problems without regarded to be a crackpot. So this paper is pretty interesting. So because there was no good explanation for inertia, so Sciama formulated vector potential for gravitation. Addition, of course, this scalar gravitation. So he showed in this theory, so that the quotation from his work, so that we obtain for rectilinear motion a combination of Newton's law of motion and of gravitation with the inertial frame determined by Mach's principle. And because this theory accepts this Mach principle, and when you know gravitational constant, so this gives estimate of the mass of the universe. So, and more interesting from this paper. So, he wrote, equation implies that the total energy, inertial plus gravitation of a particle at rest in the universe is zero. So I continued this my personal literature study, and I found one person I guess you have not heard before, because I think he is not at all known in cosmology. And his name is Ilan Kroh, and he is now a professor of aeronautics and astronautical at Stanford University. And what I looked his careers, he has been very successful in his field, and a lot of excellent publications, but none from cosmology. But what I found. So, as a postgraduate, about same age than Skiama, he wrote a paper, but not knowing Skiama's work. And this name of this paper is Physical and Epistemological Foundation of Einstein's General Theory of Relativity, a Critic and Alternative View. And this is never published, but how I have found this, Professor Kroh keep this manuscript on his home page. So somehow he keep this important from his student time. And it is very interesting. I don't know Professor Kroh, and so I can only guess why this is not published. Even I will give example what he achieved in this paper. So in this paper, he developed exactly same vector potential for gravitation than Skiama, based on Mach principle. Exact same formula there, and he had exactly same conclusion than Skiama, that local laws of motion are determined by the potential of the mass of universe. And he derived formula for the acceleration based on Mach principle. And you see, this is from his work. So that this force and this is acceleration, and here is this is mass density of critical mass of the universe, and this is the radius, and divided by velocity of light to square. And if you put instead of density, replace this density with volume, so you will have so the Newton's law requires so that this is 1, like he stated in his paper, and then you replace this density by volume and mass, you will have here the zero energy principle. He didn't mention this so that this is zero energy principle, but it's same formula. So why he didn't publish this? So I can only guess so that because he didn't thank anybody in the end of this paper. So my guess is so that he got advices so that it's not very good start for the career to start to criticize Einstein's general theory of relativity. So he stayed in his field last of his life where he is successful. Okay. Kroh, he found so that there is a problem because space is expanding and R will increase. So how this equation is possible? So because there is this conflict, so he had proposal in his paper, so that, and I have quotations. So according to the view of presented here, however, it is the quantity mass multiplied by square root of gravitational constant. This must be taken as constant in time, and mass is found to vary. This was his proposal. And in the end of this paper, because this was unpublished, end of the paper he wrote so that he is going to continue this work, but never continued. any case, very interesting. If you found this, I recommend to read it because it was very well written, like as well as Sciama. Okay. So, next person I found in this field is Richard Feynman. My company, 15 years ago, we had close relationship with one company in Princeton, and I used to travel there, and near university is a nice university bookstore. And I often went to look what interesting books I can find. And I found, I have bought 3 books there. One was this Feynman book I will refer soon. Next one was English translation of Newton's Principia. And third one is Professor Narlikal's Introduction to Cosmology. So let's look what is this Feynman's book. This book is published after Feynman was already dead, but from his lecture notes was made this book, and this is Feynman Lectures on Gravitation. This does not belong to this famous Feynman Lectures. You might know those three books. In this book, why I bought this, because I was looking this in this bookstore, I found so that Feynman was wondering this, so that if we compare gravitational energy and compare this to total rest energy of the universe, and you put numbers, those are equals. So the total energy of the universe is 0. So, and Feynman was wondering so that this is great mystery and important question to study in physics. So in this book was also second comment from Feynman. Feynman was proposing so that this our space may well be so that this is 3-dimensional surface of 4 square. And those two, what Feynman two quotation, they are exactly the same what Sunderla had used in his model or theory. But Feynman, he never developed any cosmology based on those comments. And I found so that he was rather skeptical on Mach's principle, and even he didn't even mention Mach's name in his well-known textbook, Lectures on Physics. Next active scientist in this field is Professor Unnikrishnan from India. We met him in London, it's maybe 6 years ago, and he also visited here. And he is active scientist in Mach's principle, and he is not only looking theory, but he is doing experimental work. I take this quotation from his laboratory. So he is calling his theory cosmic relativity, and that identifies all relativistic and kinematical effects and dynamic laws in physics as due to the gravitational effect of cosmic matter, and an elaborate program to experiment, test, and verification of these ideas is underway in my laboratory. So we are waiting forward what is coming out from his research. And I have read his papers, and he is, of course, he is when he studied Mach's principle, he is very well known its relation to the possible zero energy principle. Okay. So, okay, let's go to look, are those ideas, are they real? Is this zero energy principle, is this real? Of course, difficult to say. So, but what we know, or we have very good indications, so that total charge in the space seems to be zero, because electrons and positrons, they always appear in the same process together, or they annihilate each other, so that they are no extra charge remaining. Also, there is no evidence so that total angular momentum of space differs from zero. So space is not rotating. There are experimental data on this. And next, I have put question mark, is this total energy also zero? And what about geometry of space? Do we have any evidence so that our three-dimensional space is expanding surface of force sphere? So, what we know, so that space appears rather accurately Euclidean. And when we observe in any direction we see to the beginning, I guess so that Dr. Suntola will explain more about these geometrical effects in his presentation in afternoon. Then there are some unexplained phenomena, like periodic redshifts discovered by William Tift. And those observations, they are real, but they are not often even mentioned in cosmology textbooks. It's a pity so that in many textbooks those phenomena are not mentioned, which are not understood. And in his book, An Introduction of Cosmology, Professor Narlikar wrote on periodic redshifts, tendency on the part of the conventional cosmologists is to discount them in the hope that with more complete data they may disappear. And at the time writing those accounts, the data show no such tendency. So I have not many comments on those. Some properties of those periodic redshifts. They appear most sharply in the rest frame of cosmic millimeter wave background. And tomorrow you will hear so Dr. or Professor Ari Lehto, he has predicted very accurately frequencies of those redshifts based on his periodic doubling. Not only explained, but also predicted. So I have one comment, I don't know if it's true or not, but in any case, it appears like we are in the center of the spheres of periodic redshifts. So it's surprisingly, this is beautiful symmetry. And so, because explanation is difficult, so I have made survey of literature, and I found retired physicist Dr. Russell Humphrey, and he turned to creationist. And I looked this person, and I found so that he has really written, he has a very good career in Sandia laboratories and a lot of good papers, but he could understand this, and because it was impossible to explain those and how, and also it looks like we are in the center of universe, and he calculated so the probability is 1 to 10 to 12 or something, so that this is accidental. So his only explanation so that we must be in the center of universe and this is sign of God. So I think this is a rather old-fashioned type of explanation for physical phenomena. So it's better to look other explanation. So there are some peculiar phenomena observed by TIFT. So that redshift of galaxy, this can change in very short time, like according to his observation, into 20 years, when diameter of galaxy is 100,000 light years. So redshift of whole galaxy changes rapidly. So I will give only one comment. I don't know if it's true or not, but for me this indicates that those periodic redshifts may be energy frame phenomena on the surface of force sphere. But I would advise to look physical explanations. And then, because in any case, this zero energy universe, this has been presented by many authors. What is explanation of this? And that, as an explanation is proposed by several authors, that universe has really appeared from nothingness as a quantum phenomenon. And when this has appeared from nothingness, this explains this zero energy principle. Also, when space expanding, this means so that this everything what we have here, this is loan, and when this loan is paid back, nothing remains. At the moment, we can only guess. So, I have, during those 15 years, I have tried to be devil's advocate, and I have tried to test if the Suntula's model can explain phenomena. I have been looking phenomena from solar system, and if those will match with his theory. I have two. I will explain two of those, which are the most interesting. One is faint sun paradox. In this society meeting, I had full presentation about this. I will talk more about this, but first I will look this second one. Days in the year, they have not been same million years ago. And this is actually experimentally very well known. And how it is known? This is known from fossil corals. You know, trees they have rings, and you can calculate what is age of the tree. So when corals are growing, and you make a fine slice from the coral, you see under microscope so that they are daily rings there, and because we have winter and summer, and temperature in the sea will vary, and also light. So you can see this daily variation of those rings. So you can calculate how many days has been in a year. So when you go back to 500 million years, so it is much more days, because also there are several factors there. So I proposed this. I contacted scientists in this field. I collected papers, and this is in any case complicated enough calculation, and I discussed with Tuomo, and Tuomo calculated this, putting together, because in Tuomo's model, it's important and interesting. So solar system is expanding like whole space. In a standard model, solar system and galaxies, they don't expand. So, but when solar system expanding, so radius, distance of the Earth was smaller former days, earlier, and also this is one, and then you can also calculate, you can take account this tide how Earth is rotating, and also timing is done. Those coral, by the way, of course, radioactive decay method. You have to put all those phenomena together and calculate a model how days in the year has varied over 800 million years. And perhaps Tuomo will show this result because those results fit very well. So I can say so that I failed because I proposed this, this phenomena and this fit. Of course, this does not prove the theory, but vice versa would be serious. This faint sun paradox, I like this very much, this phenomenon. So, like Professor Narlikar told, so evolution of the sun is very well known in solar science. How this brightness is developing all over the years. And 400 million years, 4 billion years ago, brightness of sun was 25% lower than now. And we know also so that life appeared on the Earth 3.8 billion years ago. So our planet has been favorable for life, at least of course from the appearance of life, but maybe a little bit longer. So also from geology is known so that we had ocean here 4 billion years ago, but according to current studies, we know also so that there have been oceans on Mars. So, how this has been possible when sun was 25% less, this luminosity 25% lower than now? We know so that the Mars is very frozen, and if this luminosity will be so much lower, this be even deep, very deep frozen. And also Earth does not tolerate to drop luminosity 25%. All oceans would be frozen. So this is this faint sun paradox. And there have been a lot of explanation over the years. And scientists, they have tried to invent different type of atmosphere to have a greenhouse effect. But the greenhouse effect should have been same time in Mars and on the Earth. And those explanations are rather artificial. So it was now very interesting to test, to make this acid test to the theory, so that because Suntola explained the solar system expanding, this means so that Mars and Earth, they have been closer to Sun earlier. So if this can explain why we had oceans there and Mars has ocean. So I made calculations. So this some data about this faint sun paradox. So also it is known from mineralogy, so that those early oceans, they had temperature was higher than now on oceans, maybe 30 to 40 centigrade. Okay, so, but those calculations. So, here is my results. So, let's look. This first row, this is tells what is distance from Sun to planets. So, Mercury, 58 million kilometers, Earth, 150, Mars, 230 million kilometers. And those are in astronomical units. So Earth is 1 and others in astronomical units. And I calculated what was distance when life appeared on Earth. So, Earth distance wait a minute, is here. It's so much closer, 116 million kilometers. Mars also very much closer. And so from literature I looked what is so-called habitable zone. Now it is here. This maybe those are a little bit artificial, so that the habitable zone, if you see, so that could be a little bit closer to sun and also certain distance out. This is where we could have liquid water. So that we could have liquid water in this frame. How this is, I looked this literature, what is proposed to be so-called habitable zone. So then I calculated what habitable zone was according to this model when life started on the Earth. So habitable zone was closer, and when you compare those numbers, you see so that Earth and Mars, they are both they are in this habitable zone. Again, of course, this does not prove any theory, but does not disprove. This would be very bad if there would be conflict. There is no conflict. Okay? Yeah. So this, in any case, interesting, and I think this is a better explanation that what current theory will give. Paljonko? Yeah. So I don't have any more much to say, but also I have to now review what is officially accepted view about reality in physics now. So this Mach principle, this is gone. This inertia is now explained by interaction of Higgs field, and there is no role anymore of gravitational potential of the universe. This has no role anymore. And then is also explained so that university expansion, this is accelerating because of dark energy. And nobody knows what dark energy is. And this dark energy, this will increase in time. And so there is no need of energy conservation. So this tendency is, I think also Professor Narlikar said, so that phenomena, they are explained by tuning parameters. So actually this is rather bad, because good or bad, it depends from whose point of view you are looking, but theories cannot be falsified anymore. So this is rather short, but I have even shorter summary of my talk. I have here one citation. This is citation from Lev Landau. Cosmologists are often in error, but never in doubt. So this might be.
Thank you, Dr. Sipilä. We have a few minutes for questions. The talk was very interesting and illuminating, so I'm sure you are curious about asking. Heikki.
Could I ask exactly what these periodic redshifts are? Does that mean that cosmologists have measured redshifts and then they've changed and then they go back again? I've never heard of this. Could you say exactly what the phenomenon is?
So Professor Tift in USA, he has measured long time redshift using radio telescopes, which is very, very accurate. And so he has found so that looking galaxies at different distances, so redshifts, they differs very regularly. Because there is no explanation for this, like I mentioned. This is not often mentioned in textbooks. And you will hear tomorrow, Professor Ari Lehto will give maybe more information about those. Can you comment those redshift measurements, something? Yeah. Can you comment? Because you know better those redshifts.
Is it okay that I'll comment on this tomorrow morning? Because there may be other questions now, so...
Okay.
While you are still thinking, I'd like to ask you if the zero energy principle is working so nicely in our universe. Does this imply that there are no other universes nearby?
So I think we can't have any evidence from any other universe, so that, like Professor Narikal said, so best to believe so that we have only this single one universe, so that, yeah.
But then the Mach's principle would tell that we are working against the gravity, total gravitational potential of all universes. But it seems that it applies only in our universe. So it seems to rule out other universes, does it?
I cannot say anything, because I think this question is from other universes. Is of course, this is speculation. We can speculate so that if our universe is. Can we leave the question to those who live in the other universes? They can solve their own universes. Yeah, but of course, it was nice to speculate so that if this is like quantum phenomena, so that and like I said, so that this one appeared and disappeared, so then those universes, they can pop up and have different rules. I don't know. This is speculation, science fiction.
Okay, thank you, Heikki. Now it's time for lunch. Welcome back. I have the pleasure to introduce to you another distinguished speaker, Professor Julian Barber. He is a British physicist with research interests in quantum gravity, Machian physics, and the history of science. Dr. Barber has worked as an independent scientist, collaborating with several researchers in academia. He has written 2 books, The Discovery of Dynamics, which investigates the background to Newton's great discoveries, and The End of Time, which advances timeless physics. The controversial view that time as we perceive it does not exist as anything other than an illusion, and that the number of problems in physical theory arise from assuming that it does exist. That's certainly very interesting to hear.
Well, thank you very much. It's a great pleasure to be here in Helsinki. This is my first visit to Finland, and I seem to be blessed with exceedingly good weather. I won't claim I'm responsible for it. This is the title of my talk. I gave an almost identical talk in Krakow a few days ago, And for that talk, because it was translated simultaneously into Polish, I provided the translators with the text of the first 2/3 of the paper. So I'm going to read the first part of my talk from that. You see here details of my collaborators. If you just how do we press this one to go? Oh, that's the thing there, isn't it? Yes. These are the two papers on which my talk is largely based. And there is a more technical talk you can see. If you go to my website, I gave a talk in Zurich. There's a link to that. Let's go. This is a conjecture, really, basically, the whole of my talk, but I hope I can persuade you to at least consider it seriously. Now, wait a minute. How do I, this way to go forward. So the conjecture is that timeless laws of geometry and dynamics are the origin of time, structure, and beauty. And my first timeless law is geometry. Galileo said, "He that attempts natural philosophy without geometry is lost." Geometry holds the world together. It dictates how things are related to each other in space. And these shapes that you see reflect the three possible structures of space itself. Three different curvatures are possible. Whoops, wrong way. Oh, sorry about this. Positive, flat, and negative curvature. The simplest possible structure in flat space is a triangle. It always has 180 degrees. Hold the triangle anywhere in space, move it around, those angles, you will change the orientation, its position, but you won't change the fact that the angles add up to 180 degrees. This is a triangle in Euclidean space. And another thing is that the shape is fundamental. That's fixed by two internal angles. Its size is not in any sense fundamental like the shape. Size is relative. I see the size change as I move the triangle backwards and forwards, but the shape doesn't change one iota. That's going to be an important part of the story. The second timeless law is dynamics. It tells us, if we're talking about the whole universe, how the structure of the universe at one time is related to its structure at another. Here you see these are the time derivatives of the position and the momenta, and this quantity is on the right, the Hamiltonian, the partial derivatives of the Hamiltonian. That tells you how large those rates of change are. The law is timeless because its form is the same at all times. That explains why energy is conserved. It's a direct consequence of Hamilton's equations. We say that these equations are beautiful because of their symmetry, simplicity, and universality. There are so many processes that they govern. Another key fact which I should have put on the slide is this. To use the dynamical law, you need to know the state at some time. You need an initial condition. That's going to be absolutely central to my talk. And as regards the beauty of these equations, you could echo Goethe's Faust. Was it a god who wrote these signs? Now, there's a long-standing, outstanding problem at the heart of physics. All the known laws of nature, including the dynamical law I just showed, are time symmetric. You can run them backwards or forwards in time. They make no distinction between past and future, but all the processes we observe in the universe have a common direction. It's called the arrow of time. And that's basically what I'm going to be talking about. In fact, there are several arrows. The one that touches us most personally is the passage from birth to death. Why are the past and future so different? We all get older in the same direction. We never meet anyone getting younger. We're so used to that, we don't stop and wonder, is there something really deep behind that fact? Astronomers have observed billions of stars and know how they evolve. They are all getting older just like us, and in the same direction as us, wherever and whenever we look at the universe. The arrow of time first became an issue for scientists with the discovery of the second law of thermodynamics and entropy. In a closed system, entropy cannot decrease, and it generally increases. What is more, it does that inexorably, just like we age. Intuitively, entropy is a measure of disorder. You will have seen pictures like this, I dare say. Initially, all the atoms are in the small box on the left, up there. That's a relatively ordered state. Then the walls of the small box are removed, and the atoms soon spread out over the complete box, the big box. You can wait far longer than the age of the universe. The atoms will never go back spontaneously into the smaller region. There is an obvious reason for that. The atoms move randomly and are trillions in number, so it's highly unlikely they will ever go back where they were. In this example, the arrow of entropy increase exists because the initial condition is much more improbable than the final condition. That is a very special condition. Ludwig Boltzmann made heroic efforts to understand entropy. Nobody has bettered his definition of entropy in terms of probability, but he failed to give a good explanation of why it always increases. What is it in the vast profusion of nature's transformations that creates special states like the one we just looked at? You might say we put the atoms in the box, but what put us here? Boltzmann's life is a tragic example of a malign arrow. He suffered bouts of depression, and in a bad one, hanged himself. As Shakespeare said, "And time that gave doth now his gift confound." The growth of entropy in a closed system leads to thermal equilibrium or heat death. That made a huge impression on scientists when they realized it. Actually, I'll put that back so that you don't read what I'm going to say in a moment, excuse me. The general public were affected too, and it contributed to the fin de siècle gloom at the end of the 19th century. Heat death of the universe seemed an awful prospect. It was Arthur Eddington who coined the expression the arrow of time in 1928. What he said then is often quoted. The law that entropy always increases holds, I think, the supreme position among the laws of nature. If your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation. Few scientists disagree with that. But what is the origin of entropic necessity? And is it supreme? I'm going to question that. I will start by suggesting that the belief that entropy rules all may have something to do with the way it was found. It all goes back to a brilliant young Frenchman, Sadi Carnot. He was a very sympathetic man, and his name Sadi He was named for a Persian poet who was in vogue in the Napoleonic age. Sadi studied steam engines. In his book Reflections on the Motive Power of Heat, he showed engineers how to maximize steam engine efficiency. The best you can do is given by this expression here. T1 and T2 are the absolute temperatures. That difference is, T1 minus T2 is the difference of the absolute temperatures of the hot steam you use and the cold steam when you've extracted the maximum amount of work you can. Sadi showed there's a limit to that. The first law of thermodynamics says energy is conserved. You cannot get something for nothing. Carnot showed that even if you have something, hot steam, you cannot use it all in any process. It's the frustrating truth of the second law. You can get something out of something, but not all of it. That's forever thwarting engineers in the most diverse situations. Before taking this further, I'll show you two more arrows. We have all thrown a stone into a still pond. That disturbs the water at the point of entry, but soon you see beautiful outgoing waves. This is an arrow that goes from disorder to order. It's not a malign, but a benign arrow, because the same effect permits the transmission of radio waves and allows us to watch television. There is still a mystery, though. The equations would allow it, but we never see waves coming in from the banks of the pond and converging in the middle. Now I come to the master arrow that rules all arrows. It's the Big Bang. It suggests that the whole universe came out of nothing. You have to ask, was King Lear wrong when he told Cordelia, "Speak again, nothing will come of nothing"? The NASA timeline tells an amazing story. Strangely, it seems to run counter to the second law of thermodynamics. Near the Big Bang, the universe was very disordered, pretty uniform, but disordered like a choppy sea. But then structures began to form, and we get the formation of stars, galaxies, planets, and ourselves, and Helsinki. Where is the growth of entropy hiding? Well, it's within every galaxy, every star, and every one of us. What the universe creates, it also destroys. Slowly, perhaps, but inexorably. Time that gave doth now its gift confound. For all that, if you look at the big picture, it's a story of the growth of order, not disorder. The master arrow includes the accumulation of our memories and creates the sense we have of our own identity. That is very precious. Can we understand how the universe does it? Before we turn to that, look again at the picture. Can you imagine anything more asymmetric? Nothing here, profusion here. And it seems to be described by equations that give no hint of a past or a future. Is it something to do with a special condition there? This, I think, may hold the key. Carnot studied the behavior of steam in a cylinder. That is now what is called a thermodynamic system. By their very definition, all thermodynamic systems are confined. They are in some kind of box. Equilibrium cannot be established in an open space. But is the universe in a box? That seems a very strange idea. The universe is expanding seemingly forever. That doesn't suggest that it's confined. I suspect theoreticians have created the problem of time's arrows by being conceptually conservative. They have not thought to take away the swaddling clothes in which entropy, when born, was placed with loving care. We need to conceptualize differently. First, let's be clear about the significance of confinement. Experimentally, you have gas in a box. You can control the heat flow into and out of the gas. You can measure its pressure, volume, and temperature and change them in a controlled way by adjusting the position of a piston very slowly. Using the results of experiments made in this way and what he had learned from Carnot, Clausius proved there must be a further subtly hidden characteristic of the gas besides the pressure, volume, and temperature. He called it entropy and found its change, ds. The S, it seems, is for Sadi, when heat dq is added and the pressure is changed. T is the absolute temperature. And let me just emphasize that formula and entropy, absolutely impossible to discover without the confinement of a gas. Completely impossible. And I think people's intuition, they haven't shed that fact that all of this thing was discovered in a box. Soon, Clausius, Maxwell, and Boltzmann developed the kinetic theory of confined gases by assuming they consist of trillions upon trillions of molecules rushing around in all directions, bumping into each other, and crucially, the box walls. In barely a decade, they created the kinetic theory of heat as due to motion. It's a universally applicable explanation. As Maxwell said, all heat is of the same kind. Those three men created a scientific revolution. Now, what is the theoretical picture that emerges from such a kinetic theory? The natural tendency of the molecules to escape and fly off into space is thwarted by the box walls. That leads to what is called Poincaré recurrence. The gas is nearly always in thermal equilibrium. That's heat death. But there are always tiny entropy fluctuations and very rare deep dips separated by times immensely longer than the age of the universe. In fact, Nietzsche's idea of eternal recurrence is realized almost exactly. In virtually all cases, the system returns infinitely often, infinitely close to all the states in which it once was. However, the spans of time between are ridiculously long. As T.S. Eliot said, ridiculous the waste-sad time stretching before and after. This gloomy picture has a feature you may not have noted because my collaborator Flavio put that reassuring arrow there pointing to the right. But the entropy curve looks exactly the same from left to right or from right to left. Reversing Flavio's arrow changes nothing in the overall picture. It's utterly unlike that asymmetric picture of the Big Bang. As part of his heroic project to explain entropy by statistical arguments, Boltzmann came up with an idea that has captured the imagination of theoreticians. He assumed, and I quote, "The universe is and rests forever in thermal equilibrium. Only near deep entropy dips are worlds where visible motion and life exist. The direction towards the more improbable state will be experienced as the past." He's saying that the intelligent beings here will say that is their past, but the ones over here will also say that is their past. So you have two directions of time emanating there. Time goes in opposite directions. Now, there's a key insight here. Time has no pre-existing direction. It's not a one-way street. Entropy growth, said Boltzmann, puts the direction on time's world line. Boltzmann's view is now standard. Stephen Hawking says so. Boltzmann's attempt to reconcile the time symmetry of the dynamical laws with the arrows of time has very largely determined how people think about the issue. This is summarized in this slide. Boltzmann's idea there was a huge fluctuation from thermal equilibrium in the direction we call our past. I won't go into them, but this idea has severe difficulties, so it fell out of favor. However, the notion of the multiverse has led some theoreticians to revive the idea. The majority today believe the universe must have begun in the Big Bang with a very low entropy. That's why it can still be increasing today. Both of these ideas are a form of what is now called the past hypothesis, that the arrows of time are not due to timeless laws, but to some very special condition in our past. This is not an explanation, but an admission of defeat. It means modern science fails to explain the most profound aspects of our existence. Now for my idea what the real explanation could be. It starts with the simple idea that the universe is not in a box. We then see that in an unconfined system, things look very different. The next two slides are the most important in my talk. I must go through them carefully. The simplest model that gives the idea is the one that gave Isaac Newton headaches. It's three particles that interact through Newtonian gravity. That's like the Earth, Sun, and Moon, but now all alone in space. So it's just a toy model of the universe, 3-point particles. To eliminate any effect of Newton's absolute, this is where my Machian ideas come in, and Newton's absolutes were a pre-existing time and an invisible spatial frame, we insist that only the angles which fix the shape of the triangle formed by the three particles as they evolve play a role in the dynamics. And then you can show that really only solutions with vanishing energy and angular momentum are allowed. So that's the model. Newtonian gravity of three particles with zero energy and zero angular momentum. The form of all such solutions has been known for a century. It was found by the Finnish mathematician Sundman about a century ago. The motion unfolds in a plane in that case because of the zero angular momentum. So it unfolds like on that thing onto which the picture is projected. There are three particles, and their center of mass always is going to be at this point here. And in the infinite past, one particle moves towards the other two on a straight line at a uniform speed. The other two are coming in the other direction. Those two orbit each other around the center of mass of the two of them, in the beautiful elliptical motion that Kepler discovered for the planets. Unless the masses are equal, the ellipses will have different sizes, but the two motions are in complete synchrony. They complete their periods in exactly the same time. When the Kepler pair gets close to the third particle, to the singleton, there is a brief but violent interaction involving all three, perhaps with partner swap, as here with red for blue. See, there's blue there, now it's a red one. But the outcome is always the same, another singleton and a pair. The new pair, becomes ever more perfectly Keplerian. The two parts move apart, the two going down here and the third one going out. Those are the two parts of this overall system. They move apart, with ever better uniformity. Overall, it's a transition from order to disorder and back to order. Now, it's only because we have such a powerful sense of time's advance that the arrows which I've put on the diagram, or rather Flavio did, don't look suspicious. Reverse them, and the story is hardly changed. It's not identical in detail, but it's still a passage from, now in this case, from order to disorder and back to order, with the arrows going the other way. That's the time symmetry of the equations at work. It is odd. Imagine that the Kepler pair are a boy and a girl dancing towards a boy who hasn't yet found a partner. But when he meets the pair, he manages to waltz off with the girl. Her ex leaves the dance floor feeling very sorry for himself. But reverse the arrows, and now he is the one who pinches the girl. I think you'll agree it's a fishy story that can be turned upside down like that. And nothing in that picture, if you take away those arrows, which I've put there, or Flavio put them there, nothing is changed. There aren't any arrows there. It's just, that's what I mean by eternity is there all at once, like the Rocky Mountains, if you look at them from a distance. Now I'm going to deconstruct that story and give it a different interpretation. First, I'm going to take you through the original story using the successive triangle shapes now shown at the bottom. As I said, shapes are fundamental. They are all we need for a universe. You see how the same basic story unfolds from left to right as from right to left. You couldn't really decide which way to put time's arrow on that picture of the successive shapes of the triangle. This needle-shaped triangle here corresponds to the singleton there and the Kepler pair up there. They're much closer to each other than they are to the third pair. That's why you get this distance so short. When we get to this triangle, we've got to somewhere here and the Kepler pair there. When we get to the equilateral triangle, that's where they're all interacting together. And then we go out in the opposite direction and it's just the same story. Now, let us follow Boltzmann and add a direction of time only when the manner in which things change allows us to do so. Then we can say we have a direction of experienced time. It's not one that's pre-existing there like Newton thought. Then we get something like Boltzmann's entropy dips. The central region is uniquely distinguished. In both directions away from it, either going out on this diagonal, so in both directions you've got the Kepler pair going that way and that one there. So this is one diagonal. That's one way of going away from, that's this way of going away from the central point. The way going away from the central point on that diagonal is actually that story. So instead of reading it all the way through like that or all the way through like that, now you just start in the middle and read either way or that way, but in whichever way you do, you will start off where it's chaotic motion here, and you go through all the triangle shapes, but as you go out in either direction, that Kepler pair forms and becomes an ever more perfect Kepler pair. The orbital elements stabilize, and at the same time, the other particle is moving away in sort of uniform rectilinear motion. So we can interpret each diagonal, each half of the solution, as a history which begins in chaotic motion and then is transformed bit by bit into perfect order. It's like the optimistic myth of order created out of chaos, but with a twist. Now the order is created in two opposite directions. There is one past and two futures. The time symmetry of the equation is reflected in virtually all the solutions. There's a tiny set that don't do it, but that we can forget them. And these arrows of time, which we now have in each diagonal, They are created by the law. It's nothing whatever to do with any solution principle and initial condition, because every solution has that property, as Sundman showed a century ago. For us, disorder, but also we invert Boltzmann's arrows going from order. Remember, Boltzmann's arrows went from order to disorder, but we go from disorder to order. So we don't have the pessimistic twin myth in which the golden age decays through bronze into an age of rusting iron. We also see how time is created by law. Geometry gives us the triangles. In this model, they are both instances of triangles, examples of triangles, but they're also instants of time. There's nothing else that you can call an instant of time but the triangle that the particles create. There's nothing else there to call an instant of time. Then the dynamical law picks out one particular infinitude of them. Even if we found all the triangles in that solution jumbled up in a heap, the continuous change between them would enable us to put them in order like movie stills, cut from the spool one by one and thrown together. Nothing in the story is destroyed by that. We can still play the movie. The triangles, by virtue of what they are and how they differ from each other, place themselves on a timeline if we like to imagine it is there. But it does not add anything to the facts. It allows us to survey them and to grasp them in their totality. Besides prediction, that's an important aspect of scientific explanation. That's what scientists aspire to explain things in a nice, simple way so that you can look at them, to unfold them. Explain is to unfold. In fact, the law creates much more than the mere order of time's instants. It allows us to add time intervals and spatial dispositions between the triangles. As the Kepler pair tends to perfection, it becomes three things all at once. A rod, that's the length of the major axis of the ellipses. A clock, that ticks once every time the pair goes round in its orbit. And third, it's a compass, because the direction of the major axis stays fixed. It's, as the Germans say when they want an excuse for another beer, all good things come in threes. That's what we've got, a rod, a clock, and a compass. Relative to this miraculous all-purpose tool, the singleton tends to ever more perfect rectilinear motion. We even see the model universe expanding at a definite rate. The pair and the singleton get ever further apart as measured by the pair's rod. And also it's a definite rate as measured by the clock, the ticking of the clock. There is no hint of this exquisite order you get when you've got to this stage out here, in that chaotic motion there, in that middle period there. But the equations say it is encoded in the dynamics. Now, the thing that stands out most clearly in the model I've described is that if you use the Newtonian description in which there is an external scale, there is always just one single point at which the system has minimal size. I'm going to show you some equations now and take a little bit of water, if I may. Now, don't worry too much if you find the equations a bit tricky to follow, because the result I'm going to give you was found by two very great mathematicians, Lagrange and Jacobi. And in fact, Lagrange found it with the three-body problem in 1772. And in fact, our entire idea is based on this one. It's the first qualitative result discovered by Lagrange in 1772. So first of all, let me remind you, there's a thing called the center of mass moment of inertia. Here's the expression for it. It's basically, it's a measure really of the size of the system, or rather the square of the size of the system. Now, in mathematics, you speak, Euler introduced the notion of a homogeneous function or a homogeneous potential, so that you say a potential is homogeneous if you multiply all its arguments by a constant factor, and that gives you back the potential multiplied by that constant factor to some power k. Then you say the potential is homogeneous of degree k. And then it's a one-line proof using Newton's second law, which tells you that the second time derivative of that center of mass moment of inertia is equal to the center of mass energy minus this expression. K is the degree of homogeneity and V is the potential. Now, if the energy is non-negative, so it's zero or positive, and zero energy was the case of Zundman's solutions that I was talking about, then the Newton potential is negative definite, and K is -1. You put that in there, and you get the result that the second derivative of the moment of inertia is positive definite. And that means that the moment of inertia is U-shaped upwards. It executes, if this is the timeline, it executes a U-shaped curve with a unique minimum. That the time derivative, the slope of that, we call the dilatational momentum. There's the expression for it. Well, it's half of the time derivative of the moment of inertia. It's monotonic, and it vanishes just once at a point which we call the Janus point, because that divides the solution exactly into two halves, which, so to speak, look in opposite directions. And at that point, you have the minimum of the root mean square length. To find that, you take all of the separations between the particles, you square them, multiply them by the corresponding masses, divide by the total, the square of the total mass, and then take the square root. And basically, the root mean square length is the average separation between any two people taken at random here in this hall. So it's about half the size of the room. So that's that very important result. As I say, it's the first qualitative result discovered in dynamics. So now I'm going to just formally speak of Janus point systems. Now this Roman coin is fabulously appropriate because the Janus point, you must imagine, is sitting bang in the middle of these two heads. And you see that the two heads are very similar, but they're not identical. They differ. If you look carefully, you see the slight details there. In what we call a Janus point system, like the one I've just described, every solution divides at a unique Janus point. The evolution is time symmetric either side of the Janus point, and arrows of time point away from J in each half. Now I'll explain how that comes about, these arrows of time, in the model that we've done there. But so first of all, I'm going to show you another example of a Janus point system, which is those water waves. So this is the one we discussed before there. And Einstein said you never see the time reverse. Now, the law of water waves says you could see the waves coming in. But Einstein said that's very improbable because you'd have to have totally implausible initial conditions at the bank of the pond to create such waves. So he ruled that out for that reason there. But maybe the better way of thinking about this is to lift our eyes and think that we're trying to contemplate a whole universe. So instead of having a pond with a bank as a subsystem of the universe, the pond is confined by its banks. Let us suppose we just have a universe which is an infinite expanse of water, and at any one time, the waves are just restricted to a finite region. That's a region of compact support. Then actually what you will get is this picture here, which again is a Janus thing. The two orders of time, you'll just get outgoing waves in either direction. So this suggests that the arrow associated with outgoing waves is just because we're not thinking about things on a large enough scale. We're looking at things inside the universe instead of trying to contemplate the whole universe. Now I want to come back to the question of size as opposed to shape. The expansion of the universe counts as a great discovery. But in fact, we don't see the universe expand. We observe ratios and interpret them as evidence of expansion. Hubble observed redshifts, and said the universe is expanding. But redshifts are ratios of wavelengths. Easier to see are galaxies. They have an average diameter at any age of the universe, and at that age, there is an average distance between the galaxies. That's expressed by this ratio here. But as the universe evolves, this ratio is getting ever smaller. That is really all that you can say about the expansion of the universe. Now, most people say the universe expands, but a few say the galaxies or atoms are getting smaller. But both of those actually is just idle talk, if I may say so. All you can really say is that the ratios get smaller, or the ratio gets smaller. That is a fact. Only dimensionless ratios have meaning. Let me just emphasize that again with this picture here. It's all in the shapes of the triangles, and the shape of the triangle is defined by ratios of the side lengths. Now I want to come to another idea. Triangles exist in space. So this triangle is in the space of this room. However, there's an abstract space of triangle shapes. Each point here on the surface of this sphere represents a triangle shape. So say, for example, this point here might correspond to that triangle shape. So there's a one-to-one match between the points there and the shape of a triangle. And you can do that because two angles fix the shape of a triangle. You can play this game with any number of particles. With 4, you have a space of possible tetrahedra. But it's only for triangles you can make a picture. And that's because of this fortunate fact that two angles fix a triangle shape, which are represented here by latitude and longitude coordinates. They take into account a weighting for the particle masses, which in this example are taken to be equal. So the points with the same longitude but opposite latitude represent mirror images of the triangles. So you get a pairing of the triangles with mirror images. The equilateral triangles are at the north and south pole, and each point on the equator, now the equator represents the limiting case of a triangle when all 3 particles are aligned. And there are 6 distinguished points, 3 where one particle is exactly in the middle of the other 2, and then there are 3 more where one is exactly on top of the other. And as you go from there to there, one of those particles is getting relatively closer to the one on the side. And you see the whole of the abstract space of possible triangle shapes there. And I'm now going to explain the color coding. Now, we all intuitively have an idea of a uniform distribution of points and one that is somewhat clustered. Now, in fact, that's actually what we have here. You're not all sitting together in a uniform clump like a swarm of bees. There is a certain clustering here, there's 2 here, there's some there, and there's a gap down the middle. Now, I want to find some quantity, a mathematical quantity, which characterizes when a system is uniform as opposed to clustered. And I want it to be a ratio so that it doesn't depend on any external scale. And it's very easy to find one because we take, first of all, the root mean square length, which we've already had, which is actually essentially the center of mass moment of inertia, or rather its square root. So that's one length. And you see there's the definition of it. The RAB are the separations between the particles. But there's also something called the mean harmonic length, and it's the inverse, essentially, of the Newton potential, quite interestingly. So if you take the ratio of those 2 quantities, you get something which we call the complexity, or it's the clustering. And it's a very sensitive measure of clustering, because as I walk around and would come towards you, I can do that going away from the microphone because I've got a rather loud voice, I don't change our root mean square length terribly significantly. But if I go up close to, very close, it'll boost our Newtonian potential quite dramatically. So it's a very sensitive measure of clustering. And this is shown in the diagram here. The minimum of that quantity is at the equilateral triangles, the saddle points here at these things here, and then it goes up to infinitely high peaks of that complexity at those points there. So that's there. Right, now I've finished with the prepared text, and I'll just go on to do it as I go along. Now you can see the Janus point in this expression complexity. So here's the diagram we had over there before. That's one of Sundman's solutions. And here we have three things are plotted against a nominal direction of Newtonian time. There's the center of mass moment of inertia, this one unique Janus point where its derivative is flat. Here's its first derivative, which starts negative, goes through zero at that point, and then becomes positive. Now, both of those quantities depend on that invisible external scale. So internal observers cannot observe them. We don't see the universe expanding. However, what they can observe is the value of that complexity, because that was based entirely on relational quantities and depends only on shape. And you see here how it changes. Absolutely. Here's the Janus point there in the middle there. And then what are these fluctuations? Well, that's because the Kepler pair is formed. And the Kepler pair is formed in this example with quite a large eccentricity. So the two particles are sometimes closer to each other, sometimes far apart. And I said that changing of two particles getting close to each other is reflected sensitivity in this complexity function. And that's exactly what is happening here. But meanwhile, the third particle is getting further away, so the root mean square length is growing. So it goes up like that. So this is absolutely clear. You see the 2 arrows of time pointing away from the Janus point. And again, that is nothing whatever to do with any special initial condition. It's a direct consequence of the law. Every solution has that property. And this is a 1,000-body simulation. If you have 1,000 particles, this is an actual simulation. The clusters are formed, and they're all moving around out of phase with each other. And the consequence is that those fluctuations that you see in the three-body problem largely gets averaged out. So you get this very smooth ascent from there. But once again, absolutely clear that Janus point in the middle. And here's a pictorial representation. At the Janus point, the system is very largely disordered. It's like a swarm of bees, uniform distribution of the bees, but all the particles moving randomly in all possible directions. But as you go out in either direction, structures form and it becomes more structured. And I probably won't get through to it because I see my time is 10 minutes from ending. Following through these ideas, you have to distinguish, we believe, between the entropy of subsystems of the universe, which when they exist, their entropy increases, but you have to think differently about the universe. And if you can find any entropy-like quantity for the universe, it decreases with time. And it's the very fact, and you see it here, this is very uniform and disordered. This looks like thermal equilibrium, but as you go out here, you get structures formed. So the entropy of the universe, the entropy-like quantity of the universe, is going to be decreasing. But once these subsystems form, they can form with a certain entropy which will increase. So we're changing that. And to my knowledge, nobody has suggested that the entropy of the universe should not be increasing. Clausius already said in 1865, the law of the entropy of the universe tends to a maximum. But we're challenging that head on. There's a very fundamental reason behind all this. It's to do with Liouville's theorem in Hamiltonian theory. I suggest those of you who know a bit of mathematics and Liouville's theorem ask me about it, but it does explain why structure has to be formed. Well, I can say it briefly. It's to do with, there's a thing called conservation of phase space volume, which again follows in a one-line proof from Hamilton's equations. And it says that the phase space volume must be conserved, but that includes the scale part. Now, in our model, in an unconfined universe, the scale part must be increasing, but that means that the shape part will be decreasing, and we'll see the effect of that in this slide here. So, yes, don't bother about this because that's going to take us too long going in that. There's that solution there, as I originally showed it. This is it plotted on the shape sphere, on shape space. So there's the Janus point of this solution there. That corresponds to that. And then it breaks up into two halves. This represents the successive shapes as you go along one of the diagonals, and that half the successive shapes as you go around the other one. And wherever you start put the Janus point, in whatever direction you give it initially, it will finish up by climbing up those mountains of complexity. Both arms might go up the same arm of complexity, or they might go up two different arms, depending on chance. But everything that starts off here with any direction will finish up at just those three distinguished points. And that's the consequence of Liouville's theorem when you see its consequences for shape space. And this is totally invisible in this effect in statistical mechanics in all of these studies, because they all had to put things in a box. And if you're in a box, the size cannot grow. So this is why nobody's ever thought about that as far as we can see. It's a very strange fact. So here's this great question. Is the universe confined or unconfined? If it's confined, there's Poincaré. We have these Poincaré recurrences. And it's a bleak story, that one there. And you have infinitely many dips, and you have vast stretches of heat death between very brief, transient bits where there might be life. But if there's a Janus point, you start actually, instead of with order going to disorder, you start with disorder, and then you go out to order in both two-time directions, and there are arrows of time the whole time. You don't have to wait almost an eternity, many times the age of our universe, for arrows of time to appear. They appear the minute you've left that central Janus point. So it's completely different if you say the universe is not a confined system and it satisfies certain rather reasonable conditions. So what is the Big Bang? I think NASA, now this is very conjectural now because there's caveats here. But I think it's a natural thought that actually NASA is only showing half of the story. Because just put the other half, put it back there. This is actually done with a bit of a cheat because this is a mirror reflection of that one. You see, this structure here is up over there. That shouldn't be there. It should be slightly different structure on the two sides. But my collaborators at this moment are working hard back in my home in England, finishing off a paper where if we make a certain fairly reasonable assumption about the matter content of the universe, it should contain either what is called a stiff fluid or a massless scalar field. And those are not outrageous assumptions. Then what happens? Now, the universe, according to the standard story, and we don't deny it, is that its volume goes to zero. But forget the size of the system, forget the volume of the size of the universe. That's not really visible. Only the ratios are there. So if you concentrate on what the shape is doing, as defined by ratios, then my collaborators are showing that actually you can go straight through what people thought was the birth of the universe, and there's a horrendous singularity with infinitely high pressures and temperatures. We think that might be just a figment of theoreticians' imagination, that if you just look at the shape, it goes through. So this is not a bang, but a door. It's a door from one half of the solution that takes you through to the other. And it can be opened relatively easily. I think I'm going to stop at that point. There's many more things that could be said, but I think I'll stop at that point. We can perhaps go on to other things. Well, let me just show one slide, because I've got a pretty slide. I won't go into the question of whether our universe is typical, because that might well come up in there. And I've already talked about the origin of the second law. But if our idea about the origin of the second law of thermodynamics is a straight consequence, in our view, if we're right, the second law of thermodynamics must hold in any universe, and it's nothing whatever to do with a special initial condition. It follows directly from the law. And so this is when Sadi Carnot, by his devices, had improved the design of steam engines a little bit better than the first one you showed, where the horse was pulling the steam engine to do its work. And so the law of the universe creates the conditions for all steam engines, but man discovers entropy by maximizing their efficiency. And they're working on systems within the universe, not the whole universe. So this'll do to justify the story of beauty. So we think we've got a fairly good idea of the law that's governing the universe, Einstein's law of gravity and quantum mechanics. And those two laws together, as far as, if we're right, without any special conditions, without any magic explosion out of nothing to create the universe, gives rise to this picture of Saturn. This was taken by the Cassini spacecraft. I was delighted to find it. And it's rather nice with the counter-Earth, because the sun is actually eclipsed behind Saturn when they took this picture. That's what gives rise to the beautiful, somewhat ghostly effect. So, and I think everyone will agree that is a very beautiful picture. And that is just created by, as far as we know, by the law of gravity and by quantum mechanics. And all solutions should produce things like Saturn. So that's, I think, quite an impressive story. So let me stop there and we go on to questions. Thank you very much.
Professor Barber. This was truly inspiring and, I must say, mind-boggling presentation. Thank you. And I'm sure there will be many questions arising.
Yes, mind-boggling. Can time then go in both directions in two systems at the same time?
You shouldn't talk about the same time at all. If I may, let me just go back one or two slides. In fact, I go back to the one with the triangle shapes. The way I think about it, you should forget all idea that there's any time which says that this time here is the same as that time there. Let me remind you that suppose you someone had taken a photograph of your brain in all its details when you were a small boy, and now you're totally and utterly different, really. You've got in the meanwhile, all those memories in your brain. You're not the same person. And all we know is that we are in some structure now. So you should forget all about the idea that there's sort of some time out there in which we're sitting, or that you can fold that over and that time can be matched up with that. That's just the wrong way to think about it. It's just like one triangle with another triangle. You wouldn't say that two different triangles were at the same time. They're just two different triangles. And brain structures are just the same. They're just much more complicated than triangles. But my brain when I was a boy of 3 is utterly unlike my brain now. And in some ways, I'm a different person. And one just has to think that way. It's not... By the way, I'm just reading Sani Cardo's book, and it's absolutely fascinating. At that stage, they believed in caloric. And that went on until Clausius was about the first one who actually abandoned that idea. And caloric was a fluid, a special fluid. It goes back to the Greek idea of the 4 elements, one of which was fire. So caloric was a special fluid which, when you put it into a solid, squeezed the parts apart and it expanded. Time is just like caloric, I think. This idea we have that there is time out there, that there's a timeline, like a washing line, I think is just like caloric. People need to shed the idea of time as being something out there that exists without the structures that we can recognize around us. I think it is like caloric. And space is the same. The triangle, the relationships that define a triangle are completely independent of where I hold it. This is Ernst Mach's insight, that there isn't any space there really. Leibniz said space is the order of coexisting things. You don't need anything more than that. That's defined by certain numbers. It's a certain set of numbers that define a thing. If if I have, say, 10 particles and I measure all the distances between them, I get 45 positive numbers. Those are empirical facts. I put a measuring rod on top of 12, the distances between 10 particles. That gives me 45 distances. I find 45 positive numbers. A priori, they could be absolutely anything, but miraculously, they satisfy equations which then allow me to say, to give a representation by Cartesian coordinates in three-dimensional Euclidean space. But the reality are those 45 positive numbers. And the miracle of geometry is that they fit together in that way and they satisfy those algebraic relations. So just concentrate on what's given is what I say. I hope I'm not being too aggressive in my answers. I think that is an unhelpful way to think about it. I would just say that ratios are changing. I think it's a very, one of the creators of the theory of inflation, you look at his book and he explains what expansion of the universe is. He's a bit like those squares I showed. There's a small square here, there's a small square, then there's a bigger square and the bigger square. It's completely white paper. You can't see any details. And he says, that's expanding space. Come on, tell that to the Marines. What is really happening is ratios are changing. If this side, the expansion of the universe should be understood in this way, that instead of that triangle, I have a triangle where that side is there, but that side, the ratio to that side has now got much smaller. That's what expansion of space is. But people don't represent it that way. But that's the way it should be done. Because there's nothing, there's no firm ground unless you think that way. I mean, physicists always say, and engineers will agree with that, it's only ratios that have objective meaning. It's only ratios that are independent of arbitrary units, inches or centimeters that we choose. But people just forget that. Amazingly, I think the cosmologists are forgetting it. I was on a radio program with Martin Rees, the astronomer royal. I said, the expanding universe stinks. And he was very worried. He said, Julian, I think your philosophy is all right, but you're forgetting all the physics. But I think I was justified. Yeah.
Okay. Thank you. Any more questions?
Geometry means also change in energy. That means change in energy and the change in time go hand in hand. So how do you find this kind of reasoning that takes no stance whether it's a disorder or order?
Energy can, if we're going to talk anything about energy, we can only do it from relative quantities within the universe. Now, and that actually shows up in the way the universe evolves. Now, if I go back to that picture of that solution, wait a minute, where was the one with the curve? Yes, this one here. So this curve has zero energy and to specify a solution, to distinguish a solution, I choose one point where the Janus, when I say that's the Janus point, and then I choose a direction, and that is sufficient data to fix the solution. Now I can have an alternative type of theory where I need one more dimensionless number to fix a solution. And that one extra dimensionless number is what you would call Newtonian energy of the system. And it means that there's a further, for every point and direction at the Janus point, there's a one parameter family of solutions if you add energy. But they satisfy a different law. It's a different law on shape space to describe that. So if you want, and that comes in really because of Newton's use of absolute time. If you take Newton's absolute time out of the story, then the only natural law to put in is the one that is defined at the Janus point by a point where you say the Janus point is here and the particles, the system moves in a definite direction. And then energy changing to a different energy doesn't mean actually you've introduced a quantity which is the energy. You've actually changed the law of the universe. Actually, Poincaré already said that in 1902 in his Science and Hypothesis. If you talk about the whole universe, energy is actually meaning you're changing the law of the universe, not introducing a number which you can call energy.
Thank you. Questions, please.
So one question, how do you describe in your, using the idea of time, you presented such common concepts like velocity and comparing or two velocities, which are functions of, we are used to think them functions of time.
This, of course, is what Mach was arguing against all the time. Mach said Newton's laws were not verified relative to absolute space and time. They were verified relative to the framework provided by the fixed stars and by the rotation of the Earth, which is also, and you can only read that clock because there are the fixed stars. To read the clock that the Earth provides, you have to see a star, your chosen star, pass through the meridian. That defines sidereal time. So all of this familiar stuff that we have is already provided by the background universe and that we're within the universe. And this is what Mach said is the reality. Now, he didn't provide a quantitative theory of it like we have done. Initially on implementing Mach's principle, Bertotti and I did it over 30 years ago. And a huge amount of confusion has come into this because Einstein absolutely brilliantly was trying to implement Mach's ideas, but he did it indirectly and he misunderstood. I think Einstein just confused two different meanings of the word inertia. It has one meaning which is the inertial mass, and it has another meaning which is rectilinear motion, Newton's first law. And that has nothing to do with mass because it doesn't appear in Newton's first law. The mass of the particle does not appear in Newton's first law. And for some reason, Einstein seems to have overlooked this fact. And I was once having a discussion with Donald Lyndon Bell, who is a very distinguished astrophysicist, and he'd written a paper on Mach's principle, and he was telling me what Mach's principle was about. And at some moment I said, excuse me, if I can just say something. What you've just told me is your interpretation of Dennis Sharma's interpretation of Einstein's interpretation of Mach. He said, I think you're probably quite right. I've never read a word of Mach. It's fourth order interpretation. And sadly, virtually all of the literature on Mach's principle, most of the comments you read in the literature has come from Einstein's misinterpretation of Mach. Einstein, nobody's going to take Einstein's brilliance away from him. He was worth 7 Nobel Prizes, you know. But on that one specific point, Mach's ideas gave him the stimulus to create general relativity, but he set about it indirectly and in that one respect, he got in a terrible muddle.
Thank you.
Quick one there. Last. Oh, we've got a few more minutes.
I think I have a loud voice, so I don't need that. I think that we all agree that time is not like a river that flows down from the mountains to the sea. But what would you say if I said that time is just nothing else but a good and necessary tool for scientists to describe the reality and form the different kinds of models?
I would say that clocks are a very good tool. Now, how is a clock defined? It's very interesting. There's a lot of discussion of how you define a clock in quantum gravity, and I think they've missed a key point. A clock is only, you can't define a clock in its isolation. The correct definition of a clock involves at least 2 clocks, because if they don't march in step, they're useless. If I'm going to have an affair with a young lady, and we agree to meet at 3 o'clock, but her watch runs at a different time from mine, we won't meet. That might be a good thing, but never mind. But this is yeah, but there's a limit even for lovemaking. But that is why I emphasized that two particles that are forming the Kepler pair, their orbits are of different size, but they're perfectly synchronized. So each of them is a clock marching in step with the other one. And moreover, the time as measured by those two particles in the Kepler pair is also marching in step with the distance that the third particle is traversing. So in fact, if you look around the whole universe, you don't see time. What you see is vast numbers of systems that are marching in step. And I tell you, if you look in Newton at the start of his Principia, there's a beautiful passage where he derives how he shows that elliptical motion comes out of the inverse square law. And he has to, now he doesn't use the time that is defined by the rotation of the Earth, but in accordance with Kepler's law, the radius vector from the sun to the planet sweeps out equal area in equal time. And Newton's clock is the clock based on Kepler's second law. And it's utterly beautiful in that in about 6 lines of text. Newton just, without explaining what he's doing, but you can see actually that's what he's using. He's using Kepler's second law to measure the time and get the acceleration of the particles. It's one of the miracles of Newton's Principia. And he doesn't actually mention that but Kepler found his law by using the rotation of the Earth. And make one other observation. The whole of the ancient astronomy up to and well into the modern age relied upon one single clock to which we had good access. That was the rotation of the Earth or the stars, sidereal time. The laws of planetary motion could never have been discovered without that one single clock. No other clock had the accuracy that was adequate for it. So it's not time, it's things out there that march in step. I mean, as I say, it's the same everywhere. We're all getting older, together. We get older together. That's the same synchrony. That's the phenomenon we call time. But we've replaced a phenomenon which we can understand and see with our eyes by something which is invisible. But I think it's confusing us. It's sort of fog before our eyes now.
Thank you, Professor Barber. Now, there is one time, and it's coffee time, and it's now.
What, already? How nice.
So we'll be back at 15:15. And our next speaker is Dr. Tuomo Suntola. He got his PhD degree in electron physics at 1971 at Helsinki University of Technology. He has been scientist at the State Research Center, VTT, from 1968 to 1974. He is lecturer and docent at Physics Department in Tampere University of Technology, 1972 and forward. He is chief scientist at Instrumentarium Company, director of Display Division, chief scientist at Lohja Corporation from 74 to 87, managing director of Microchemistry Limited, research and development fellow at Fortum Corporation, founder and chairman of Physics Foundation Society 2008. Tuomo Suntola is the father of the atomic layer deposition, originally atomic layer epitaxy method, which allows material layer buildup, one atomic layer at a time. And as Heikki Sipilä already mentioned, we would not have our present microprocessors and memory chips without Tuomo's invention. Among many applications, also other applications, ALD has become an enabling technology for modern nanoscale semiconductor device manufacturing. Throughout his professional career, Suntola was searching for a holistic perspective to the physical reality, which in mid of the 90s crystallized to the dynamic universe model. The essential question Tuomo made is, how would the natural phenomena be explained if we assume that the total energy is conserved? Tuomo, please.
Okay, thank you very much for the introduction. Already went to the next slide. Yeah, ladies and gentlemen, as Heikki already stated in the morning, I've been working with zero energy principle. And in order to apply zero energy principle, we need a kind of from whole to local approach, which in fact is very much different as we are used to use in physics, where we observe local phenomena and then we extrapolate how the whole space at cosmological scale could look like. So we start by defining space as spherically closed structure with the energies of motion and gravitation in balance. Then we analyze the dynamics of space as whole, the whole structure. And finally, we study how the zero energy balance is conserved in local interactions in space and what kind of predictions it produces for observable phenomena. And what we will find is that the zero energy approach shows the mechanism of the energy build-up in space and produces predictions for the past and future development of the expansion of space. So it links the size of space to the expansion velocity and to time as well then. And it shows relativistic phenomena in absolute time and distance in terms of locally available energy instead of dilated time or contracted length as we are used to look them in the framework of relativity theory. And also it produces cosmological predictions that fit with observations with high accuracy without parameters like dark energy or even density parameters. Further, it discloses the linkage between local and whole in all interactions in space, and that's what is the linkage to Mach's principle. And further, it discloses the essence of mass as wave-like substance for the expression of energy. So let's first look what means local approach and observer-oriented reality. And once again, we go back to antic, like in all presentations, starting from something fundamental. So Eudoxus saw his planetary model as a geometric construction for the illustration of planetary motions. Aristotle, well, let's see what Aristotle said. Aristotle, in his Metaphysics, surprisingly, describes Eudoxus' model as the real mechanism of planetary motion. So now, first time we can see the difference, how to look the models, whether they show something of the reality or whether they simply are descriptions of reality. How about today? Distorted time and distance as the explanation for the relativity of observations is a real property of nature. That's how I think most physicists think, and that's why how Einstein expressed it in early last century. The way he expressed that explicitly was published in Physikalische Zeitschrift in 1911, and that's a direct English translation of that. So look, read very carefully. It's not easy text to understand. length contraction really exists insofar as it doesn't exist for a co-moving observer, though it really exists in such a way that it could be demonstrated in principle by physical means by a non-co-moving observer. I made the exercise several times, but I must confess that I felt still confused, maybe at a little bit higher level, but confused anyway. BBC made a much more simple description of the length contraction, so that if you are looking a cyclist and you see that she's riding with ellipses in his bicycle, then the length contraction has been observed. Okay, let's go back to physics and look at the physical point of view. So, what determines the characteristic frequency of atomic oscillators that are running the atomic clocks? Can we find any physical reason for the slowed frequency of atomic clocks in motion or close to a mass center? Or shall we blame the flow of time? And is the velocity of light linked to the observer frame of reference? So, we may question now, are the time dilation and length contraction actual properties of reality, or are they kind of epicycles in modern physics? Let's jump back to Ptolemaic astronomy, or heavens. By setting Earth at the center, Ptolemaic astronomers lost the structure of the planetary system and the observer's possible motion in the system. So what happened in Copernicus' revolution was that Copernicus introduced a system-oriented perspective of the sun and the planets, which uncovered the effects of observer's location and observer's motion in the system. So our challenge here now is, are we now looking, or are we able to find a system-oriented perspective for whole space, not only the planetary systems, in order to reorient ourselves in the system and uncover a possible hidden motion we are subject to in the system? And that's what we are going to look for. I still make a reference to Copernicus. The first chapter of Copernicus, De Revolutionibus, which was published in 1543, is titled "The Universe is Spherical." So it was a very nice reference. First of all, we must note that the universe is spherical. The reason is either that of all forms, the sphere is the most perfect, needing no joint and being a complete whole. Hence, no one will question the attribution of this form to the divine bodies. That's how Copernicus explained the need of spherical geometry, and that was in fact the book was first directed to Pope at that time. What means closing something spherically? So if we have a two-dimensional plate, for example, we can eliminate part of the edges by simply turning it around so that it forms a tube. So that we have already then created a third dimension, which is needed to the wrapping. In order to eliminate all the edges, we need to make it to form a ball. And we understand that we can't do that without adding one extra dimension to that. Now we have radius as a third dimension, which is needed in order to close the two-dimensional entity. So for closing a three-dimensional entity, our space, which we observe, we can observe three dimensions, means that we have to consider a fourth dimension, which is kind of radius to the sphere, which has surface in three dimensions. It's at the first sight, it's very, very difficult to consider a four-dimensional sphere and what kind of surface we have in a four-dimensional sphere. But it's not necessary to look all the 3 dimensions. It's really, really confusing. So we can choose one of the space direction. Out of the x, y, and z, we can choose, for example, x. So x appears in the direction of space, which means tangential direction here. And oh, thank you very much. Now the visibility is much better. Yeah, and it means that any direction in space is linked to an orthogonal direction, which is the direction of the radius of the force sphere here. It also means that wherever we are on the sphere here, we can make a similar kind of look the similar kind of coordinate system. We can also call them real directions as the space direction. So in some cases, mathematically, it's useful to look the 4th dimensions as an imaginary direction. But what is essential is that it's a direction which has metric nature and which is perpendicular to all space directions. So now we can, in most cases, if we are interested in a velocity in space, we can look the direction of the velocity in space, and we can see that it's always associated with a direction in the 4th dimension. So let's see what kind of things phenomena we may see in such a construction. If we have gravitation mass in our space, they have a gravitational attraction which results in a shrinkage force, which tends to push the structure towards the center and the mass center of the system. So it's going. Now I have to add an arrow of time through the whole thing. So it means that once we have the gravitational attraction towards the center, the whole structure contracts, it obtains velocity, it loses gravitational potential, gravitational energy, and it gains the same energy as the energy of motion. It goes to singularity and releases back the energy of motion to the energy of gravitation. So first we are losing volume, but we are gaining velocity. Then we are losing velocity, and we are gaining volume. So it's very much like a pendulum. You can see in the top position, pendulum has potential energy. It can release it, and it is converted into the velocity of motion, into velocity and the energy of motion. And once it has its motion, it climbs up back and releases the energy. So if we look that in energy scale, it means that from the beginning here, if we have a potentially infinite space, we have very, very small energies, and we consider first our masses being at rest in space. It means that we start from practically zero energy of the both component, and the gravitational energy is low, which is given for getting the velocity. So the energy of motion increases here, goes to a maximum at the singularity point here, where the turning occurs, and now we are releasing back the energy of motion back to the energy of gravitation. Okay, and this is the motion that occurs now in the 4th dimension, which we mentioned, which is the direction of the radius of the structure. So that for us staying in space, it's not observable. So it's the hidden motion. And the only thing that we can observe is the rest energy of matter. So that the rest energy can now be interpreted as the energy of motion due to the expansion of space. As I stated, the state of rest in spherically closed space is associated with a hidden velocity in the 4th dimension. The rest energy of mass m at point A here shall be interpreted as the energy of motion in the 4th dimension. So we mark it as E is mc to the second. But at the same time, due to the nice symmetry, it's relatively easy to calculate the total gravitational potential arising from all the rest of mass compared to mass m here at point A. And what we get here, gravitational potential at A, is the integrated gravitational potential for all the rest of mass in space. The reddish or violet arrows shows towards the mass. At this time, we think that all mass is still uniformly distributed. But we can easily see that the resulting gravitational attraction affecting mass m at point A looks like coming from the center of the force sphere, like here. And we can now accept using the Newtonian gravitational potential and energy in the case of uniformly distributed mass in one particular direction. Okay, what now means the zero energy principle? And the balance, it means the balance of the energy of motion and energy of gravitation. If we write it down, it says that mc to the second is m time g m double quart, which is the mass equivalence of the total mass in space, divided by r4, which is the radius in the fourth dimension. We can clearly, we can eliminate m from the equation, which now connects the velocity c, which is the velocity in the fourth dimension, which we suppose to be the velocity in the fourth dimension, and we can calculate the number because we know gravitational constant g. We can calculate the mass equivalence. It's practically almost the same as total mass. The small integration constant. But knowing the average mass density in space, we have fairly good numerical factor, and for R4 we use the Hubble radius, which is 14 billion light years. And when we make the calculation, the result is here. It says that c is 300,000 kilometers a second, which is the measured velocity of light. So this is the astonishing result, which simply means that it strongly supports this kind of zero energy assumption that we made. Okay, let's once again apply the techniques of looking one direction in space only. So it means that motion in space, the red arrow here, is always associated with motion of space in the fourth dimension. And also it shows that the momentum in the fourth dimension and the energy, we can say that the energy of motion in the fourth dimension is balanced by the gravitational energy in the fourth dimension. So in fact, the total energy is zero, but once we have motion in space, it means that due to the spherical geometry, any motion in space is central motion relative to the center of the force sphere. So it means that the central force created by the motion compensates some of the gravitational force towards the center. And as soon as we move at the velocity of light, we move like on a satellite orbit. And this is very interesting because now we can understand why the velocity of light is a limiting velocity in space, and also we don't need to define the velocity of light as a constant, but we understand that it's a result of this calculation. The dramatic thing in this is that it means also that the velocity of light is not constant with time, because as the sphere is expanding, R4 here in the equation is increasing, and it means that velocity of light slightly reduces, goes down with the expansion of space. let's look how it looks like in a local perspective. So it also means that total momentum is comprised by the momentum due to the motion of space in the fourth dimension, and total momentum is comprised the motion of space and motion in space. So that's how it looks. So we have the momentum due to motion of space, momentum due to momentum in space. And the total momentum clearly is a vector sum of these two. So this is very, very easily seen. The total energy of motion, once we apply the same formula as we have in electromagnetic radiation, which is E is C times P, we get the equation C is total energy is C times P imaginary or fourth dimension plus P in space direction. We can write it in this way or finally in this way. So the total energy, we get exactly the same formula as we get in special relativity, and what in fact can be derived from experimental data, even without any coordinate transformations starting from Walter Kaufmann's experiments. So the result was that the result here is the same as obtained in special relativity via coordinate transformations, and as I said, it could have been done even without that. And this is also the case in most physics textbooks, that they start from experimental momentum that has been measured. Now it has been obtained as an effect of momentum mc in the fourth dimension, so that it's a direct consequence now of the hidden motion we are subject to. Okay, let's continue. The complex presentation of momentum now unifies the expressions of energy. So the rest energy can be described as of an object at rest can be described as ECP, where the P has only the component in the fourth dimension, here called imaginary. The energy of motion or mass m moving in space has both components, and the energy of electromagnetic radiation propagating in space has momentum only in the space direction the propagation occurs. Well, now we obtained one very similar looking equation as we have learned from relativity theory. But let's look now, can we find physical reasons for the clock frequency, changes of clock frequency? So our question is, what determines the characteristic frequency of atomic oscillators running atomic clocks? Now we have something that Einstein and his contemporaries didn't have. We have quantum mechanical solution for atomic oscillations. So what we know exactly that the frequency of atomic oscillation can be expressed as the energy difference between the electron states resulting the oscillation divided by Planck constant h. And then the energy is proportional to the rest energy of electron, and the delta A is then determined by the difference in the quantum states. Applying Maxwell's equations without any new assumptions, we can show that a Planck constant can be expressed as h is equal to h0, what I call intrinsic Planck constant times c, which means that c appears as an hidden factor in Planck constant, and it's very, very useful to take it out there. And what it means when we do that we can little bit simplify our equation And first, so it means that now our frequency is proportional to what we can now call rest momentum of electron. These are the quantum numbers here. What is very, very interesting here is that it says that the frequency of an atomic clock is directly proportional to the speed of light. It also means that whenever we measure the velocity of light with an atomic clock, the constant result is guaranteed. So one professor in Finland called this the conspiracy of the laws of nature, so that the laws of nature are connected in that specific way that it's impossible to distinguish certain differences there. But also we can see that the frequency is directly proportional to the rest mass of electrons. Okay, the question clearly is, are the rest mass and the speed of light constants, or are they related to the state of motion or gravitation? And let's see how it looks. Now we already have the way of looking the momentum, and now we can draw a nice clock here, which tells that the frequency of clock is proportional to the length of this blue arrow here. When we add momentum in space, so it means that we put our clock into motion in space, what happens? We get the total momentum, but it's really worthwhile looking the total momentum in a little bit more detail, because we can see that it can be divided into two parts, one of which is mc, so it looks like it's like equal to the original rest momentum tilted, turned to a new direction, which comprises the two velocities here. And the extra part, delta mc, represents the energy and momentum which is due to the accelerating system, which is due to the energizing system which has needed to create the velocity. And when we look that more carefully, we can see that now that the real component can be expressed as the sum of these two components as well. So now we have the real component of our kinetic energy part and the one that originates from the rest energy, at the state of rest. Which means that once we have removed this real component from the total momentum here, it means that the imaginary component or the fourth dimension component is reduced here. And now it means also that our clock runs slower because it's proportional now to the momentum in the fourth dimension. And in fact, if we look the factor here, it's exactly the same as the factor explained as time dilation in the theory of relativity. So that now it's drawn in a little bit different way, but you can clearly see that the dilated time has exactly the same kind of formula as what now is obtained for the real physical frequency that is measured. I like to make a comparison between, let's say, the effect of the approach, whether we rely on relative observation or whether we rely on universal laws of nature. Relativity principle belongs to the first category, so that relativity principle says one way of stating it is that the observational reality is adjusted in such a way that the laws of nature we have adopted appear unchanged for the observer. So if we observe the increase of velocity with time, as we can easily do, and if we apply Newton's equations of motion here, we should have a straight line. So as long as we apply a constant force on an mass object, the velocity increases linearly without any limit. However, as Kaufman already noticed in his and published in 1902, was that, well, the nature doesn't behave in this way. So in fact, this was one of the factors behind why we needed the new theory, so that the nature works like this, so that shows that something is wrong. Whether the reality doesn't behave as we expect it to behave, or then the law of motion by Isaac Newton is not correct. Once we apply the time dilation, as we are modifying the time, and now please look carefully what occurs. Now we adjusted the time to meet the straight line, and now we have saved the Newton's law of motion. That the price we have paid for that is that our time has very, very special properties here, so that time is no more understandable for us. Universal laws of nature. The laws of nature shall apply in the observational reality where the coordinate quantities, time and distance, have univocal meanings. The observation certainly is exactly the same, so that we observe velocity under a constant force, and it looks like this. If we now choose our law of nature in a little bit different way, simply by saying the total momentum is the sum of momentum in the fourth dimension and momentum in a space direction, two orthogonal components, then the prediction we get is exactly what is measured. And what also it means is that we have saved our simple original concept of time as a universal coordinate quantities, which is used as a measure for the rate of any changes that we can offer. Okay, now clearly we have find something that is behind the effect of motion on the clocks. Let's say gravitation. As stated in our holistic view, the rest momentum or rest energy, in order to put it in form of energy, we should put it CO to the c to the second here, is balanced with the gravitational energy. So the total energy or mass, our test mass m, is 0 here. Well, and it's as long as we have the symmetric sphere, so that the mass equivalence of whole space appears really in the center, in the direction of the center of the force sphere. But once we disturb that we have a local mass center, like the Earth here in one space direction, in order to save the total energy, because we like to save the total energy here, we need to make a small trick here. In fact, the only way of saving the total energy is that we must bend the space, as already I had drawn here in the picture, so that it means that let's look first velocity, because they perhaps are the easiest thing to do, so that we get velocity v in space, the red arrow here, as the orthogonal component of the local imaginary velocity, or the local velocity in the local fourth dimension. And now we have saved the original velocity. It means that the velocity of space in the local fourth dimension is reduced when we are approaching a mass center. And in fact, on the gravitational side, it's exactly the same, so that we have removed certain share of our original total gravitational energy or mass resulting the gravitational potential, and we get a component in the real axis, in the direction of the real axis. And this is very easy to calculate, and this we get this kind of equation which has now the local mass m here, and r, small r here, is the distance from our test mass to the local mass center here. And as I already explained, the velocity of free fall in space is obtained against the reduction of the velocity in the local fourth dimension. So now we are not adding any energy in order to get the velocity, but we got it from the velocity the object already had at the state of rest. And this is a very, very interesting difference, which has its consequences. Now we can express the reduced velocity of light with this simple equation, and also we can see that our local rest energy is reduced with the same factor. The factor c in front of the momentum is the velocity in non-bended space, so that everything works well now. And now we have the equations for the frequency of our clock. And we have gravitational term, and we have a term related to the motion we have in space. So our clock, the rate of our clock is reduced, on the other hand, due to motion in space and due to the vicinity of a mass center. And this kind of mass collection in space occurs in several steps, so that you can think about that this is the mass center of our galaxy. This is the sun that creates a dent in space in the local fourth dimension, and then the Earth that makes a much more smaller space. And it also means that we can now explicitly express the rest energies in all cases. Once we make any of the reductions, we reduce the energy with a similar looking factor here, which is very, very easy to straightforward mathematical operation. So the total energy can be expressed like this. Let's summarize a little bit. Relativity of observation indicates that something is finite in our observational reality. Observer-oriented approach leads to the conclusion that the velocity of light is the upper limit for observed velocity. So that's something that is limited. A system approach we are now applying simply states that the total energy in space is finite. So we started from finite energy, and that's what we ended up with. Let's make some comparison here. Relativity between observer and an object. That's what we have obtained through a kinematic concluding that has been made in the development of the theory of relativity. And it relies on coordinate transformations, which means that certain physical factors, physical quantities, some as the frequency of atomic oscillator, is constant wherever it is, but time runs in a different way when the clock is in the motion or close to a mass center. And in the case of relativity between local, now we can say that with a local from whole to local approach, our relativity is not relativity between an observer and an object, but it is relativity between local and the whole. And of course, once we have reference in common to all states in space, we can also locally compare then two objects and the energy state and understand the difference between the rates of the clock. A state of motion and gravitation is related to the state of rest in hypothetical homogeneous space, which means here so that it's the reference in common through the system what I call nested energy frames. Let's look how the solar system looks like, so that we have sun in a dent, a bigger dent, and around Earth and other planets here we have smaller dents. And now we can easily also calculate the distances, or the depth of such dents, so that we can see that Earth, for example, here is about 26,000 kilometers higher than Sun in the fourth dimension. 26,000 kilometers means roughly twice the diameter of the Earth. So it's not in the scale of distance to the sun, it's not very much, but it's measurable anyway. Also, it means that the profile of the velocity of light can be calculated accurately, so that during the year, Earth in January is closest to the Earth, and in early July it is most far away from the sun. So the distance to the sun. Now we are looking the steepness of the dent caused by sun around in the whole planetary system, and we can see that the difference for the velocity of light in perihelion and aphelion situation here is about 10 centimeters a second. And on the other hand, when we go from the Earth to the distance, roughly to the distance of the Moon, we can observe that the velocity of light is increased by about 20 centimeters a second. And these are all measurable. Today they are measured, they are explained with a difference in the flow of time. But when we compare the equations, we can see that in the vicinity of the Earth, the distance between the general relativity prediction and the dynamic universe prediction here appears not before the 18th decimal or something like that. So it's not very easy to detect, but to distinguish these two factors. But it also tells something about the conspiracy of the laws of nature, in the sense that it's very difficult to observe the difference in our clock frequencies during the year. There are some indirect indications of that, for example, comes in the lunar laser program, but we are not going into that in detail. Also, but what I like to emphasize here, that now we understand what is the reference for the velocity of light, so that it's question of balance between the velocity of light at certain location in space and the mass equivalence of the rest of space. And clearly you can imagine, once the dent around the Earth is moving with the orbital motion of the Earth around the sun, the velocity of light, the balance follows the orbital motion of the Earth. So it says that the local velocity of light is locked to the local 4 radius of space, and there's the apparent location of the mass equivalent space, which follows the local dent here. In practice, it means that in the vicinity of the Earth, the velocity of light is locked to the so-called Earth center's inertial frame, which is used in the general relativity framework. But this shows why that is the case, and it was a very big problem during the time this measurement has been made. And this all comes from the zero energy principle, or the conservation of the balance between motion and gravitation. Let's go further. The local velocity of light is locked to the local 4 radius of space. In the vicinity of the Earth, velocity of light is locked to the ECI frame. And let's see what it means for certain experiments. The very famous experiment, which had historically very important role for the relativity theory, was the zero result of the famous Michelson-Morley experiment made in 1887, where they tried to measure the effect of the orbital velocity of the Earth on the velocity of light. But we can see that based on our conclusions we just made, it's guaranteed that the result is the same. So that it was important for the development of relativity theory, but it was in a sense a zero experiment. Another experiment which is not that often referred to is the Michelson-Gale experiment in 1925, which instead of trying to measure the velocity, the effect of the orbital velocity of the Earth, now measure the rotational velocity of the Earth. And once again, we can see that the velocity of light in its gravitational state doesn't care about the rotation of the Earth, which means that we should be able to observe a certain interference difference in the Michelson-Gale loop interferometer. I don't go into detail. That was a very nice experiment made in 1925, which is very seldom referred to in physics and cosmology book. And the reason, I think, is that it was not referred to because it was regarded as an exception to the relativity theory. It's important to understand here that there were no atomic clocks available at that time, so the only way of measuring the velocity of light was some indirect or interference, which measures the phase velocity of light, which in fact is a little bit different thing than measuring, for example, the signal transmission velocity. Okay, let's see the next experiment made in real atomic clock was Haffele-Keating, very famous experiment made with cesium clocks, which were put in commercial airplanes, one flying around the Earth eastward and one to the west. And there were a lot of speculation in the literature whether the readings of the clock should be interpreted relative to the clock at the base airport where the flight was started and finished, or whether it should be related to a rest clock in the ECI frame. And the result was that the relative velocity here don't work, but the rest clock in the ECI frame works correctly. So it means that it's a hypothetical clock which is at rest compared to the rotational velocity of the Earth. From this presentation, I skipped the gravitational term, but therefore gravitation, we make exactly the same things, such like we do in the famous Gravity Probe A experiment in 1976, which first was reported as an proof of special relativity. And if it's a very special history behind that, because I noticed that also, and I was convinced that it should be here, and I contacted Professor Wessott, who was the director of the experiment that happened in 1999, and asked him the analysis that how did they come to this conclusion? Because that was different what they originally expected. The prediction was the rest clock in the ECE frame. And after some calculation, I analyzed that very carefully, and it turned out that there was some extra terms that resulted from the so-called Doppler cancellation signal, which is drawn in blue in my drawing here. So there's a small difference between the up signal and down signal due to the rotation of Earth. And when we make this correction, we get the right result here. The report was never corrected, but that's another story. We don't go into that. Okay, then also the Sagnac effect can be now understood directly. It's not any separate effect, but it only results from the fact that during the flight time, transmission time of the GPS signal, our observer moves certain distance, which makes the final distance longer. In the literature, it's called as relativistic Sagnac effect. Okay, let's say cosmology. Let's look at cosmology. What it means in a very large scale. And now I show some of the same pictures as we already saw in Professor Barbou's presentation. So that's the present interpretation of standard cosmology model. I don't go into details here, but what we should add here is that everything starts from here. When we apply the zero energy, let's first look what happens in the expansion phase here. So it looks like this. It looks quite much the same as here, but now we have explicit relation between we have mathematical expression to the development of the size and to the development of the velocity, so that there is no extra parameters. But we can look, we look back in time. However, we are not changing the arrow of time here, but we get very similar picture as what we saw. So in the contraction phase, we are first we have first energized space by converting gravitational energy into the energy of motion, and now we pay back the loan we have. In the energy scale, we have the symmetry back in time and in the direction of time, so that in terms of energy, this looks very much like the time arrow in Julian Barboux's presentation. Now we have two alternatives. If the relativity principle and the equivalence principle are postulated, then the geometry and the development of space is unknown. The velocity of light and the rest mass are constants, and the coordination quantities, time and distance, become functions of the gravitational state and the velocity of the object. If we choose zero energy principle in spherically closed space, then the geometry and the development of space are determined. And the coordinate quantities, time and distance, are constant, but the velocity of light and the rest mass become functions of the gravitational state and the velocity of the object. That's our choice. We can build our models into these postulates here, if we like, and we can build them into these. And our predictions may look much the same, but certainly there can be found differences. Let's see some very principal differences. From relativity principle, we have problem with the concept of time, and it has raised a lot of literature and different kind of solutions. Also, this is true for the state, for understanding the state of rest. In the energy approach, the state of rest is very clear. For any motion, the reference at rest is the state where the energy for obtaining the motion is obtained. So it follows bookkeeper's principle. So loan is paid back to the one who has given the loan. Very simple. Some cosmological consequences here is that the angular size of distant object is magnified. I will show a closer look on that shortly. Also, magnitude of distant objects suggests dark energy and accelerating space. Equivalence principle has one very dramatic consequence, which means that orbits near black holes are unstable. And we can quite easily find out the reason for that, and it comes from the difference than when we are up there, which I already showed, so that somebody might have noticed it already, that when we create velocity at constant gravitational potential, we have to inject some extra energy in form of mass equivalence of electromagnetic energy or something else. But in the case of free fall in space, we get the velocity without increase of mass. And I tested the relativity equations that if I eliminate the effect of the relativistic mass increase, then I get stable black holes, like I have in the dynamic universe. In zero energy principle approach, the frequency of a clock is determined by the energy state, which can be defined for any state following the history. Each velocity has its history, so it has started from the hypothetical rest. It has certain value in galaxy groups, in galaxies, in planetary systems, orbitals, and so on. And finally, we can determine the precise energy. Also, the distant space now appears in Euclidean geometry, and the most essential difference for this is that, one essential is that looking the total conservation, then it means that all gravitationally bound systems follow the same rule, so that once the total system is expanding, then also the local systems are expanding. So that is one factor, together with the spherical geometry, that gives the Euclidean appearance of space. What is very important is that we don't need any dark energy anymore, because we get a prediction without any parameters. We get orbits near black holes which are stable, and also it shows that there are very slow orbits near the critical radius which maintain the mass of the black hole. So there is no magic point-like masses in the black hole. And the very last thing which I tested recently was the shortening of the double star period due to the rotational, which is said to be the energy released to gravitational radiation. And here I can see the explanation from the rotation of the orbital plane, of the angular momentum of the orbital plane, which is a little bit different explanation, but the prediction is very much the same. What is expanding and what is not expanding in a dynamic universe? So gravitational systems expand with the expansional path. Electromagnetic objects like atoms conserve their dimensions, and the wavelength of electromagnetic radiation increases in direct proportion to the expansion of the four radius. Some examples here. These are observed angular sizes of galaxies. The horizontal axis here is the redshift, which describes the distance of the object, and this is the angular size which is measured. The prediction of the standard model equation is down here, and using the original parameters, we have only ordinary mass, no dark energy. The prediction looks like this, and it doesn't look very good indeed. When we add the dark energy as what we have done, we get a little bit better result, but not very much indeed. So that the dark energy doesn't solve this problem. In the case of dynamic universe, our prediction is that simple, which comes from the spherical geometry. Geometry is simple, the prediction is simple. I stated that all gravitationally bound systems expand with the expansion of space. Heikki Sipilä used that argument for the faint sun problem, but there's one also a very precise measurement, which is the lunar laser ranging, which states that the distance to the moon increases about 38 millimeters in a year. The observation, of course, is the same in these both theories. According to general relativity or standard cosmology, nothing comes from expansion, and tidal interactions are responsible for the whole change. In dynamic universe, 28 millimeters comes from the expansion, and 10 millimeters comes from the tidal effects. And the very unique observational data came from what I got this from Heikki Sipilä. So he had found the measured number of days in a year in old coral fossils where the oldest one extended to something like 800 million years back. Well, according to this expanding universe, we can compare the development of the rotational speed and the orbital speed, which gives the first term here, and the second term here comes from the change in the moon distance. And this I have to estimate a little bit the linear term, but this is very precise without any parameters, but the result is very, very precise. So we can see that the shape of the curve fits exactly with the observations. Perhaps the most convincing is then what we get from the supernovas. So the observations are this. So there's absolutely no observation of the acceleration of expansion. The only observation is the magnitude, which means the brightness of the object, and as a function of the redshift, which is the horizontal line here. The standard model without any dark energy is not very bad, but it clearly shows that something is missing here. Once we add in the equation here omega lambda, certain amount of dark energy, we get it fixed quite well, quite nicely to the observations. So let's look the better prediction and compare that to the predictions and the curve obtained with the dynamic universe. So as you can see, the prediction here has no parameters. It has no density parameter, no dark energy parameter, and it's very simple, and it's the blue curve which fits extremely well. When I remove the standard model here, you can see that the fit is really perfect. One surprising result, which in fact I made this calculation several years ago, but it became interesting after the LIGO observations. So it was the decrease of the period of double stars, and the explanation in the general relativity is that there's certain energy loss resulted by the emission of gravitational wave due to the rotating quadrupole moment of the mass systems. I made a little bit different thing by stating that any elliptic orbit has an angular momentum in tilted fourth dimension, and rotating angular momentum means certain work that is made, and I calculated that work, then probably is the reason for the reduction of the orbital period. And surprisingly, I get practically the same result. All the terms here are these, the constant term here is 123, I have 120. These terms are equal and the mass terms are equal. The only difference comes from the eccentricity terms. So I compare these two. How do they look? In the general relativity case, there should be loss of period even for circular orbits. In the dynamic universe prediction, there is no reduction for completely circular orbit, but once we have eccentricity, the two predictions meet each other. And if we compare the famous Taylor experiments, the binary pulsar, which has eccentricity of 0.0 and a little bit more than that, the two predictions are equal. I close my talk with some final conclusions. The zero-energy approach describes the energy build-up of space as a balanced interaction of gravitation and motion, and produces a detailed description of the observable reality in absolute time and distance, essential for human comprehension. There is nothing separate in space. Any object in space is linked to the whole, and any mass object contributes to the gravitational potential of the whole. The rest, I think, for me at least, this is philosophically very, very interesting and important. The rest energy or mass object is counterbalanced by the gravitational energy arising from all other mass in space. And a state of motion is primarily characterized as an energy state, not as a state having characterized as velocity. Any motion has its history which links it to the state of rest in the local frame and through the system of nested energy frames to the state of rest in homogeneous space, and finally to the contraction-expansion process of whole space. And another very interesting area, which we have not time to go into any detail, is that mass can be characterized as the wave-like substance for the expression of energy, and localized mass object as mass wave resonators with Compton wave momentum in the fourth dimension and de Broglie momentum as a mass wave in the direction of the motion of space. And now I thank you for your attention. Thank you.
Your work aims for a better understanding of the universe, and I think this is exactly what it does. But I wonder if you have several questions concerning Tuomo's presentation. Please raise your hand.
So it was fully understood. Oh, that's the best I can hear.
As far as I understand, the present theory of the general relativity states that the gravitation proceeds with the speed of light.
Sorry, can you put the microphone a little bit farther away so that I could distinguish?
Sorry.
Oh, please, yeah.
The present theory of relativity states that the gravitation proceeds with the speed of light.
Yes.
Did I understand correctly that in your model, the gravitation effect is immediate?
Yes, yes, it is very important indeed, because the very fundamental difference is that I start from potential and from energy instead of forces, so that each mass carries its potential profile along with it all the time, so that once the mass is moved, the potential profile around it is moved. And the local gravitational force is simply sensing the local gradient of the local gravitational potential. So that's why it's local. And this is very important. And historically, this is interesting because Laplace showed it very clearly that the stability of the planetary system necessarily demands instant gravitation. Poincaré reminded Einstein and others at that time from that fact. But then as a gentleman he stated that maybe this new theory then creates some term that eliminates, that compensates the problem. But as you know, Laplace developed the accuracy of celestial mechanics to an unbelievable level and explained all the known occurrences that were observed. So, answer to your question is that there is no delay in gravitational interaction because the quantity to be sensed is there already. It's a local effect.
I think one has to make a distinction between the propagation of gravitational waves, which is just like light goes at the same speed as light in Einstein's theory, and the Coulomb or the Newton potential in the solar system, which in accordance with Einstein's theory is actually due to equations which hold at one instant. Einstein's equations consist of two parts. There's a part which says how the universe, the gravitational field must be at a given instant of time, and the second one where it evolves. And the behavior of the Earth around by the Sun is described by is due to those equations which hold at a given instant of time. They're called constraints. And then the evolution is where the speed of light or of gravitational waves comes in. So those are two distinct things. So there's no conflict there with Einstein's theory.
Yeah. Okay. Yeah, that's a very good question indeed. And when I when we heard the news of the observations or something that can be interpreted as gravitational waves, it of course raises the question: how is the gravitational waves? We could see that the energy that is said to be behind the gravitational waves comes more or less the same way in this theory. But what I'm saying here, what is the result? Energy doesn't accumulate in the rotating orbital momentum, but I could well see that what is emitted there is not can be called gravitational wave, because potential wave doesn't carry energy. If we carry energy, we can call them mass wave. Now we didn't go into detail what means mass wave, but we can clearly see that it's really possible that we can describe the energy flow as a mass wave, which naturally have the velocity of light, because that carries energy. Potential doesn't carry energy.
Yes, a simple question from a commoner. Do we now at last have a simple and beautiful equation between universe physics and quantum mechanics?
So beautiful equation of what?
Between universe physics and quantum mechanics.
Yes. Yeah, it's a little bit longer story, but let's see. I have some extra slides here. The very essential thing is that we describe a mass particle as a mass wave resonator. So it behaves exactly any symmetry in space directions. In a resonator, we have equal momentums in both directions. In such a kind of symmetry, we can describe the momentum. It's not disappearing as the vector sum does, but it appears in the fourth dimension. And that's a property of the spherically closed structure. And that is the mechanism that connects the rest mass to the mass wave to the gravitation, because the energy and momentum in the fourth dimension is balanced with gravitation. So that gravitation is always the negative counterpart of the positive energy of motion, which may appear both in the fourth dimension and in a space dimension. And if we take energy as a scalar, it's the sum of these two. I'm afraid that I can't go very long here, but it's very interesting to know that once we put this kind of resonator in motion in space, the difference, the Doppler shift of the back wave and front wave creates the de Broglie wave. And now, once we have removed the velocity of light from the Planck constant, we can interpret it, this mass wave, moving at the velocity of the moving object. And this is very interesting because we can now put our particle in motion, so there's always the mass wave, which works like an Aristotelian mover or impetus around the particle, and now we have very nice connection to the idea how a mass wave can be created without, as you see here, we didn't need the wave function here for the localization of the mass particle, because we needed to handle that as a resonator. to make it a resonator means that we need some local potential energy to keep that together, and that's where we need electricity and something else.
Thank you, Dr. Suntala. Our non-distorted clock demands a new presentation here.
Okay, now Avril's picture was, I have to take it here, for you to introduce Avril. This gentleman is here. Nyt se täytyy, mä operoin tänne tästä vielä.
Our next speaker is doctoral student Avril Styrman. He is a postgraduate student at the University of Helsinki, and his forthcoming PhD thesis is Applying the Method of Economical Unification in Metaphysics and Philosophy of Science. The thesis introduces economical unification as a method of philosophical analysis as an alternative to plain conceptual analysis. In the method, concepts are disambiguated and problems are resolved in the context of an openly explicated minimal and unified worldview or ontology that is philosophically and scientifically sound.
I have to put this down here and open this one from here.
All right. Thank you, everyone, for coming. I try to be very brief so we can get out of here quickly. Yeah. As you see, the title is The Principle of Economy as an Evaluation Criterion of Theories. Now, all you need to understand about this is in this picture. So you can see that the tiniest weight has number 1. So the whole core idea is that the lightest theory that explains the perceptions is the best. Okay, we'll go through first principle of economy, basic formulation, then look at the structure of theories and why economy is needed. Then the notion of economically unified theory as something that brings together theoretical virtues. And last, the evaluation of the standard model of cosmology against Suntala's dynamic universe model. Of course, evaluation by the principle of economy. So, it simply states that given two theories with equally accurate predictions, the metaphysically simplest is the best. And another formulation below, if you have all theories in one basket that give the most accurate predictions, there may be several, then you take all that have the simplest sum of metaphysics, if you have two or more, and just select one of them. So we have two criteria here. That's empirical sufficiency. So just select all theories which give the most accurate predictions. Explanations, they explain the perceptions or observations and say the phenomena. And the second is metaphysical simplicity. And if you have some metaphysical postulate, it's the same as it's an unobservable. They've been called brute facts or primitives or axioms or unexplained explainers. Now comes several compatible or congenial formulations of the principle of economy. We can see that all these 4 formulations, they state that if you don't need something, there's no need to use it. So if you have the minimal unified theory, so what these people are saying that, okay, if it's sufficient, then it is. No need to add more metaphysics in it. And here Ernst Mach and Einstein, they are both saying that the goal of science is the simplest expression of facts. So Mach says that it's abstract expression. Of course, we have theories, they are mental constructions. And the goal is to have the simplest mental construction or theory that explains everything. And now, as you see, today is a celebration year for Mach also. And then Eino Kaila's formulation called relative simplicity. So you just divide the number of empirical propositions that are derivable from the theory by the number of its postulates or metaphysical postulates. So you divide its explaining power by the number of metaphysics. So it's basically the same as the principle of economy. And here we have basically 3 very similar reductionist formulations. So they all say that we have just some basic postulate base. We like to be minimal, and then we reduce or explain everything in terms of this kind of a minimal postulate base. So if we do that, then we have economical total science. Okay. And here's 2 more modern formulations. Well, Dewitt says here that basically the same as the principle of economy, the less the better. And the latest formulation I could find is from the famous book. They call it the principle of naturalistic closure. So if you take this new metaphysical claim that unifies something that was previously separate, then you have a theory that explains more with less, or at least as much with less. Okay. And now let's look at theories and why the principle of economy is needed in evaluating them. Okay. And the conclusion is it's needed because there are no practical alternatives for using it if the progress of science is the goal. So we can look at theories as fusions of ontology and the concepts defined in terms of the ontology. Now, ontology is what is supposed to exist, and then all the rest is defined in terms of the ontology. With philosophical theories or pre-scientific conceptions, the concepts are very important, but with scientific theories, they are mostly dealing with ontology only, as this example shows. So of course, all these objects are supposed to exist, and of course, ontology is what is supposed to exist. Also, the orbits are supposed to exist in the sense that the planets are supposed to go on those orbits, and some kind of a universal law of gravitation is supposed to hold between the objects. So this is all ontology. And then we can have, for instance, the concept of time defined in terms of this change of these objects. So when these objects change, time has gone forward. Here's an example of how concept is defined in terms of ontology. Again, the same thing, but now we look a little at the ontology. What does ontology consist of? The basic idea here is that ontology consists of verified beliefs and metaphysical beliefs. So we perceive objects like the sun, the moon, and other people, and our perceptions yield verified beliefs. And they are verified because they are verified by direct perceptions, direct or indirect. But the verified beliefs leave over questions which are then explained by metaphysics. So that's why we have ontology as a fusion of verified beliefs and unverified beliefs, where everything that is supposed to exist but is not verified to exist is called metaphysical. And the metaphysical beliefs, they are not themselves, of course, not verified, but they explain the verified beliefs. Okay? And why we need to evaluate the metaphysics is that basically all theories can be considered to have the same verified part. Whereas different theories have different formulas, concepts, and metaphysical postulates. So we must evaluate the accuracy of formulas, the fitness of concepts, and the complexity of metaphysics, because this is all we can do. Because you can't very easily deny that, okay, the sun isn't there or something. So you must evaluate what you can, and that's basically scientific theories, the accuracy of formulas, and the complexity of metaphysics. And much of the following is concentrated on showing that accuracy alone is not enough. So we have here the famous comparison of two models that in principle could give equally accurate predictions. But even if they did, this one would be metaphysically more complex than this, because these epicyclic orbits are more complex. So the principle of economy favors this one over this, because this is simpler. And the same thing in other words. So your model does not explain perceptions as such, so then you can complement the model. When you complement the model, you in fact complement the reality. So if the reality does not match your model, then you can always complement the reality so that it does match. And that's why we need to evaluate also metaphysics. This is a famous problem in scientific realism or philosophy of science called underdetermination. What is said here is basically that we can have two theories that both conform to data, but we can't. The data alone cannot make the selection between the models. So they are underdetermined by the data. So when we have the principle of economy, the underdetermination challenge is tackled because we can measure their metaphysics. And we already reviewed in earlier presentation Popper's falsifiability criterion. So a scientific theory should be falsifiable. Okay, but if, don't mind this, but if the theory is not falsified by any counter instances, then it's not falsifiable. Where has the falsifiability falsifiability criterion disappeared. Here are the supernova perceptions of the standard model. What this shows that this is without the famous dark energy, and this is with the dark energy. So you first had a theory that was in a way falsified because it didn't match the predictions. Then the falsification was like dumped by incorporating dark energy, and whoops, now it again corresponds to perceptions with the dark energy. So if we just can increase the number of parameters without no limits, then theories are not falsifiable. But if we take the metaphysics, that is the parameters in account in evaluating theories, so that counts for the falsifiability, because more metaphysics, the worse the theory. So kind of principle of economy takes in account falsifiability as far as it can. Another challenge is the challenge of pessimistic induction. So if all theories are always rejected, then all theories are false. Our present theories are false. So no theories are true. So we are together dealing with, today, dealing with false theories. And the principle of economy is not tied to the notion of true or false, because we have just more economical and less economical theories. So it's an approach to the pessimistic induction challenge. So we make a shift from true to more economical. And a similar shift has been made in scientific realism from true and false to approximately true. So if all theories are in any way false, we want to sustain some notion of truth, so we replace truth by approximate truth. And there are two basic approaches of defining approximate truth. So one is formal and the other is informal. The formal path has meant contemplations without any metaphysics, practically, or with hidden metaphysics. But in any case, without contemplating in any way what kinds of postulates are at play in physics. Certainly, it's not typical in philosophical literature to evaluate the models of physics. And the informal path has meant characterization of theoretical virtues, including simplicity of metaphysics and empirical sufficiency. So it's basically the same as the principle of economy, or very close, that informal path. And now I'll proceed on this informal path, maintaining that this concept of an ideally unified theory brings together all theoretical virtues. And I contrast this to this disunified sum of theories that has all the vices and here are all the virtues. The basic idea is that if you have these virtues, then you have a progressive science, but if you have these vices, then you're dealing with bifurcation. So the first notion is that if you have an empirically sufficient theory and it is genuinely unified, then it's also metaphysically minimal. Okay. You can look at these three half circles. They are shifted from here to there and unified in one, so we get this overlapping parts. So these overlapping parts mean that there's less metaphysics. So we get the same explanations with a less cost, and what is, of course, more economical. And this disunified science, where there are many disunified theories, they have in sum the greater amount of postulates. And we reviewed quickly Nagel's and Oppenheim-Pottham's and these reductionist models, Kaila's relative simplicity. Of course, if we have this smaller set of postulates that explains exactly the same as this greater amount, so we have a greater relative simplicity here, and we have achieved what the reductionist models have to say. And when you have everything unified together, then you can understand it. It's a lot easier to understand like one theory of everything that is coherent than to understand completely, not completely maybe, but anyway, isolated theories, like one theory of cosmology, one theory of one quantum theory, something in between. So it's takes a lot of more efforts to understand three different theories than to understand one. And here, Ville Martikainen, who just arrived, comments that a good theory describes its target in an understandable way, explains logically, and predicts its behavior accurately. And understandability and comprehensiveness, they're interrelated, because if all aspects, central aspects of nature are incorporated by the theory, then, nothing central is left out of the picture, and that's why it can be understood. For instance, in contrast, if you look at this, the one half is missing, so it's quite difficult to understand the reality if you have only one half of it. And consilience, it only means that multiple sources of reference or support the theory. So you can arrive at the theory from many different directions. So I illustrate here, we have three different theories with postulates A, B, C, D, E, F, and one unified theory with three postulates. Okay, this unified theory might alone have more postulates than any of these three disunified theories. But when these are counted together, these postulates are less than all these together. So eventually we should evaluate all theories that in sum explain everything and their postulates together. So that's the only way we can objectively eventually evaluate theories. Okay. Consistency, coherence. we must have a coherent theory whose postulates and everything is are compatible. So if we have an incompatible or incoherent theory, or we have contradictions in the theory, then we have a good reason to doubt that does it really explain something if it's contradictory. And if it's contradictory, we really cannot understand it. And if we really had this ideal unified stage, then external coherence would be quite misleading because there's nothing external, because everything is just one theory and everything else then is derived or defined in terms of that one theory. Whereas if we have these disunified theories, we can naturally have contradictions because their postulates might contradict one another. Ideally, the postulates are simultaneously sufficient and necessary. So if we have sufficient and necessary postulates, they are also metaphysically minimal. Of course, if you have only the necessary postulates, you have also the minimal postulates. And I present two examples of philosophical theories. So we can have a theory that commits to many, many worlds that we already saw in Narlikas' presentation, but all theories must commit at least to this world. So if this world is sufficient, necessary, this world is necessary, but if it's also sufficient, then it's necessary and sufficient. And a theory may commit to whatever combination of the existence of past, present, and future. But all theories must admit that at least the present exists. So the present, it's at least necessary. But if it's also sufficient, then it's necessary and sufficient. So our goal is to have a necessary and sufficient postulates that are metaphysically minimal. And if we have this ideally unified theory, it must be a fusion of philosophical theories and scientific theories. Like scientific theories like cosmology, and we must explain all scales, like atomic scales. Then we have the must unified with this philosophical theories like presentism and naturalism, one world theory. And when we evaluate these theories, I mean, we evaluate the one unified theory against, for instance, 3 disunified theories, we must take the scientific and philosophical postulates in account. Because some scientific theory might dump the metaphysics under the rug by incorporating like this philosophical postulates. For instance, many worlds or existence of the past might result from the scientific theory. So we must take that in account. And it's also compatible with the general ideology of unification that the philosophy and science are one. They are not so different at all. They are all unified in one. There's also an approach to fundamentality. While theories in neither class, philosophical or scientific, they're not considered as more fundamental than in other class. If we have genuine fusion of both classes of theories, we can consider that as more fundamental than some only scientific or only philosophical theory. Now, there are many different approaches to fundamentality. Basically, all combinations are listed there below. And finally, we can ask that why should we favor the virtues? Why should we have virtues theories? What's the reason? Why wouldn't we have virtue theories with vices, for example, instead? So the only justification is in the end the progress of science. If you have light theories that are easily learned and easily understood, well, it's quite natural that people are better off with those theories. And then it's easier to achieve progress of science. So the defense of economical unification, it only relies in the end on the progress of science. Basically, if you have a virtuous theory, you have a high probability that it works. And if it works, everything goes fine. It's so simple. Now, we go to the evaluation. That's the final stage. DU versus the standard model. And of course, we apply the principle of economy in evaluating the theories. So everybody can contest the principle of economy, and everybody can contest the conclusions, but it's open criterion, and everything is open. You can all see yourselves. Primary notion is that okay, DU offers postulates that are sufficient for all scales. That makes it to start with a unified model. And if we would evaluate it thoroughly, we would have to evaluate all theories in all scales. But we only evaluate now the scale of cosmology and celestial mechanics. That is like everything from the scale of the solar systems or star systems. First, let's look at the implications of the relativity principle. We go a little bit deeper in both of these cases. So, relativity principle contradicts absolute simultaneity, and therefore it contradicts the notion of cosmic time, conservation law of energy too. What the relativity principle means that there's no time that is the same, for instance, for the Earth and Alpha Centauri, because it especially says that time is relativistic, so different parts of the universe have different times. And we need to talk about the age and size and density, mass and expansion rate, or total energy of some temporal stage of the universe. That means we're talking about all its parts at one time. There are two sources, Lehti and Janssen, they both know several instances where Einstein himself is talking about using cosmic time when talking about the form of the universe. So let's say again that you say that the age of the universe is like almost 14 billion years now. What do you mean with it? Of course, you mean the universe as a whole. Otherwise, what does it mean? And when you say that universe has some size, what do you mean by it? If its diameter is something, you must talk about all its parts at the same time. But the relativity principle contradicts this very thing. So we have the special relativity principle of relativity principle there, general relativity, inherited relativity principle. Then we have the standard cosmology built on general relativity. And in cosmology, we must talk about universe as a whole. But the relativity principle contradicts this very thing. So it's kind of a problem how to fit together the relativity principle and when we still must talk about the universe as a whole. So it's really, it sounds like a contradiction, but who knows what it is? I don't know, nobody else knows. In DU, there's only cosmic time and absolute simultaneity. And another strange implication is that we have these theories of temporal existence. So the simplest of these is presentism, where only the present exists. The past did exist, the future will exist. But theory of relativity, or the relativity principle, it entails eternalism, where the past exists and the future exists. So all these times exist equally. There are several proofs around this. And of course, it's more complicated metaphysically to have the past existing and future existing simultaneously as the present. And it doesn't end here, because we must couple it with either partial or total determinism. Now, if we couple it with total determinism, so we get this just one straight line. But people complain about this because then we don't have free will and everything. We have total determinism. So if we couple this eternalism with partial determinism, we get this kind of a branching space-time. Now here's the present. It exists, but also the past and future exist, plus all these branches exist. And there's Noel Belknap. He especially tried to combine theory of relativity with partial determinism, and this is what you get. It doesn't end here, of course. So if you have eternalism, any version, then it doesn't have a direction of time. So the question arises, what is the direction of time then? If the past exists, present exists, future, they all equally exist. What is the direction of time? So as we saw in Julien Barbour's presentation, Arthur Eddington proposed that entropy, that's the anchor for direction of time. Now, when entropy increases, time goes forward. But the problem is that if you have an entropy, in order to make it applicable, you have to commit to total entropy of the universe. But if you commit to total entropy, then that contradicts the relativity principle. So we have here, oh, it has disappeared there, but it says the relativity principle. So first we suppose the relativity principle, and then get eternalism, what was this, as an implication. And then we have the problem of how to define the direction of time. And then people selected entropy as the anchor. But if you want to apply entropy as an anchor, it must be the total entropy of the universe. Otherwise it doesn't make sense. But if you have the total entropy of the universe, you must talk about the universe as a whole, which contradicts the relativity principle. So this just testifies that the relativity principle is like a nice, strange creature that has all sorts of funny implications. And it has, of course, mixed up the whole philosophy of time for more than 100 years now. Okay. And now we have in the standard model, we have 3 different 3D models of, or 3D geometries of space. It's an open question. And here in DU we have one 4D model. So there's clear difference here. Again, the expansion hypothesis that we saw in the previous presentations too. So first notion is that the standard model requires the density parameter with the dark energy, about 70% of the total energy. A very big deal. And DU does not need the density parameter nor the dark energy, of course not. So to illustrate, again, same picture, we have the supernova predictions, then we had the standard model without dark energy that misses the target quite much. That's why it had to be corrected by the dark energy. Now we have the corrected model, and then we have DU's prediction without dark energy. So no problems if you add some parameters. And again, the same picture. We have a little bit more parameters. We have here the accelerated expansion, and we have here inflation. So 2 more parameters, and the dark energy. So here we don't have dark energy, no acceleration, and no inflation. So the same thing explained, no special parameters. And also we saw in the Suuntola's and Sipilä's presentation that in the standard model, star systems do not expand. Whereas in DU, all gravitationally bounded systems expand equally. And this can be illustrated by this picture, very simply that many billion years ago in the standard model, and both in the standard model and DU, the sun was fainter, because this is what everybody agrees. So it radiated less. But in the standard model, the distance was the same then as it is now. And in DU, the distance was shorter then than it is now. These are not the real distances, just to make the point. So the problem became that now based on the empirical data, there should have been water on the Earth at this time. But it was so cold here that it contradicts the findings. So they had to invent a special atmosphere for Earth at that time. And exactly the same thing with Mars. There should have been a sea at this time, somewhere around, but now it's frozen. It's deep frozen. And if it's frozen now, it should have been even more frozen back then, but it isn't. So the solution was to invent an atmosphere. So the point here is standard model contradicts the empirical data. That's why it needs to be complemented by parameters, and whoops, it matches the data again. Also in the previous presentation, we saw that based on Laplace calculations, the solar system is unstable with the velocity of light gravitation, whereas in DU, gravitation is instantaneous. So these were not, of course, not all parameters of the models, but there were some of the central postulates counted, and now we evaluate these. So we apply Kaila's relative simplicity. That's basically empirical propositions divided by metaphysical postulates. But we also take in account the virtue, so that if we have a contradiction in the model, or it fails to explain something, so it must count somehow. So we take one explanation away from every contradiction. Now, this is very scarce, this evaluation, but it gives some kind of a picture. So E is for an explanation and P is for postulate. So here we have a cosmic time and relativistic time. So that's two times. Two different times. That's one explanation of time and the atomic clocks, but two postulates. But then we have a contradiction between cosmic time and relativistic time. That's one minus. And here we have a cosmic time, plus we also have the changing velocity of light. So that's two postulates and one explanation of the atomic clocks. So I take that both have two explanations and two postulates, but here is no contradiction, and here is contradiction. So contradictions, can't go unnoticed, so we take one minus. Okay, here is eternalism with or without branching space-time, but this eternalism where the past and future exist equally. So I take that's two postulates, whereas here is presentism is sufficient, where only the present exists. So here are three different three-dimensional geometries, and here is one four-dimensional geometry. So I just thought, okay, maybe these count as equally complex. So one explanation, one postulate for both models. What is the geometry of space? Then we come to the expansion hypothesis. So in standard model we have the density parameter and dark energy plus inflation plus acceleration. So I take it to count at least two postulates, only one explanation. And here, no density parameters, no other parameters, but there's a conservation law of energy. So I take it that one explanation, one postulate. And here's the solar system, explanation, stability of the solar system. So when the solar system is unstable, you can't consider it as a good explanation. That's why it's one minus. And here are instantaneous influences. That's one postulate. But it also explains the stability of the solar system. And then finally, we need the special atmospheric conditions on Earth and Mars. So that's two postulates, one explanation, and here no special atmospheres. One explanation, one postulate. So you can put this in many ways, and whether you take one explanation away or whether you add more postulates, but anyway, you get the general picture that you have here. You have less or worse explanations with more postulates. And here you have at least as many explanations with less postulates. So we can get some kind of a numeric value like this. But we shouldn't look at the numbers, we should look at the total picture more. And we count in like all the good virtues and explanations and predictions and accuracies. We count them all together, and then we count all the vices together so we can evaluate that which model is better. And here I put this higher on the scale because it weights less but explains more. So based on this evaluation, dynamic universe is a better model than a standard model of cosmology. So you might think that it's just my opinion, but I want to insist that we have an objective evaluation criterion. So you can suppose any other criterion if you want. So what is the alternative? What is it? I don't know. It can't be the accuracy of predictions only, because then all the parameters get just swept under the rug. So we need to evaluate the metaphysical complexity. And so it is evaluated here. And that's the only way I can see this case, but I might be wrong. But if I'm wrong, then there should be some reason why I'm wrong. So you should give some reason. So please show me I'm wrong and why am I wrong? So, and if you can't, then you should understand, yeah, we have here a new model. So what will you do about it? It's of course entirely depends on you and us, what we do, if we like the progress of science. So I want to give the responsibility, progress of science for you. Thank you.
Thank you, Avril. That was very interesting and exciting talk. Is there anybody who wants to prove Avril wrong? If not, then questions, please.
Mr. Styrman, I come today with a sore throat. Not that I'm apologizing for it, but only to get exactly the kind of reaction that I was expecting, and you have given it. I shall try to raise my voice, and you shall help me do it by improving your hearing. Now, I don't believe that if you doubt that you could be wrong with your theory, that I need to prove you wrong. I do believe and remain convinced that if you doubt that you could be wrong, then you go ahead and prove it to yourself. So, let us be economical about what I have just said. Because I have presented to you also a kind of theory The theory has some very, very implicit assumptions in it. But I'm going to present to you another theory for which I am thankful to you, because during your talk, I came upon it. It is a perfect theory, as perfect as something beautiful itself, not as beautiful as something perfect, but as perfect as something beautiful. And I'm going to read this theory out, and then I shall give you a question which relates directly to the topic of your lecture today. The theory goes as follows. I'm reading it out from this handout which was given to us. Page 2. If you look at the time point 1515. So, the ultimate purpose of a model is to replicate its correlate. Nevertheless, models do not fit into naturally perceived realities, where time and distance have equivocal interpretations. Should we abandon a perceived reality or rethink the theory? In a holistic approach to space as a zero-thought system, I identify relativity as a direct consequence of the finiteness of the absolute in space. Instead of describing relativistic effects in terms of distorted absolute time and distance, the effects can be described by me in terms of locally perceived, thus saving the universality of the coordinate quantities absolute time and absolute distance, which in any case are not essential for human comprehension. The zero-thought approach can be built on direct empirical evidence. It shows unification via unified expressions of thought and absence of thought conversions, rather than unifying the same. The zero-thought approach leads to precise, simple predictions of all observables without additional parameters like myself, and cures the impossible gap between macroscopic and the quantum. So you have heard my theory now. My question to you, Mr. Stuurman, is it economical by the standards that you have been so kind to show us? Thank you.
You mean, is the DU economical? Yes. It's if you compare to the, if you take all scales, take a scale of quantum mechanics or atomic and subatomic phenomena, then the celestial mechanics, and then scale of cosmology. Then you have all three scales. Okay? Then you count the postulates of DU that it needs in explaining the scales. Okay? Then you get some kind of an approximation. Then you take current, some other cosmological theory, and the sum of all other theories that you get to explain all the same phenomena. And then you calculate their postulates. So there you get an answer. I didn't take any account to the postulates of this quantum mechanics scale. It would take too much time, and it's kind of difficult, out of my area anyway. But
Can you compactify your question?
is it okay?
Mr. Stuurman, you are a good man. you promised to send me a link, and you did. But unfortunately, you understood my question in a way which I can't even begin to describe because I don't know what to say. I simply wanted to know whether the theory that I read out was economical by the standards that you described. My theory, not DU. Thank you.
But didn't you read the DU introduction? Well, then you have to list all postulates that are in your theory. Then we can measure it. But that's the only way we can measure these theories. To openly take postulates, list of postulates that your theory has, and then put it below the line and put above the line all the explanations your theory gives. And that's how you get the relative simplicity. So that's the only way you can evaluate theories. Is that a good answer? Because you didn't exactly give the postulates. So it's hard to say.
Yes, thank you for your talk. I have a question about the unification ideal, let me call it this way, and its relationship to the economy principle. So before my question is, I would say that between the theory of unification in science and this unification, as you called it, there are many things in between. And I would like to ask you, why not rather think in terms of plurality? So I think your argument makes sense if you only compare these two theories. But what we have seen, or what I have seen and also discussed a little bit with Professor Suntola these days, is that in the context of cosmology, there is a plurality. So I would say it would be very difficult, if not impossible, to think of a unified theory. And also in the end, maybe it's not what we want. So two questions. Would you have a place here for plurality, and why unification and the economy principle are inseparable, as you argue?
Okay, I'll first answer why unification and economy are inseparable. Let's look at here. So I tried to explain here why they are inseparable, because here you have a disunified theory, and here you have a unified theory, and here you have three disunified postulate bases. And if you count them like 0.5 plus 0.5 plus 0.5, that's 1.5. But when you put them together in one, then you get a simpler theory that explains the same thing. So there's a difference between the weight of 1.5 here against the weight of 1. So, and you have this simplicity and unification this way fused together. So that's how simplicity and unification are fused together. And economy, because economy is only the explanation of perception and metaphysical simplicity. So that's why they're intimately interrelated. But the plurality question, that's a difficult one, because in the context of philosophy, it's kind of a pluralistic world. So I get people who say, oh, your projects of unification can never work because everybody's pluralist these days. And you can see it, of course, if you read the articles, because there's everything between heaven and the earth. But then we must ask it, okay, how do these things apply to something? Okay, we have the sphere of philosophical articles or academic philosophy. Then we have the sphere of what people can apply. If you have some article that works in the philosophical sphere, but it does not apply, then we must ask, okay, what is the use of it? Where do we use it? So what I'm trying to say that, okay, if you can say that you can use it, it has some use for somebody. Somebody gets something from it. Okay, that's completely fine. Pluralism is fine in that way. But then again, if everything goes, then is it really progressive? Is it, in the end, is it really progressive that we have like, we have, for instance, theories of time. We look, for instance, we have different theories of time. One is presentism, one is eternalism. Then we have growing block theory. That's basically only the past and the present. Then we have what is searching spotlight theory. Sorry, that's eternalism with the moving present in any way. So we have all combinations of these theories of temporal existence. So we can think of the academic metaphysics currently as a project of explicating all metaphysical possibilities, like everything you can think of. For instance, is matter infinitely divisible? Is space infinite? So all possibilities you can think of. So imagine you have all the possibilities that a priori metaphysics can come up with in the list. So what do you do with that list? So that's the question. So is it like, it's one thing that we have this discussion on these possibilities, but when you have all the metaphysical possibilities on the list, then what do you do with them? How do you apply them? So what I'm trying to search is, okay, you must search for some combination of physics and philosophy. And the only way I could find something was that, okay, if I want to specify some ontology or some unified theory, then only way I can do it is to search for a minimal combination. Because unless you don't have some criterion, you just end up with a list of combinations. So, and then if you have 100 little combinations, 100 different combinations, then your problem becomes how to solve further problems. For instance, notion of truth, possibility, and that kinds of things. So we need some kind of a worldview so that we can use it in resolving other things. And that's why you must have something. So, and then it becomes a problem of different people have different worldviews. So how do you evaluate them? So if everything goes, then it's just like the current stage, that everything goes. So that's the problem of the pluralism. So if you have just, if everything goes, then everything goes, but who does it help then? So. Okay, but do we still have a little time? So, well, thank you for the question. That's a difficult one because it's difficult to try to suggest economy in the world of pluralism. So.
Broadly, I'm all in favor of trying to simplify. I mean, the simpler theory is better. I'd like to make one point which I think could be made. You said that the Ptolemaic system and the Copernican system were equally good as regards the observations, explaining the observations. But there is actually a very interesting point. When Ptolemy died, he was able to predict pretty accurately what the sky would look like from Alexandria in the first place, or basically from the world, several hundred years ahead of his time. That was the strength of his astronomy. But he had no idea what the sky would look like from Mars. When Copernicus died, he had a very good idea what the sky looked like from Mars, and in fact his prediction, it took over 400 years before spacecraft actually went to Mars and confirmed him. So there is something very much, that was a very dramatic thing, which is largely not appreciated when people say that Ptolemaic astronomy gives the same as a Copernican astronomy. I don't know if you'd like to comment on that.
Could you repeat in short, specifically what you want me to answer?
The one assumption that Copernicus made was that the sun is not moving, but the earth is moving on a circle which has the sun near its center, not necessarily exactly at its center, but near its center. That one assumption immediately enabled him to say where all the planets are relative to the sun, and their speeds, the speeds at which they're going, and the size of their orbits. And from that he could immediately deduce what the sky looks like from Mars. Because Ptolemy described each planetary motion separately, there was no unifying thing that put them together. There's a very famous account by Copernicus. He says the Ptolemaic astronomy is like an artist who had drawn limbs of animals belonging to different animals, each limb from a different animal, but when you put them together, a horrendous monster arises. But his system was actually one beautiful, harmonious one, where it corresponded to just one animal. So there was a huge advance in, it took a long time before that happened, but it did happen then.
Well, what you said that I would perfectly side with Copernicus and agree that, okay, that's beautiful, as you described. So there's beauty and simplicity, and these are like these theoretical virtues. What I was trying to say that this ideally unified theory has all the virtues. So
I was just questioning the claim that they were observationally equivalent. In my opinion, they're not observational.
oh, yes, they're not. They're not because, but you could, in principle, you could develop the Ptolemaic system if you wanted. You could develop it so that it would be equally accurate. Of course, it was dropped, I think, its development after the transition to the sun-centered model. But the point is that even if it would give as accurate predictions, it would still be more complex. So, okay, thank you.
Another point about Einstein and his theory, there is nothing inconsistent between Einstein's theory and the fact that a cosmologist can use a cosmic time. Einstein's theory does not predict what solution it will have. It will just say any solution will satisfy certain properties. Now, the universe we observe around us is perfectly consistent with Einstein's equations, just because they seem to distinguish a special convenient time is not in any way inconsistent with the underlying principles of Einstein's theory.
So, what do you, if you have relativity principle, isn't it the postulate of...
The relativity principle is about local observations. It's purely a matter of, say, what you do. I mean, it started with the ones that the plot of the how the mass changes with the things like that. These are purely local observations. It doesn't say anything about what the universe in its totality would look like and whether it might be such that there would be, that the disposition of the matter in the whole universe would single out a particular way to look at things as more convenient.
Well, if the relativity principle doesn't imply a contradiction with absolute simultaneity, if it's so, then we can just drop it as a fundamental postulate. But if you have two conceptions of time, cosmic time and absolute simultaneity, and relativity principle, then they contradict one another. You can't have them simultaneously hold.
In cosmology, it's not perfect absolute simultaneity. It's a good approximation for describing what the universe looks like. That's totally different from utterly precise statements that have been verified umpteen times about local experiments made here on the Earth. Those are two very different things.
Okay. Well, if you have the concept of the form, geometrical form of the universe, so if you have like a spherical form of the universe, you say that the universe has the form of a sphere at this time. So what do you mean by talking about the universe at one time? Do you mean all its parts at one time, or do you mean its parts different times?
Well, the cosmology as it exists at the moment is, although there's a lot of things have to be put into it by hand, it is still an amazingly successful theory which has passed every test that general relativity has been asked to pass. And in fact, as Martin Rees, the British astronomer royal that I mentioned, said, the cosmological model at the moment just needs 6 parameters which you have to put in, taking it from observation. That's not a bad success story. Everything else fits with incredible accuracy.
Well, of course, it's better than nothing. I'm not saying that, but if we have 2 models, we have to evaluate the models somehow, don't we? So if you, what kind of a criterion would you suggest then?
Well, you have to make, I haven't seen the details of how the alternative model, the DU model, actually makes any calculations. I mean, it's one thing to talk about a de Broglie wavelength. It's quite another thing to have the complete theory of quantum electrodynamics, which predicts things to, it's based on relatively simple principles, but the calculations are very complicated, and they lead to very, very precise predictions. It's like hitting a hare by shooting from New York to California, the accuracy of quantum electrodynamics. It's not clear to me that that comes out of the DU model. Until it does, I wait to be persuaded, I have to say.
Yes, okay, that's a very good attitude, because you must contest it. You know, you must argue that it doesn't give correct predictions, and Suuntala can try to show you that it does. But that's like, I take it, it's not my responsibility, because I'm only evaluating, you know, what I've read from the books. So you must, you know, show that it's not correct. So if you show it, then I believe you.
Well, I think the results that match the present ones have to be derived from the first principles by calculations. Yes. That's what I wonder whether that's been done.
Yeah, that's a you know, I could not have put out a better point, because like the point in DU is that you have zero energy principle and this changing velocity of light and the basic structure. So the point is that you derive everything from that basic structure. So that's the point. That's a basic starting point, that you have the basic postulates that are 4-dimensional geometry of space, conservation of law of energy, you know, the velocity of light changes as the radius changes. And then you just derive everything more specific by the basic structure, because that's the point in DU, as far as I understand it. So it should answer your critic. That's the goal, at least. Well, what's the difference between aspiration and achievement?
Mr. Sturman, I think you have been terrorized quite a lot, and I think that the panel should now get its own fair share. So I should like to begin by giving my question to the panel, which will replace you shortly. And I would like to present a description of a very bad habit that I have. I still have it, and it's called jumping to conclusions. Now, I indulge in it simply because of the fact that it helps me get out of confusion. So you see, it has been a habit which has also been developed. I am confused by the idea of making predictions. I'm even more confused by the idea of testing theories to confirm predictions, because there's something you pointed out very correctly. Are we talking about predictions that we are making now, which can only be tested by observation, let us say 1,000 years from now? Are we talking about predictions which we are making about something which might have been 1 million years in the past, which are also not observable? What are we exactly talking about when we talk about predictions? What are we exactly talking about when we are talking about testing those predictions? And what exactly do we mean by making observations and not creating observations by the power of observation that we use to observe? So, this is the question that I am giving to the panel, which I hope will replace you shortly. Thank you.
So was it to me or the panel? Well, you were asking very basic questions, so I think one here could answer them. So we make observations with bare eyes or with a telescope. So that's there's no ambiguities in that. We make observations with telescopes. But when you make observations in CERN, then it's not clear, are they just observations or are they interpretations with the results of those observations? It's unclear, very unclear. But when we measure the brightnesses of some supernova explosions, so there's not very much ambiguity in that. So what I have presented here, those tests of DU, well, there's especially no ambiguities in those observations. So did that answer your question about the observations?
I have given my question to the panel, which is going to replace you shortly.
Okay, thank you.
Thank you. So there was a question to the speakers of today. Would you like to comment on the question? It seems that there will be no comments on the question, but now we don't collect the speakers in front of this room, but you are free to ask any speaker or comment on any speaker? Please. Joo. Haluatko kysyä? Mitä? Ei me keritä enää.
As Ari stated, so that we are now open for questions concerning any of the talks today, so that you can answer or comment any of today's speeches. So we don't need to ask the speakers to come up here, but they are ready to answer whatever you are asking. Or if everything is absolutely clear, then we can, of course, be prepared to orient to the reception, which starts in 40 minutes from now, so that we have 40 minutes time to move to the university. It will be opened by our host at 6:30, so it would be nice that we are already gathered there at 6:30. Thank you for your attention, and thank you for using your time here, for even it's so nice day outside. Thank you.
Professor Laurikainen, the founder of the Finnish Society for Natural Philosophy, held popular seminars in the cellar auditorium of the Department of High Energy Physics on Thursdays in the end of the 70s. The main topic was quantum mechanics and its implications concerning observations versus reality. This is a long story, but I just state that the inspiration for searching a simple structure-creating natural process came from these seminars, not from blue sky or thin air. Chaos was an active field of research then and still is, and it offered an interesting possibility for a simple natural process. Mitchell Feigenbaum showed that period doubling is a universal property of nonlinear dynamical systems. The word universal is important because nothing in nature is truly linear. And so we should be able to discover the period doubling phenomenon at least in the nonlinear gravitational and Coulombic 1/r potential systems. The aim of this presentation is to illustrate the fundamental role of the period doubling mechanism behind natural processes in creating the structures of the elementary particles, planetary and galactic systems, and others. What is period doubling or frequency halving? Suppose we have an oscillating nonlinear system, for instance, a string of a violin. We analyze the spectrum and we find that there is not only the fundamental frequency, but there are other frequencies which are so-called harmonic frequencies, and they are simply n times the fundamental frequency, where n is 2, 3, 4, 5, etc. These harmonic frequencies are generated instantaneously. Applications can be found, for instance, in radio and laser technologies. In a linear system, there are no harmonic frequencies. It is less widely known that subharmonics may be generated too. The process is called period doubling or frequency halving. Generation of subharmonics is not instantaneous because a long period cannot be generated within a short period. The subharmonics stabilize or become chaotic in the course of time. We shall use the period doubling phenomenon as a tool in analyzing experimental and observational data. So if our fundamental frequency is 1 kilohertz, then the period is 1 millisecond. And what period doubling does is that as time goes on, 2 millisecond periods appear in the system if we analyze the spectrum. And then 4 millisecond, 8 millisecond, and so on, subharmonics. This is called the period doubling phenomenon or frequency halving phenomenon. And the period is simply inversely proportional to frequency. Now in the chaos theory, an attractor is a set of numerical values toward which a system tends to evolve given enough time for a variety of starting conditions of the system. System values, for instance period or energy, that get close enough to the attractor values remain close even if slightly disturbed. This means stability. Is there enough time for the attractors to develop? The vast majority of the elementary particles have lifetimes on the order of 10 to minus 20 seconds or less, whereas the planetary systems have evolved for billions of years. The electrons and protons have existed for billions of years too, and they have well-defined intrinsic physical properties. Well-defined means that there is a very small uncertainty in the physical properties. Our solar system is likewise very old. Now, is 10 to minus 20 seconds long enough for the attractors of the artificial elementary particles to fully develop? An answer will be given later in this presentation. Now some mathematics and equations, sorry for that, but it's necessary in this presentation. If the shortest or the fundamental period of the system is tau naught, then the nth period is simply 2 to the nth times the fundamental. So the subharmonic periods are 2 times the fundamental, 4 times 8 times 16, 32, 64, and so on. So the number of doublings is 1, 2, 3, 4, 5, 6, 7, and so on. But there is an interesting subset of periods. We find that some of these numbers are integer powers of 2 themselves. And this is a very important subset. Namely, if the number of doublings is one of these numbers which are integer powers of 2 themselves, that is n, the number of doublings, is an integer power of 2 itself, then we have what is called superstability. And this is what we will later find out. Period doubling is not a mathematical curiosity, but a real physical phenomenon which has been observed, for instance, in pulsating stars, in our sun, and demonstrated in many experiments. Now the important thing is that period doubling has a direct connection to physics. For instance, energy, it's inversely proportional to period. Wavelength or distance is directly proportional, temperature inversely proportional, magnetic moment directly proportional. So these relations indicate that period doubling will manifest itself as a halving or doubling behavior in these quantities too. For the fundamental period, we choose the Planck time, tau naught, defined by natural constants h, c, and g, because this gives Planck energy and others which are process independent. These values are simply determined by these natural constants. As you can see, some of these values are out of this world. For instance, a Planck period is 10 to minus 43 seconds. Nothing in real life is this short. Planck length is 10 to minus 35 meters. For comparison, the diameter of a proton is 10 to minus 15. Planck temperature is 10 to 32 Kelvin. For comparison, the estimated temperature of the sun's core is 10 to the 6th or 10 to the 7th kelvins. It is now possible to compare the measured values of different quantities, for instance energies, to the corresponding Planck reference using equation 4. Just calculate the ratio. If the number of period doublings is an integer, then period doubling may be taking place. So put, for instance, Q equal to 1 MeV, which is the rest energy of electron-positron pair, and Planck energy here, and see what is the value of N, whether there is period doubling or not. Figure 1 shows ratios of 49 commensurate quantities, including rest energies of the elementary particles, semi-major axis of the orbits of the planets, etc. This was made in the 80s and published in 1990. Of course, the magnitude of the ratio depends on what is compared. It turned out that the majority of the ratios were something else than integer powers of 2. However, the decimal part of n, the number of period doublings, tells how close the exponent is to an integer value. For instance, 63.98 and 64.01 are close to 64. The decimal parts seem to form 3 groups. So out of these 49 ratios, about 1/3 was such a form that the ratio was 2 to an integer 0.00. 1/3 of the form 2 to integer 0.33. And the third column here is ratios of 2 to an integer 0.66. So the ratios were of the form 2 raised to integer over 3, which means that the 49 calculated ratios are cube roots of an integer power of 2. Now, what does this mean? The corresponding periods for our finding means that the nth period is simply 2 to the n over 3 times the fundamental period. Now, cubing both sides, we find that the nth cube is 2 to the nth times the fundamental cube. So, it is the volume that doubles in the period space. Volume means that the 49 systems we analyzed have 3 internal periods or degrees of freedom, or dimension of the period space, if you like. So we have the fundamental cube, the Planck cube here. As time goes on, the volume doubles, and finally we have the nth cube, which is 2 to the nth times the fundamental cube. This is the symmetric doubling case. Degree of freedom means that the 3 periods are independent and that the number of doublings can be different for each period. So the total number of period doublings is I plus j plus k, where these numbers are integers too. So now what we have is a straight parallelepiped. In the general case, there is different number of doublings for each period. The perceived period is then given by the cube root of 7. It's this equation 8. We simply take the cube root as before. Now the number of doublings is a sum of 3 numbers of doubling. And this equation 8 can be converted into other quantities, for instance, energy, as mentioned before. In terms of energy, equation 8 becomes equation 9, or what we perceive is 2 to minus I plus j plus k over 3 times the Planck energy. Integers I, j, and k represent the number of energy halvings from the Planck energy in the 3 degrees of freedom. Rotation and vibration are well-established phenomena in nuclear, atomic, and molecular physics. Even the Earth vibrates in addition to rotation after an earthquake. We assume that rotation and vibration are ubiquitous phenomena and that rotation and vibration can be taken as internal degrees of freedom of the system, for instance, like in molecules. It was Niels Bohr's idea that a wave can close or localize itself into a circle such that the circumference of the circle is in an integer multiple of half a wavelength. The structure is called a ring resonator, and the energy levels of a hydrogen atom were explained for the first time. A ring resonator describes energy in rotational motion. The Fabry-Perot interferometer is a linear resonator where an integer number of half waves are trapped between two parallel mirrors. This type of an interferometer describes energy in linear or vibrational motion. It is plausible to assume that the elementary particles have rotational and vibrational energy levels too. To find out whether this is so, we include a factor of pi in our energy equation for particle rest energy analysis because the ratio of the circumference of a circle to the diameter is pi. So for 1 degree of freedom we have this normal energy path, and then there is the Rotwib indicator, which is either 0 or pi or 1 over pi. Now the 3D form of energy is simply a product of 3 of these individual energies. And finally we get equation 12, what represents the perceived energy. It is pi to the a over 3 times 2 to the minus n over 3 times the Planck energy. And this is the cube root that we need for returning the volume into a scalar value. A system with 4 degrees of freedom can be described using the same formalism. Why 4 degrees of freedom isn't free enough? Our world is 3-dimensional. Now the natural reference for the elementary charge is the Planck charge Q0, which is defined as a square root of 4 pi epsilon naught hc, where epsilon naught is not the gravitational constant, but the permittivity of vacuum. So now we have a different set of natural constants here. And because we are interested in ratios, let's calculate the ratio of E squared to Q0 squared. Squared, therefore, at Coulomb energy is proportional to charge squared. And what we get is the ratio is 2 to minus 9.7499, which is 2 to 9 3/4. Now the number 4 here tells that we have a 4th root, that there is 4 degrees of freedom. So the intrinsic Coulomb energy system of the elementary charge has 4 degrees of freedom. The 4th root also brings about the plus-minus polarity for electricity. The cube root means monopole for mass. The system is super stable because m equal to 39 is sum of integer powers of 2 according to the stability rule down here. We remember the exponent is a power of 2 itself, and we find that the ratio is 2 to the 0th, 2 to the 1st, 2 to the 2nd, and 2 to the 5th. Later we find that this is connected to the rest energy of the electron-positron pair. But anyway, the elementary charge is stable. Enough time for the attractors to develop. Suppose an initially 3D plus 4D or 7D system that is mass with electric charge has enough time to evolve. The corresponding mass part and the electromagnetic part become fully developed independently, and the system becomes a combination of the 3D and 4D parts. So what we perceive is possibly some rotation and vibration. Then there is the 3D mass part, the cube root. Then some rotation and vibration in the EM part and the energy part, the period doubling part. Now you find that we have here E sub double naught. What is that? Now E sub double naught is what I call now is the generalized Planck energy, which takes into account the Planckian Coulomb energy and not only the conventional Planck mass energy. Therefore, the generalized Planck energy is larger than the Planck energy by the ratio of the Planck charge to the elementary charge squared. But this later we'll see that this allows us to analyze particles, divide the mass part and electromagnetic part and see what their structure is. Not enough time for the attractors or the long periods, the subharmonics, to develop. For the short-lived elementary particles, there may not be enough time for the attractors of the 3D and 4D parts of the particle structure to fully develop. The period space volume of the structure can be now described by a nonlinear system with 7 degrees of freedom because they have not separated yet. Then the energy levels are simply, the energy part is 2 to the minus n over 7. This is the 7th root times the generalized Planck energy. And here we have the Rotwip indicators for the mass part and the EM part, if there is rotation and vibration. Now equation 17, this here, describes a system with 3 independent phase spaces, namely the period space, the Rotwip space for the mass system, and the 4D Rotwip space for the electromagnetic system. Let's analyze the short-lived particles where there is not enough time for the attractors to develop. The Large Hadron Collider in CERN is one of the biggest, and I forgot to write down that it's also the most expensive and complicated device ever built by man. Protons travel there in opposite directions at nearly the speed of light, and their collisional energy is 14 tera electron volts. Electron volts is an unit of energy used by physicists. But for comparison, the proton rest energy is 1,000th of the collisional energy of the protons. The device itself is a vacuum tube. Its circumference is 27 kilometers, so it is a huge thing. And you can hardly see here, here is one of the researchers. So, most artificially created elementary particles are extremely short-lived. Their lifetime is on the order of 10 to minus 23 to 10 to minus 19 seconds. This may be too short a time for the particles to obtain stable 3D and 4D parts, which is manifested by the wide Bright-Wigner distributions. Bright-Wigner width means essentially the width of a resonance curve. Therefore, we consider these particles as 3D plus 4D, that is 70 degree of freedom, flashes, rapid flashes of energy, and apply our equation 17, which is here written as equation 18. And what do we get? The total number n of period doublings can be solved for from our energy equation if the particle rest energy is known. The number of doublings is simply this ratio of the logarithms. Now I have combined the Rotwib indicators to one number, it's the lowercase n here, power of pi. Because the Rotwib mode, or the A and B, is not known a priori, we calculate the n values for all different possible modes from n equal to minus 2 to n equal to plus 2 for each particle. Integer n's are colored and written in a column in downwards growing order. So what we do is we write the rest energies of particles here. This is the epsilon particle. Then we calculate the number of doublings for all possible Rotwib states, which we don't know beforehand. So this row here is quite long, and in every cell there is the corresponding number of doublings. Then we find out that one of those numbers is an integer. We color that and calculate all the rest of the numbers and do the same. Pick up the integer numbers and color it. So this is a huge table. There are more than 8,000 cells in this table. Then we order the total number of doublings in downwards ascending order. And what follows from this? I calculated the integer number of period doublings for the baryons. They are shown here in ascending order from equation 19, which is our energy equation. The baryons are, loosely speaking, heavy protons and neutrons. So they belong to the proton-neutron family. And what happens here that the particles seem to form three groups. Because in this period doubling scenario we don't have any names for these groups, I have used the names used by people who have the standard model of the elementary particles. But otherwise, the concepts used in this analysis have nothing to do with the concepts of the standard model. But I call these, according to standard models, these particles are the bottom particles, these are the so-called charmed particles, and these are the strange and non-flavored particles. But particles clearly split into three groups according to this period doubling analysis. And each particle has its characteristic number of period doublings and Rotwib state. The nucleons are kind of a ground state particles because A and B are both 0. But this is an interesting picture because we have no theory here. This table includes the rest energies of the baryons. Here are the omega particles, xi, sigma, delta, lambda, and the nucleons. And I have simply made a scatter plot of these energies. And we can see that part of the particles have rest energies little less than 6,000. Then there is another group little less than 3,000, and another group around 1,500 MeV. So this clearly indicates that there is a doubling or halving process going on. And this is just a plot, no theory here. What is jiggling or ripples here are, they are due to the Rotweb states of the particles. Now the same calculation for the mesons. The blue shades here are so-called double bottom mesons. Then there are the bottom mesons, charmed mesons, charmed strange and light unflavored. But we can see that the mesons have exactly the similar behavior as what we already had for the baryons. There are two interesting particles. They are called gauge bosons in the Standard Model, mediating the weak force. They are very heavy. Their rest mass is about 90 times that of the proton. They seem to form a group here of their own. Now you may ask, where is the Higgs particle, the God particle? Well, it's here. It seems to form a group of its own. And now there are indications that even heavier particles exist. And I would like to forecast that they go somewhere here and form a group of their own. There are some outliers here, as you can see. They have special names in the Standard Models. They are pseudoscalar and so-called vector mesons. So, period doubling seems to organize the artificial elementary particles. How about the electron-positron pair? There is enough time for the attractors to develop. Why I go to this, the reason is that the rest energy, electric charge and magnetic moment of the electron and positron are normally taken as natural constants. They are not normally explained in any way. Electron-positron pair creation is the fundamental process for converting energy into matter. According to the present understanding, these particles are stable over billions of years, which suggests superstability according to the theory of nonlinear dynamical systems. So what we do is, again, take the ratio. This 1 MeV is the rest energy of the pair, and this is the Planck mass energy. And the ratio seems to be 2 to minus 74.667. And this 2/3 clearly belongs to the first group of the systems. The total number of period doublings is very close to 2 to 4 divided by 3. Now, the total number of period doublings is the sum of I, j, and k, which are integers. So we should be able to split 2 to 4 into the sum of 4 numbers which are powers of 2 themselves, and we find that 2 to 4 is 32 plus 64 plus 128, which is 2 to the 5th, 6th, and 7th, which means that the structure of the electron-positron pair is superstable. Otherwise, we would not exist as we are. The superstability of the pair means that electrons and positrons always coexist. If so, where are the positrons? Or the positive elementary charge? This is an interesting question. Where are the positrons hiding? Now with exactly 224 period doublings, we can calculate the rest energy of the EP pair, and this is what we get, 1.021, which represents an inaccuracy of 1 kilo electron volt. We can now write down the combined superstable structure of the electron-positron pair. This is the mass part, 2 to the 5th, 6th, and 7th, it's superstable. And we find that the 4D part represents the Coulomb energy of the elementary charge. The electron has a very large magnetic moment, actually 658 times that of the proton. And let's take a look at that too. Magnetic moment mu is defined as a current loop, where the magnetic moment is current times the area of the loop. Take copper wire, make a loop, connect it to a battery, current starts flowing. The magnetic moment of the loop is current times the area of the loop. Moment means that it tends to turn in a magnetic field. The Planck loop serves as a natural reference where the loop circumference is the Planck length and the current the elementary charge divided by the Planck period. And equation 22 is what we get for the Planck scale reference magnetic moment. Now take the ratio again. The EP pair magnetic moment is 4.6 times 10 to minus 24 ampere meter squared. That's half of the electrons because the pair energy is twice. And the magnetic moment becomes EP magnetic moment is 2 to plus 2 to the 5th, 6th, and 7th times our reference. So the number of period doublings in the EP pair rest energy is the same as the number of period doublings with the magnetic moment. Now we can calculate the magnetic moment and we find that the difference is 0.061 as compared to the NIST value. So for every electron-positron pair, every process step halves the energy and doubles the magnetic moment because of the number of doubling is the same. How about the proton? Let's use again our energy equation 17, put in numbers. This number here is the proton rest energy. This is the generalized Planck energy, which includes the Coulomb part. What we find is that this is pi to the 0th times 2 to minus 192 over 3. Now here we have pi to minus 2 over 4 times 2 to minus 39 over 4, which can be written in a more illustrative form, which is here. We see that the mass part or the 3D part is superstable 2 to the 6th, 6th, and 6th, which means that it is symmetric. Proton is a cube or a sphere, if you like. And the 4D part seems to be Coulomb energy. But now, out of the 4 degrees of freedom, 2 are vibrational. The proton has magnetic moment 2, and because of the 2 vibrational or linear modes in the 4D EM part, we define the reference loop such that the loop diameter is half of the Planck length corresponding to the ground state of a particle in a box in quantum mechanics. And what we get is this equation 27. This is a slightly different reference than what we were using with the electron-positron pair. Anyway, the ratio becomes 2 to plus 64 or 2 to the 2 to the 6th, which tells us that this is a superstable structure. We can calculate also the theoretical value for the proton magnetic moment, and it differs from the NIST value by 0.07. So NIST is the National Institute for Science and Technology, and these are so-called official values that they publish. How about the neutron? It's kind of a funny particle. It is electrically neutral, but it has a rather large magnetic moment. Now the scattering experiments have shown that the neutron has a negative surface and it is positive inside. So we can model neutron's magnetic moment using two loops, one negative and one positive. Because the proton and neutron sizes are essentially equal, and we simply assume that the magnitude of the magnetic moment caused by the negative surface is the same as the proton's magnetic moment, but of opposite sign. The magnetic moment mu I of the inner loop is obviously smaller and positive. With these assumptions, we can write that the neutron magnetic moment is minus proton magnetic moment plus the magnetic moment of the inner, so far unknown loop. But we can solve for the magnetic moment of the inner loop, and it becomes 4.4 times 10 to the minus 27th ampere meter squared, and it belongs to the period doubling system because the ratio, this is now our Planck scale reference, is 2 to plus 63 plus 3, 3, 3. So this belongs to the first family in our distribution that we showed in the beginning of my talk. So neutron is also a period doubling system, both energy and magnetic moment. Now if we insert the calculated magnetic moment into our previous equation, we get the theoretical value for the neutron magnetic moment, which is practically the same as the measured value. Antiprotons can be artificially manufactured, but they are not found in nature. Therefore, some property of the neutron must possess the nucleon anti-property. This analysis suggests that the negative surface magnetic moment of the neutron is the required anti-property, fully cancelling the proton magnetic moment. And magnetic binding between these particles follows too. Yeah, this is the deuteron, but let's skip it. Now, this presentation may have been rather boring up to now. Plenty of elementary particles, plenty of equations and explaining. Why this much about the method and the elementary particles? The reason is that to our knowledge, there is no other theoretical scenario enabling the calculation of the intrinsic properties of the elementary particles to great accuracy and simultaneously explaining the stability of the basic particles. This refers to the chaos theory. We hope that the following will be more interesting because it may explain the unexplained too. The cosmic microwave background radiation. As we heard yesterday, Professor Narlikar mentioned that even before Penzias and Wilson, this was predicted and discovered, but sorry, I forgot the name of the researcher. Anyway, officially, Penzias and Wilson discovered the background microwave radiation in 1964, and they were awarded Nobel Prize in 1978. This is electromagnetic radiation as if there were transmitters all over the space. And the power spectrum is exactly the same as that of a black body whose temperature is 2.73 kelvins. So it is now interesting to calculate a ratio again. Here is the Planck temperature, and this is the observed black body temperature. The ratio is 2 to minus 106.68. This is again 2/3, so this ratio belongs to the electron group. And we find that this is superstable, 2 to minus 2 to the 6th, 7th, and 7th. And this relates to the EP pair. The ratio is 2 to minus 2 to the 5th. How about the Big Bang then? If this radiation is related to the system of electrons and positrons, how can it have anything to do with the cooling universe? These are fixed ratios. Well, let's go to hydrogen. There is a hydrogen sky. The sky would look like this if we could see 21 centimeter wavelength light. This bright strip here is our Milky Way, and there are huge glowing filaments of hydrogen that transmit 21 centimeter wavelength. This is one example of the radio eye. This is the Effelsberg 100 meter radio telescope. Hydrogen atom is quite a marvelous thing. Its radius is 10 to the minus 11th meters, yet it can radiate 0.2 meters wavelength radiation. The atom is far too small to be able to radiate 21 centimeter wavelength. Classical or quantum physics cannot explain this. But I would like to say that Tuomo Suntola's dynamic universe has a very elegant and nice explanation for this radiation from this small atom. Now, again, the ratios are interesting. How does 21 centimeter relate to the Planck length? Now the ratio is 2 to 112. Now let's split it into the 3 parts, and we find that this is 2 to the 4th, 6th, and 8th. Again, a superstable structure related to the EP pair. Now the 21 centimeter corresponds to 5.9 microelectron volts, and the relation to the electron-positron pair is, again, ratio of energies. This is the radiation energy, this is the EP pair, and this is 2 to the minus 2 to the 4th, 5th, and 6th over 3, showing that the 21 centimeter radiation, or the structure of this energy system, is directly related to the electron-positron pair. What could possibly the sunspot cycle to do with period doubling and electrons and positrons? Well, everybody knows that there is a 11-year sunspot cycle. The sun is very quiet, then it becomes wild. Here it's wildest, and then it gradually calms down again, and the cycle is about 11 years. Now, the radio emission from the sun at a wavelength of 10.7 centimeters, often called the 10 centimeter flux, has been found to correlate well with the sunspot number. These crosses here are the actual sunspot numbers, and the solid line is the 10 centimeter flux. The radio flux at 10.7 centimeters can be measured relatively easily and quickly, and has replaced the sunspot number as an index of solar activity for many purposes. But what do we find? We note that 10.7 centimeters is half of the hydrogen's 21 centimeter wavelength, suggesting that the sunspot cycle, hydrogen and electron-positron pair are connected. Actually, if we think of it, this is not a surprise, because after all, the sun is hydrogen, and it shows all the properties of hydrogen. How about the solar system? Can we calculate the orbits and orbital velocities? Equations for the circumference of the orbit and orbital velocity are here. These have been published before. And you can see that these relations are universal. There is no reference to the sun. L naught is the Planck length. C is the speed of light. And these are the terms that double or half these quantities. Now, given enough time, the initial dust and gas around the protosun accumulate into orbits, which are attractors, determined by the period doubling process. Note that the orbital velocities of the planets are given by consequent integers here, 38, 39, and so on, up till 84. And this is a comparison of the observed orbits and those calculated from these two relations. Now here is one interesting thing. There is an empty allowed orbit, as if a planet were missing there. We can see that Jupiter has been pulled towards the empty orbit as if there had been a strong interaction sometime in the past, and as a consequence, planet 44 has been thrown out of the system. There is also a planet missing from the other side of the Jupiter. There is the asteroid belt. So if we do some guesswork, this means that Jupiter has been hustling around here. Well, there is a more detailed analysis published earlier. But as you see, the orbits are not formed by any random numbers, but consequent integers. Every orbit is filled, except orbit 44. Now we go to the galaxy redshifts and quantization. I added an extra slide here because Professor Barber yesterday asked about the quantization of the galaxy redshifts. So what Professor Tift did, he wanted to be an astronomer, and he started to measure the redshifts of galaxy pairs. Stars are often binaries, and there are hundreds of galaxy binaries. He measured the redshifts of the components of a binary, plotted them down, measured, plotted, measured, plotted the values, and he found out that the redshift clump around certain velocity values if redshift is interpreted as velocity. So the redshift difference of the pair seems to be quantized. This is the redshift quantization. And the redshifts or the velocities seem to group around 36 kilometers per second, 72, 144. And this was in the 70s. Now we know that there are many more redshifts that are belong in these groups. He then started to measure redshifts of single galaxies. And what we found is that those redshifts belonged to these groups too. But because he was a careful experimenter and observer, he returned to the redshifts he had measured earlier, 10 years, 20 years before. To his surprise, he found out that the redshift of some galaxies had changed within 10, 20 years. They had become redder by 1 redshift quantum. Now, if we think of the size of the galaxies, they are typically 100,000 light years. So no signal can traverse across the whole galaxy in 20 years. So something happens which deals with the whole galaxy simultaneously. And this is which calls for the fourth dimension and Tuomas Untola's theory. So let's see how period doubling is related here. These are again our ratios. We find that they are integer powers of 2, which tells us that this is a period doubling energy system in 3 internal degrees of freedom. Note that the velocity is obtained from the same equation which was used in the analysis of the solar system, pointing to a common universal mechanism. In Professor Tift's opinion, the quantized redshift does not mean quantized recessional velocity. This is an intrinsic property of the galaxies. Here is a couple of pictures of Professor Tift's publications. These curves are the observations. Here we have power. Power means the number of galaxies with redshift within a given interval. And the straight lines here are the theoretical values that come from these equations. As you can see, now P here means period, but it's the same as velocity. And this is what we originally had already with the solar system. But what Professor Tift found, that the total number of period doublings depends on the morphology of the galaxies. Therefore, he was able to split the total number of period doublings into families according to the morphology. What he found was that we need the 9th root to describe the intermediate redshifts when the galaxy is in changing its redshift. There seems to be fine structure. Now Professor Tift says that 3 studies have been made to look for power inconsistent with these equations. No deviations have been detected so far. Now, do we have any theory for period doubling? Both gravitational and Coulomb potentials are 1/r nonlinear, and it is possible to derive a differential equation in period space. So this is entirely different from space-time. We have no time here, these are structures. And we obtain a differential equation like this. We are not going into any detail. Here is the Kepler's third law. Radius cubed has function of period double, and we find that the volume doubles nicely 2, 4, 8, 16, 32, and so on. Is our world complex, or is this just an illusion? This is a fractal tree. A fractal tree is an example of an object which seems to be very complex at the top. This is an illusion, however, because the structure of the tree results from repeating the same simple principle. A closer look reveals that the stem and the branches are continuously split into 2 when going upwards. This phenomenon is called bifurcation, which eventually leads to an apparent chaos. In nonlinear dynamical systems, bifurcation means period doubling. So our tree grows from the natural constants, from the Planck scale. As the system develops, there is the first period doubling, second, third, fourth, fifth, and so on. The top of the tree is present time. There is a large number of period doublings, as we can see, we have seen already. At the top, there are many, many small crisscrossing branches. And what we do, we try to find the relations, physical relations between these small branches. But that's a very difficult task if we don't know that all these branches belong to different pickup branches, which belong to different pickup branches. And because we feel that this is also complicated, there are no clear relations between the branches, we need something that is dark, we need fluctuations, we need virtual things and whatever. These are called free parameters. But this is a very well organized system, grows from natural constants and goes nicely forward. We can say that nature is economic. One simple physical process seems to create structures from small to large. This process is the period doubling phenomenon in nonlinear dynamical systems. And then, summary. We have analyzed observational and experimental data and found distinctive marks of the period doubling process, characteristic to nonlinear dynamical systems. The key finding is that the doubling process takes place in systems formed by 3 and 4 internal degrees of freedom. The period doubling process organizes the elementary particles into groups, creates the elementary electric charge from the Planck charge and gives it the right value, explains all measurable physical properties of the electron, which are mass, charge, and magnetic moment, explains all physical properties of the nucleons and the stability of these basic particles, determines the orbits and orbital velocities of the planets from the Planck scale, not from the Sun, connects the electron-positron pair, cosmic microwave background radiation, hydrogen 21 centimeter ratio, radiation, and the sunspot cycle. Explains and predicts the quantized galaxy redshift. I must clarify a bit this last sentence. When I had found the equations for the velocity and played with numbers and the solar system, I read an article in Scientific American in December 1992 where Professor Tift explained his findings of these quantized galaxy redshifts, and he mentioned 3 velocities. I immediately noticed that these are exactly the same numbers that I had calculated with this period doubling phenomenon. So I sent a telefax to him and said that this extremely simple equation starting from the speed of light seems to yield exactly those redshift periods that you have observed. And Professor Tift replied me by telefax, we didn't have email then, that, oh yes, that's what it seems to do. And it seems to predict many more redshifts that I have in my drawer and not yet published. So we started to collaborate, and the Lehto-Tift equations were born in this way. So the period doubling process seems to create natural structures from small to large, from a common process-independent origin defined by natural constants. And that's it. Thank you.
So thank you, Professor Lehto, very much indeed. So it looks that we are living in far more ordered universe than we could expect from the existing theories. Is that correct?
Yes.
Okay.
Yes, that is correct.
Okay. So then the talk is open for questions. So please go ahead. Okay. Atocha, yeah.
Maybe I don't need a microphone.
Okay.
So
Yes.
So my question is, then do you think this could help us? Well, if you could say a bit more on that, how the structure of this table would look, and if that could be useful, let's say, to predict the existence of some other particles.
Oh yes, thank you for the question. My colleagues have very often asked me to draw a periodic table of the elementary particles, but I haven't done that yet. Sorry. But it can be drawn from the classification of the particles.
Professor Barbour.
Thank you for expanding a little bit, but I'm still a little bit mystified about these galaxy pairs. How are they
Identified, and secondly,
if their redshifts have changed in 20 years?
I mean, astronomers have got very good records of galaxy redshifts. Surely they must compare them with their and see
That either they agree or disagree with Tift's thing. So perhaps you can answer the first question. How does he identify galaxy pairs? Because I mean, all the astronomers see are just galaxies and their redshifts. They have really no other information than that in principle.
I am not an.
How do you identify a pair out of that?
I think that they are reported in the catalogs of galaxies. I don't know how they are defined to be pairs, but this is common knowledge among astronomers that galaxies and stars are binaries very often.
That is because of their morphology, I think. I suspect if they're close to each other, they will exert tidal distortion on each other. So I imagine that might be the way that they do that. But what is then the phenomenon, if we accept that there's a good way for astronomers to identify pairs of galaxies, what is then the phenomenon you say of period? I mean, what is it about them? They have the same redshift or what?
No, the redshifts of the components of the pair are different, although they are physically connected. So I would like to add that.
Well, that would then be relying upon possibly statistical chance. I mean,
No.
Well, I would agree. And it seems to me absolutely crucial to this is how the pair is identified.
Well, they are physically connected. If you scan with the 21 centimeter wavelength across the galaxy pair, you see that they are physically connected. And that is one indication of that it is pair. There are arcs that connect the galaxies.
It's only seen at 21 centimeter.
No, it can be seen in the infrared too.
Okay.
But anyway, there is a redshift difference between the components, although they should be at about the same distance from us because they are pairs. That's why Professor Tift thinks that this has to do with some internal property of the galaxy. So the galaxies are energy systems which depends on total mass of the galaxy. But of course they are moving around in the space, and that obscures, of course, the quantization if all galaxies are plotted. We need to measure the redshifts for a system of galaxies. For instance, in our local group, the peaks of the distributions are very sharp. But Tift published a book of all his works last year where all this is thoroughly explained. Professor Tift calls galaxies hyperparticles because they have their distinctive structures and properties. So this is property of fractals. It's the same for the small and the large and in between.
Okay, any other questions? Yes, please.
Thank you. Galaxies are energy systems. Would you please open that idea more? Thank you.
Energy is frequency or period. And we showed that there are 3 intrinsic degrees of freedom within these systems, which means that there are kind of 3 independent energies which form a phase space volume, which is joules cubed. But because we observe joules, we need to take the cube root or geometric mean of the 3 energies, and then we get what we observe. But I refer to the relation between period and energy. So we see the period doubling or energy halving in this system. And this is now speculation, but I think that what I call energy is the gravitational energy of the system. But this is speculation. I don't know.
So, okay, I'm sure that you have been asked many times that what is the probability that this is just a coincidence that we fit those specific numbers?
For all these that I showed, yes, a statistician friend of mine calculated that the probability of coincidence is almost 0.
Essentially 0.
Yes, but not
Okay.
quite.
There's still time for one short question. So is there anyone having something important in your mind? Okay, then we once more thank you, Ari Lehtova, very, very interesting this presentation. And we have coffee served at the second floor here. We will come back in half an hour and continue at 11:15. Thank you. Okay, I think we are ready to start and continue our workshop. I have a great pleasure to introduce Professor Ilkka Niiniluoto, who is very well-known person in the academic communities in Finland. If we shortly look at his background, he's both philosopher and mathematician. He started as associate professor in mathematics in 1973 up to 1981. The Philosophical Society, pay attention to the long period, he served as the president of the Philosophical Society in Finland for 40 years, ending last year. That's maybe a record or that kind. And professor in theoretical philosophy, 1977, Acta Philosophica Fennica, editor-in-chief, 1980, and then the rector of the University of Helsinki and chancellor of the university, 1908 to 2013. And we may remind that Professor Niiniluoto's significant contribution to the philosophy of science, particularly to the concept of verisimilitude or truth approximation in his Truth Likeness, which is published as Syntis Library by Springer, and another notable publication is Critical Scientific Realism from year 2002. So, Professor Niiniluoto, audience is yours.
Yeah. Okay.
We take this and continue from here. Presentation mode. And now we have the laser pointer here, so you can choose between these two.
So thank you, Tuomo Suntola, for this introduction, ladies and gentlemen. Thank you for the invitation to this workshop. Now, there are different opinions what is the most fundamental question within philosophy of science. The famous Austrian-British philosopher Karl Popper argued that it is the demarcation problem which tries to define science and distinguish science from other kinds of activities and non-science. I think the most fundamental question concerns the relation of science and reality. And there are, of course, very, very different answers to that question. The Finnish philosopher Eino Kaila, who is still well known to many of us, at the end of his career, he came to the conclusion that the relation of scientific theories and reality should be analyzed in terms of isomorphism, so some sort of structural similarity, and that anticipated treatments which are today known as structuralist approaches to science, or even structural realism, which claims that there is only structure in the world, and the task of science is to find what this structure is. Now, my own approach is similar but slightly different. I'm, in a sense, using the perhaps more old-fashioned way of treating scientific laws and theories as statements which can be formulated in language, but usually by means of mathematical concepts and by means of mathematical equations. And then the answer to the relation between scientific theories and models and reality is in a nutshell to be expressed by the slogan, which is my title, that science approximates reality. And then the task is to analyze this approximation relation, and what I will do in my lecture today is to start from a historical example of approximation, which not only was important within the history of science and astronomy, but also important for philosophers of science when they started to think about this idea of approximation. and that example then leads me to the more general issues about science-reality relations and to the notion of truth-likeness, which was mentioned in this introduction. So some of my works where I have discussed this issue about the relation between science and reality include the books Truth, Likeness and Critical Scientific Realism, but also some articles on the same topic. The most recent one, Approximation of Laws, in 2014. So let's look at in very broad outlines the development of astronomy. So in early astronomy, we had sort of observational approaches. There were everyday observations, or perhaps one should say every night observations when the stars were visible, observations of the sun, the moon, planets, and stars, and some records in early culture were made of the movements or the apparent movements of these different stars. And then very vague generalizations about these apparent movements were made by vague qualitative concepts. So we have sort of unexact statements, approximate statements like in everyday language that the sun rises from the east and sets in the west. That is what we all learn as a child. But then in Greek astronomy, especially in Plato's Academy, the task of giving a scientific account of these movements was given, and that was formulated by the demand that there should be some kind of account which would save these appearances by using circular orbits. So there should be a system where these stellar bodies are moving in circular orbits, and you should then be able to put the system to work in the way that it gives us as a result the observed movements of these planets. Now Aristotle, who was Plato's pupil in Athens, he thought that this kind of treatment gives answers to why questions. So besides knowing that, which was Plato's concern, knowledge in Plato's sense means that we have true and justified beliefs. Aristotle was interested in knowing why, or explanations which tell the reasons or causes for observed events and processes. So this task of saving the appearances of the movements was interpreted already at the time in two different ways. One was the instrumentalist view, assuming that this is only a conceptual tool of saving the appearances, in the sense that we don't argue for any reality for these assumed systems and mathematical orbits, etc. So this is simply an instrument for presenting the phenomena. But then the realists, like Aristotle and some of his followers, thought that these systems which explain observational phenomena are real, and they have a truth value, they are even necessarily true. So this division between realism and instrumentalism has been also a fundamental difference between philosophers of science, and that is still a very active debate among us. And I myself have tried to defend the realist position. Now, when Ptolemy gave his geocentric system, that was interpreted in both ways. Some thought that it is simply a mathematical instrument for saving the appearances, and when he added all kinds of epicycles there, it was not so problematic, except that it led to a very complicated system. But some astronomers also interpreted Ptolemy's system as, in the realistic terms, as a true description of the phenomena and astronomical systems. When Copernicus then formulated his heliocentric system, his own view was clearly the realist view, but it was not acceptable to the Catholic Church to state that the real movements are around the sun, and the sun is a stable center of the system. And the Church allowed the teaching of Copernicus and its use for predictions only on the condition that it was not interpreted realistically. But many followers of Copernicus and then the great astronomers, Kepler, Galileo, and others, favored the realistic interpretation, arguing that this is the true account of of the solar system. A very clear account of this historical debate and interpretation of theories has been given by the French philosopher and historian of science, Pierre Duhem, in a book called Saving the Phenomena. Now, the next step is Kepler. Johannes Kepler formulated his 3 laws, the first 2 laws in 1609, and the 3rd law in 10 years later. And as you all know, the first law differs from the idea that the orbits of the planets are sort of perfect circles. So Kepler's law says that the orbit of each planet is an ellipse with the sun at one focus. And then the second law says that a line joining a planet and the sun sweeps out equal areas in equal times. So these are already mathematically precise formulations of laws based on observational astronomical data. I'm more interested here in the 3rd law, the so-called harmonic law, which says that the square of the orbital period of the planet, this is t, this is the time what the planet needs for making its one circle around the sun, that is t, and the square of t is directly proportional to the cube of the semi-major axis of the planet, and this is a. And this a is also the average distance of the planet from the sun. So Kepler's law states that, let me see if I can use this laser pointer. So we have here the law t up to 2 divided by a up to 3 is a constant for all planets. So again, we have a very clearly formulated mathematical equation based on data. Here is an account of Kepler's data. So the planets in his account were Mercury, Venus, Earth, Mars, Jupiter, and Saturn. And here we have the values for t measured so that the sort of astronomical unit is the orbit of Earth, that has value 1, and then we have the values for other planets in relative terms to the orbit of the Earth. Then we have here the values for this for A. Again, the distance of Earth from the Sun is 1, and then we have the relative distances of other planets from the Sun. And here we have the value which is in Kepler's formula, t to 2 divided by a to 3, and we can see that it gives quite accurate result on the basis of this data. All these values are very close to 1 with very small distances in some decimal values. So it seems that this is quite accurate or quite good approximation what Kepler was telling, and one can also find then this same or use the same calculations for the data concerning the new planets which were discovered after Kepler, Uranus and Neptune, and that formula gives also fairly accurate predictions for these values. So Kepler's result was quite successful and celebrated as a new scientific discovery. Now then comes Newton, and Newton's Principia in 1687 was praised especially for its ability to unify by his universal law of gravitation many earlier results of astronomers and physicists. Not only Kepler's 3 laws were consequences from Newton's general theory, but also Galileo's law of free fall and other phenomena like the precession of equinoxes. So there were many phenomena which were had been independently discovered. There was no antecedent grasp of the idea that there could be some unifying theory which explains all of them, and Newton's great achievement was this ability to unify these different empirical laws. The British philosopher of science, William Whewell, who is one of the first professional philosophers and historians of science, in his 1840 book, Philosophy of the Inductive Sciences, called this phenomenon the consilience of inductions, meaning that we have sort of inductive empirical generalizations coming from different directions, and then we have unifying theory which conciles or combines them in the sense that it explains these independently discovered empirical phenomena. And that was, he illustrated this kind of tendency to unification or tendency to more powerful and simpler theories by what he called inductive tables from physics and optics. And this idea that theories explain laws by deductive arguments was important at that time. John Stuart Mill, in his System of Logic, 1843, he had some differences with Whewell. They were arguing against each other. Mill was more empiricist. Whewell had some Kantian ideas in his system, but still both agreed that Newton's theory explains Kepler's laws, and Mill was one of the first to give a kind of general account what this explanation means, that we have a general theory, and then we can deduce by using logic the empirical law as a kind of special case of that more general law. So the deductive explanation, which was then later more precisely formulated by Popper and Hempel in the 1930s and 40s, was already proposed by Mill. Now, next person in this story is the French historian and philosopher of science, Pierre Duhem, who wrote a famous book on the structure of scientific, the aims and structure of scientific theories in 1907. Duhem was an instrumentalist, so he did not accept the idea that science explains anything. He didn't accept that theories are truth. He thought that they are simply devices for systematizing observational phenomena. And he had an argument about the relation of Newton and Kepler, where he concluded that formally Newton's theory contradicts Kepler's law. So it is not the case that Kepler's law is a precise deductive consequence of Newton's theory, but rather they are incompatible. They contradict each other. And Karl Popper, who famously denied that induction has any role in science, accepted Duhem's claim. He thought that it sort of supports his idea that scientific theories are not obtained by inductive reasoning from empirical phenomena. So Newton's theory is not an inductive generalization from Kepler's laws because they are in fact incompatible with each other. But another, well, that is of course an issue which can be debated, and I will not be talking about the problem of induction here. I think Popper was exaggerating his criticism of induction, and there are interesting new treatments of the generation of Newton's theory from the evidence that he had at his time. William Harper has written an interesting book on that, and in Finland, Oiva Ketonen in Suuri maailmanjärjestys wrote an interesting account of that already in the early 1950s. Now, but for the purposes of this talk, there is another aspect of Popper's remarks which is more interesting. He noted in a paper in 1948 that even though there is some discrepancy between Kepler's and Newton's laws, Kepler's laws can be obtained from Newton's laws approximately by the assumption that the masses of planets are negligible compared with the mass of the Sun. So the Sun is much larger than the planets in terms of their mass, and if the masses of the planets are sufficiently small, then there is some kind of approximate relation between these laws. And in 1957, Popper also formulated this case by concluding that Newton's theory unifies Kepler's laws and Galileo's laws, but it corrects them while explaining them. So this is an idea of corrective explanation, that a theory can be used for explaining some empirical laws, but at the same time the theory may give some corrections to the original observational or empirical law. Similar ideas were formulated by Wilfrid Sellars, who was a famous defender of scientific realism. And then Carl Hempel, who gave a precise formulation for this deductive model of explanation, he referred both to Duhem and Popper and this Kepler-Newton case when he proposed in 1965 that there are approximative deductive nomological explanations, and the Newton-Kepler case is one example of that. So let's see how this relation can be given. This is based on sort of standard accounts of textbooks in physics. So we have capital M is the mass of the Sun, small m is the mass of a planet at the distance r from the Sun, and using the approximation that the tangent of an angle theta is approximately the same as theta, then for a planet moving with velocity v along a nearly circular orbit, the centripetal force towards the Sun is m times v up to 2 divided by r. And by Newton's second law, F is ma, we see that this means that the acceleration of the planet towards the sun is v up to 2 divided by r. On the other hand, by the law of gravitation, this acceleration is a constant g, gravitation constant g, times m, small m plus capital M divided by r up to 2, and hence combining these two formulas we get the result that v up to 2 is equal to g times small m plus capital M divided by r. On the other hand, v, because this movement is approximately circular, v is approximately 2 times pi r divided by t, and using then simply taking the square of these values, we get this formula here, and just by combination we have the result that t up to 2 divided by r up to 3 is 4 times pi up to 2 divided by g times capital M plus small m. So this is the derivation that we can have from Newton's theory, and as you see, this derivation already uses some methods of approximate reasoning. But what is interesting here is that this derivation gives a correction to Kepler. Now, Kepler's original law stated that this ratio of t up to 2 divided by a up to 3 is a constant for all planets, but this new formula shows that this value in fact depends on the masses of the planets. So it is different for different planets, because this mass of the planet is here included in the formula. But from this more general result, we can also give sort of conditional statements which say that if we have planets whose masses are approximately equal, then the ratios which were in Kepler's original law would be approximately equal. And also, if the mass of the planet would be 0, then it will disappear from the formula, and we get the result that this ratio is in fact a constant which is independent of the mass of the planet. So Kepler's law is a kind of counterfactual special case of the more general result, and often you can see that in textbooks Kepler's law is derived from Newton's simply by assuming that the masses of planets are negligible, so that the acceleration of the sun towards the planets can be ignored. And in that case, you get the original Kepler's formula derived from Newton's. Now, this corrected form of Kepler's law here is still not a final truth. It is still idealized in some respects. For example, the permutations from other planets, the influence of other masses in the system is not included in this formula. And of course, then the step from classical physics to relativistic physics will also introduce some small changes which should be stated in the more complete account. So the relativistic effects are not included. But still, one can say that Newton's theory gave this kind of corrective explanation, approximate corrective explanation of, of Kepler's harmonic law as Popper and Hempel suggested. And in the same way, we have the relation of Newton and Galileo. From Newton's theory, you can derive Galileo's law for freely falling bodies with some simplifying assumptions. So Newton's law approximately entails that for a freely falling body at the height h from the surface of the Earth, which is assumed to be a perfect sphere with radius r and mass m, we get the formula from Newton's law, which depends on the height of that body from the surface. And if you simply neglect this quantity h from this formula, you get the original formulation of Galileo's law, stating that so we have this traditional formulation that the distance traveled by this falling body is minus g t up to 2 divided by 2. But again, we have this kind of approximate explanation of Galileo's original law, and there is a more elaborate, in fact more precise law, which is derivable from Newton's theory. So to generalize then from these explanations we have, or these examples, we have the concept of approximate explanation. We have the initial question, why E, where E is some empirical regularity or law based on observation. So it could be Kepler's third law or Galileo's law as they stated it. And then we have a theory like Newton's theory T, and we derive a consequence E prime from T. And if the consequence of our derivation is too far from the original law E, so the distance between E and E prime is too large, then the explanation fails. But when the distance is sufficiently small, then we can say that the theory T approximately explains E. And so I think this is the kind of key idea of approximation in science, that we need some sort of way of measuring the distances between in this case laws, which are usually mathematical formulas or mathematical statements, and then if we have this distance measure, then we can also introduce the idea of approximate explanation. And in Kepler's case, the distance should say that his original law and the one which derived from Newton's are approximately equal. So they are approximate counterparts. So the difference is not very small. And the idea of corrective explanation means here that when we derive from the theory T a consequence E prime as an answer to the question why E, so this is the case of approximate explanation. This is corrective explanation if the consequences of the theory are more accurate or more precise than the original empirical laws. So in the Newton's case, if the consequence which allows that there is some very small variation among the planets with different masses, if that is more accurate than Kepler's original law, then we have this corrective explanation. Some philosophers of science prefer to formulate explanatory questions not simply as asking why something is the case, but rather we have contrastive explanations why E prime rather than E. So we have two alternatives, and then we ask a theoretical explanation why one of these alternatives is in a sense better than the other. For example, Frank Hendricks has used this kind of idea of contrastive explanation in his formulations. Again, to generalize this idea, there are many relations between different types of statements or systems in science. So we have here we have the world itself. By observation and measurement, we can obtain data about the world, empirical data, and a theory is valid or more or less accurate relative to such data. From such data we may obtain by induction or by methods of confirmation more general laws, and then, as illustrated by the Newton-Kepler case, a theory may explain such laws. And then from laws we can formulate more general systems of laws or theories by perhaps using some unifying ideas. So we have this step of theory formation to theories, and then we have inter-theory relations, so the relations between theories which can be studied, and usually the notion of reduction is used in such cases. So we have large-scale theoretical systems and another system, and reduction means that one of the systems or its elements, the laws in that systems, can be derived from the reducing theory. And the idea of approximation, which I illustrated in this case from the explanation of a law by a theory, approximately can be then applied to all relations within this picture. So we can speak of approximate validity or accuracy of the theory-data relation. We can speak of approximate reduction as inter-theory relations, and then finally we can speak of modify the idea that the theory is true about the world by the condition that this relation is also in some sense approximate. And the key to all these approximation relations is that we need an account of approximation or distance between these linguistic statements. So to illustrate that, we have approximate success. So the success of theories in explanation and prediction is often approximate. The validity or accuracy of a theory, its relation to empirical data, is often approximate. And for example, in so-called curve fitting, we have some observed points in some coordinate system, and we try to find a law which would give account of this law, and then we can measure the similarity or fit between a law and data. This was used by in astronomy by the least square difference methods, and then statistical regression methods are using similar accounts of such approximate success. Approximate reduction then means that relations between theories are often approximate, which means that the laws of one theory approximately reduce to the laws of another theory. And again, to make that idea precise, we need some account of this approximation relation. Now, within philosophy of science, there is an interesting criticism of the standard analytic philosophy of science and its treatment of theories by Hempel, Nagel, and others. That was stated by Polish philosopher Leszek Nowak, who was interested in idealization as a general method in science, and he argued that the method of idealization is something which is common both to the natural sciences like physics and the social sciences like economics, and his main figures in history are Galileo in physics and Marx in economics. And Nowak argued against Hempel and others that their treatment of explanation ignores the idealizations in scientific laws and theories, and there is a whole Poznan school which has worked on this problem of idealization. Among others, besides Nowak himself, there was Vladislav Krajewski, who wrote a well-known book on this topic. Now, Hempel's conception of approximate explanation was one kind of answer to Nowak's criticism, but more generally, I think it's important to note that one source for the fact that theories are in an approximate relation to data laws and even reality is that the theories are usually idealizations in the sense that such theories or models represent reality by deformation or one could even say caricature, in the sense that some relevant properties are neglected by ignoring them or by assigning them extreme values. So when Galileo was studying free fall, he assumed that there is no resistance of air. That was an idealization. He gave the law in a form which excludes that factor, which in reality is always present when we have free fall within our circumstances. So Galileo was using idealizations, and this method is used by all sciences in formulating theories and models. Or classical physics, it looks like classical physics, the relation of classical physics to the relativistic theories seems to assume that the velocity of light is infinite, so it can be obtained as a special case from the relativistic equations by letting this velocity approach infinity. Now, so an extreme value, which is counterfactual. But the fit of the theory and its the domain of its description can be improved by what Nowak called concretization, which means that those idealized factors are reintroduced to the equations, and then the law is modified. So for example, Galileo's law can be modified by introducing the resistance of air and thereby making it more accurate. And what is required in general in such cases of concretization is that the principle, what Bohr called the principle of correspondence, holds that the old theory is a counterfactual special case of the new one. And an illustration of this idea of idealization and concretization comes from physics. Again, we have Boyle's law, which says that for ideal gases, the pressure and volume, the pressure times volume is a constant. We have a more precise formulation by Boyle and Mariotte saying that this is P times V is R times T, where T is the temperature of the system and R is a constant. And this law holds for ideal gas, but not for real gas, but it can be improved or concretized by introducing some of the neglected factors. So let A be the intermolecular forces, so the gas is a system of molecules, and there are some forces between attraction between these molecules, and let B be the finite size of gas molecules, so they are not of size 0. But we have the concretized form of the Boyle-Mariotte law, which is known as van der Waals law, which has this form, where these new factors are introduced. And from this formula, we can obtain as counterfactual special cases the original Boyle's law, because if A is 0 and B is 0, then this reduces to this original form. So this illustrates the idea that we first have this idealized law, and then it can be concretized into a new formula, and from that new formula it is required that by letting these new factors to take some extreme values, there we get the original one. And of course, van der Waals law is, again, it's not any final truth about gases. It is still idealized with respect to some other factors. But this method is illustrated by this. So, in general, we can say that two scientific statements are approximate counterparts if their distance is sufficiently small, and that allows us to define notions like approximate validity, approximate explanation, approximate reduction. And then we can also say that science approximates reality, which is, of course, a tricky one, because reality is not a linguistic entity, but something else. It is a material system with forces and energies and qualitative properties, etc. But if we want to introduce the idea that science approximates truth, then I think we have to analyze that also by saying that science approximates some true statements about the world. This presupposes the notion of truth, and which I think is a notion which was precisely defined by the Polish logician Alfred Tarski. So I'm presupposing that notion of truth. And then Popper in the 1960s proposed that we could introduce the idea of approximate truth or truth likeness or verisimilitude, which expresses the distance of a theory from complete truth. And in the special case, when truth is expressed by a true law, this is sometimes called not verisimilitude, similarity to truth, or verum, but rather legisimilitude, similitude to laws. This is the term used by Jonathan Cohen. And here the general picture looks like this. We have here some real system which we are interested in studying. We have here, within some conceptual framework, the complete truth about this system, and a theory may be then similar to this complete truth, and if it is similar to the truth, then it has verisimilitude, or it is truth-like. So truth-likeness is a kind of combination of truth and similarity. Popper's original definition of truth-likeness lacked this idea of similarity, and it failed. But others then have tried to improve his idea by introducing this approximation or similarity relation between statements. And another way of looking at the situation is that a theory is true about a model, and then this model is similar to the real system. So there are two ways of formulating the idea, either a similarity between the system and the model, or similarity between the complete truth and a theory. And for this analysis, we then need definition of the distance between statements, and I think that has to be worked out in special cases in different ways. It depends on what kind of statements we are using. My own first formulations were introduced for qualitative languages, so we have some sort of first order logical language with qualitative predicates, and then we have constituent structures in the sense of Jaakko Hintikka, and we can introduce distances between constituents. This is one case, but then later I also used distance measures for mathematical statements or quantitative statements, and including singular quantitative statements and general ones or laws which can be expressed by mathematical equations. And for the quantitative case, we have already from mathematics a quite elaborated machinery of metrics which can be introduced for various kinds of mathematical spaces or state spaces. So if we have singular quantity, real valued quantities, we simply have the geometrical distance between them. If we have quantities in the n-dimensional Euclidean space, there is a variation of measures here, like the Manhattan or city block measure, which simply is the sum of the differences between the coordinate values, or the Euclidean measure, which is given here, and then the generalization to real valued functions, which I propose to use for the purposes of philosophy of science, is using the Minkowskian LP metrics between two functions. So let's assume that our two laws are expressible by real valued mathematical functions f and g. Then this is the general Minkowskian distance between the functions, and for different values of p we have some slightly different emphasis of the situation. The value P1 is a generalization of this Manhattan measure. P2 is the Euclidean measure, which looks like the least square measure, least square distance. And for P as infinite, it gives the Chebyshev distance, which is simply the maximum of the distances between all values of these functions. And these different cases behave in different ways. I don't know if you see this, but if we have here the true law, and we have two alternative laws, then for the red one, the maximum difference from the true law is larger than for this one, and the Chebyshev measure would give different answer than the Euclidean one in those cases. So for small values of p, these measures are roughly measuring the average distances between these two functions, and for large values of p, the emphasis will be on the maximum distance. There is an interesting article on these quantitative approximation measures by Chinese-American philosopher Zhang Liu, Approximation, Idealization and Laws of Nature from 1999, where he gives some arguments against using these, these Minkowskian measures, and I have tried to answer, to give an answer to Liu's criticism in a paper in 2014, which I mentioned in the references. Now, one of Liu's points is that such distance measures, which I had proposed, are flat in the sense that they assume a kind of Euclidean state space, and he thinks that it would be interesting to consider also the possibility that the distance of a singular statement from the true point would somehow depend on the location of the true law in the state system, and that would lead to a kind of a new kind of metric which depends on closeness not only to the true point but also to the true law, which makes it more complicated, and I think to solve that kind of worry, one should introduce some kind of non-Euclidean state spaces where the metric circles are replaced by ellipses, which are sort of influenced by the location of the true law in the state space. Another point by Liu is that there is a sort of contrast between the idea that closeness between two functions depends on the distance between their values, and on the other hand, and the idea that it is good if you have the correct mathematical function identified. And they may give sort of different results. It's possible that a false law still gives a correct mathematical formula or mathematical function. For example, it is quadratic or linear, but it is still further from the true law in all of its individual values. And to answer that kind of worry, I think one should then one could propose that these two criteria are combined with each other, and we have a kind of two-dimensional way of measuring these distances. But given that we have these distances, we can then say that it makes sense to say that one theory is closer to the truth than another. This was what Popper intended with his notion. Or we can define precisely that the sequence of theories approaches to the truth, and we can analyze scientific progress in the sense that theories are increasingly truth-like. That was also Popper's intuitive idea, and I think that can be defended by the similarity approach, which has been worked out by many logicians and philosophers, including Hilpinen, Tihi, myself, Oddi, Kuipers, Festa, Surge, and others. I will not then say more about this approximation. This is my concluding slide, and I think this kind of treatment of approximation gives us a realistic picture of what science can aim with its theories and models, and this is my sort of my general formulation of scientific realism and the claims. Of course, to defend all of these theses is a quite heavy task, because there are, on all points there are different alternative philosophical approaches, but in any case, in my critical scientific realism, I accept the ontological thesis of the existence of mind-independent reality. I accept the semantical idea of truth as correspondence. I accept the theoretical realist view that theories postulate theoretical entities or mechanisms or systems to explain observable phenomena and regularities. I accept the epistemological thesis that it is possible to have knowledge about this mind-independent reality, and scientific inquiry is the best indicator of the success of such theories or the truth. But I'm at the same time a fallibilist in the sense that all human knowledge is uncertain or corrigible. This was Charles Peirce's formulation. And the best results of science may be false because they are usually idealized, but still they may be probable, truth-like, or approximately true. And finally, I accept the so-called no miracles argument that the best explanation of the empirical success of theories is their truth or truth-likeness. So truth simply would be too strong requirement of all theories. Truth is a goal or aim of science, but in practice, by introducing theories and models, we may obtain more or less truth-like representations of reality, and that is the basic thesis of scientific realism. I think I have now used my 1 hour, but that leaves still time for discussion.
Heikki.
Is it possible to talk about the laws in same sense in physical sciences and like economics and politics, social sciences?
Yeah, that's a good question, and there are different opinions of that. Of course, in some fields of the social sciences, it's possible to use quantitative methods. So, for example, in economics and econometrics, you introduce mathematical models to represent economic phenomena. So you have formulations which look like laws in physics. They are quantitative and precise. But on the other hand, there is a difference between social reality and natural reality. In the sense that I accept the idea that laws of nature are some sort of permanent features of the mind-independent world, but regularities in the social reality are not so strict and not so permanent. So they may be more temporary and there may be even sort of temporal changes in such regularities. But certainly one can use similar methods in both cases.
How would you compare two theories that explain the same phenomena and observations, but have entirely different starting points?
Yeah, that's also a good question, because one of the challenges in philosophy of science was the thesis of Thomas Kuhn and Paul Feyerabend that different theoretical systems or frameworks can be incommensurable in the sense that there is no common measure of comparing them, and so in different conceptual systems there is variation of meaning change, meaning variance, and this concept of truth-likeness, as it is usually formulated, presupposes that we have one language where we formulate the alternative theories, and then we compare compare alternative theories within the same framework. and then the next question is how to extend that to cases where where we have theories coming from different frameworks. And I think that has to be solved by trying to find some sort of broader framework where both of these alternatives can be expressed, and then make the comparison in that higher framework. That involves quite tricky problems of translatability, and it's not an easy task, but I think it can be done.
Okay, other questions? Professor Barbour.
Just a very quick comment. Of course, within quantum mechanics, that's exactly what happened initially. The Heisenberg and Schrödinger pictures looked totally different, and people were puzzled. But then after a few months, Schrödinger showed that there was a larger framework in which...
Yeah.
And then it was developed by Dirac to show that there was an overarching thing which really could understand how it went on. I have a question, though. You're selecting out Kepler's third law has really made me think a little bit to what extent Kepler would have regarded his own work as a theory. And now he was sent to work by Tycho Brahe to explain the notion, to explain Brahe's observations. And it would seem to me that Kepler would have described his first two laws as actually just establishing, so to speak, empirical relationships. He wouldn't have thought of them as a law.
Yeah.
It just occurs to me from what you're saying, and you put in harmonic. Kepler, of course, was obsessed with the idea of the music of the spheres, the celestial harmony. And of all his three laws, perhaps the one he would have regarded as a theory in the modern sense would have been his third law. Would you agree with that?
Yeah, well, Kepler is an interesting historical figure, of course, because he had, besides being a very, very successful astronomer, he believed in astrology, and he had very, very strong metaphysical ideas about the sun and its meaning for the universe, and which were sort of speculative ideas, but in any case, they influenced his work, and certainly the harmonic law was a kind of triumph for Kepler's ideas. Whether this kind of regularity is then called a law or a theory, I think that's a sort of semantic question. Sometimes there is a difference between them, but sometimes they are simply used as equivalent terms. But certainly the harmonic law was very important for Kepler. And what you said about quantum mechanics, it is true that some formulations of theories which may look very different, then one may be able to prove that they are in fact equivalent, and that was the case with different formulations of quantum mechanics.
Okay,
Yeah.
Professor, please.
Yeah.
Well, thank you for your talk. I like very much this approach, but let me bring Charles first into
Yeah.
in the following sense.
Yeah.
This account explains really well, or is an account of how science approximates, but it doesn't bring the scientist, him or herself, into the picture. So if we think of how a scientist approach they hit on the right theories, first we say that it's not only a realism that we have to assume, but also we need an additional assumption, in a sense that human nature, in this sense that humans are tuned to nature. So that's why we can hit into the good hypothesis and we are closer to it. So although you may not need to take this into account because your approach is how science
Well, thank you, Professor Aliseda, for this for this question. Charles Peirce is an important philosopher as a background of critical scientific realism, because he had this idea that science approximates the truth. So science converges to the truth, or science is self-corrective in the sense that that even though our theories are false, then we may improve them by correcting them, and then we come closer to the truth. But he didn't make that very precise, and so it was first Popper who tried to give an exact logical definition for this idea, but he failed. His own students showed that his definition doesn't work, and then that has been worked out as I see sketched here. But Peirce had another idea which you referred, that he was interested in also in the process how scientists discover truth. So that is sometimes called the logic of discovery. And Peirce had the concept of abduction, which describes the process of finding explanatory theories. And some philosophers think that is a good account for this discovery process. Peirce was also puzzled by the fact that the scientists in many cases have been able to formulate true theories. Well, or at least I think we should say truth-like theories. So we have the ability to grasp some important aspects of reality, and Peirce had a somewhat speculative idea that, as you said, human beings are tuned to reality, in the sense that they have a kind of inner capacity, and he referred to Galileo's notion of natural light, or il lumen naturale, which is a kind of innate ability to find true hypotheses about nature. But well, I think to some extent that can be justified at least in contexts which are relevant to the theory of evolution, because we have developed within the world, and our way of perceiving the world and understanding the world has been such that we have been able to survive here, and that means that we have some capacities of understanding nature. But whether that can be extended to very abstract situations of contemporary physics, where we have theories which look very strange from the everyday perspective, like quantum theory, then I don't know. Peirce himself anticipated some of the indeterministic ideas of quantum theory already in the late 19th century, but whether he would have claimed that we had some sort of innate idea which led to quantum theory, I don't know. But that's an interesting theme. Yeah.
Okay, thank you. Okay, Tarja.
Yeah, I think the main criteria for evaluating theories are sort of epistemic criteria. So theories should be true, truth-like. They should give accurate accounts of what has been observed. So they should be accurate in that sense. They should have explanatory power. They should have predictive power. This ability to give sort of independent predictions, which were not anticipated in advance, it has been a very important aspect of theory evaluation. But then we have also what might be called aesthetic criteria, and usually scientists, when the other conditions are satisfied, then they prefer theories which are somehow beautiful or simple or such that they can be managed and handled by us. So there are sort of there is a kind of hierarchy of different kinds of criteria. Eino Kaila, whom I mentioned, had his concept of relative simplicity, which was a combination of explanatory power and simplicity. So a theory should explain as much as possible, but then at the same time it should not be too complex. So, and that's there is a kind of trade-off between these two criteria. But in the history of science, you have examples like Kepler, who had his kind of metaphysical vision in the background of his preference for the heliocentric system, for example.
Further questions? Okay, then, okay, Heikki.
I think Professor Kurkis once, when he made definitions, tried to make definitions in one of his papers, what should be the criteria for a good theory. One of them was that it has no practical use before it is accepted by the Institute of Science. And this seems to be the case in many cases. We might have potential true-type theories, but before they are sort of accepted and recognized by the Institute of Science, there's no meaning to them. What is your opinion on that?
Well, following Peirce, I think the introduction and evaluation of theories is a task of the scientific community. So we need the community, as Peirce said, that the individual scientist has to identify his or her interests to the unlimited community of all investigators, present and future, and that is the only guarantee that we eventually find the truth, and that requires that this community is autonomous and using objective standards for the evaluation of theories. So there is a danger of this practical applicability has the danger that we would favor theories which are in some sense profitable for us. It would be good for us for economic terms or for some personal preference to if this theory would be true, and then we introduce some non-objective criteria for our assessment of theories, and I think that kind of danger should be avoided, and therefore I think the demand of objectivity is so important in science. But it is a community issue, so it is really up to the community to have also an open-minded discussion about new ideas but then also the possibility of open criticism of different proposals, and that in that way science may then make progress.
Okay.
Often said that science is public, critical and self-correcting. I would like to ask your opinions about
Yeah. Yeah, that really depends on different cases. Today there are more living scientists than ever, so we have more than 1 million refereed articles published every year. So the scientific progress in that sense, assuming that the referee system is working well, it means that all of these more than 1 million papers per year introduce some new ideas. But some of them then also correct earlier ones, so they make earlier claims more precise, more accurate, perhaps even reject old theories and improve them. So in that sense, one could think that scientific progress is quite rapid, but perhaps there is also quite a lot of repetition within this enormous amount of scientific publication. So not all published papers introduce great new ideas, but largely repeat old ideas and do not really contribute to progress. And there are many articles which are not cited at all, perhaps not even very well read. So there are great differences between the acceptance of new scientific information and depending on the field where you work. So clearly there are sort of stages where one scientific discipline is advancing very rapidly and then more slower periods when nothing seems to happen.
Okay, so we are almost ready to lunch. May I make a layman's question, layman's logic? Yeah. So you spoke about distance to the truth. Yeah. Can we measure the distance to the truth without knowing the truth?
Yeah, that's a very good question, and that has been presented as an argument against the concept of, or the applicability of the concept of truth likeness. And I think there are two different issues. One is the logical problem of analyzing what it would mean to be close to the truth. So, like when Tarski was giving his definition of truth, he assumed that we have a language and statements, and then we have a model or structure, and then he asked what it means to say that this statement is true within this structure. So that both were given. The statement and the structure were given, and then Tarski analyzed the truth relation between them. But that is, of course, a different question than how we can know whether some claim is true. So this epistemic question is different from the conceptual question. And what I was here discussing only was the sort of conceptual question, what it would mean to be close to the truth. And that was Popper's logical problem of truth likeness. But Popper introduced, also stated that in some cases we have good arguments to claim that one theory is closer to the truth than another. And his example was Einstein's theory of relativity is closer to the truth than Newton's classical mechanics. But it's of course quite tricky. If we don't know already the truth, how can we measure distance to that? And my own proposal in this truth likeness book is a kind of probabilistic approach. That if we have some probabilistic account or beliefs, rational beliefs, where truth may be, then we can estimate closeness to the truth. So, for example, We don't know exactly how many, or what is the population of Finland. No one knows the precise correct answer. But still, if I claim that it is 4 million and you claim that it is 5 million, I think you are closer to the truth, even though we don't know the exact number. And I think that sort of argument can be defended by assuming that we have some kind of probability distribution of these values of the population, and they concentrate somewhere over 5 million.
Saying physics, I would still like to make a short reference to some of our discussions with Professor Kalle Kurkisuonio. So instead of using the term postulates, he prefers saying that certain things are experimental facts, such as the constancy of the velocity of light. Yesterday we had a discussion which showed that once we study a little bit more detailed the quantum mechanical solution of the atomic oscillators, we can show that the frequency of the clock is directly proportional to the velocity of light, which means that whenever we use that instrument for measuring the velocity of light, we get the constant value. And that's what Professor Raimo Lehti called the conspiracy of the laws of nature. What do you think about that?
Yeah, that's an interesting issue. I don't think I have a ready-made answer to that, but yeah.
Okay,
but that's also a kind of classical problem which occupied Eino Kaila and others, that sort of difference between realism and conventionalism. Conventionalism claiming, Poincaré and others, that all laws are simply conventions and we can simply make choices between different sort of conventions, and the realist arguing that there is still some standard from the reality which decides which system is better. But that is a classical case of that problem.
Okay, thank you very much. And we now have the lunch break, and we continue 1:30. Lunch is served in the cafeteria here, Tiedekahvila, Science Cafe, at the lobby floor. Thank you. Okay, welcome back again. So now we have real pleasure to listen to Professor Atocha Aliseda. She comes from Mexico and serves as the professor of National Autonomous University of Mexico, the Institute for Philosophical Research, and the National Research, and UNAM. And at UN, what means UN? UNAM. Yeah, but what does it mean?
It means the National Autonomous University of Mexico.
Okay. Professor Aliseda has published and entitled books and articles on logic and philosophy of science. Her research topics include abductive reasoning and the logics of scientific discovery. Her present interest is in the application of formal models in medical diagnosis. Awards: the National University Award for Young Academics in the area of teaching in the humanities, and the Research Award for Young Scientists of Mexico, Mexican Science Academy in the area of research in the humanities in 2003. And she has also been serving as the coordinator of the research project Logic of Discovery, Heuristic and Creativity in the Science. So we are now ready to listen what Professor Aliseda has to say to us.
Thank you. Thank you. Well, thank you very much, Professor Suntala, for the introduction. I just want to make sure I know how to use this thing. It's the first time I use this digital view. You have two points of view here, the point of view of the observer, that is you, and the point of view of the speaker. So let me see if I can manage here. So, well, as you have seen in the abstract, the title of my talk is what makes a logical or a physical system a comprehensive picture of reality, following the workshop title. And the first thing is I would like to thank you, especially Professor Suntala, for this invitation, and more in general to the Finnish Society for Natural Philosophy, and also to the Physics Foundation Society. And although I would like to say many things about my experience in Finland, in particular in Helsinki, this is the second time I'm here, already in less than a year. So you can tell I liked it very much. But more in particular, in this context, I was, when I studied my PhD at Stanford, one of the things that was very much promoted was interdisciplinary work. So this is something I like very much. But at the same time, of course, it's really difficult because you have to get to know the language of the other discipline to some extent. And although I like it very much, I also want to make it clear that I am not a cosmologist, not even a physicist. I am a philosopher of science, more in particular a logician interested in methodological issues. So what I try to do for this time, I would like, before going into the outline, tell you a little bit of my background so I can use these first two slides to set the ground on the framework in which I will be speaking. So to go to the next one, just like this. So about previous and ongoing research, I wrote my dissertation and then later the book called Abductive Reasoning, Logical Investigations into Discovery and Explanation. This has to do with the logics of discovery. And more recent work, I am interested in hypothetical reasoning, and I just edited a section on the Handbook of Model-Based Science called The Logic of Hypothetical Reasoning. So this is part of my work in logic for philosophy of science issues in general. The publications I have, however, that are more related to the talk I will be giving today are, on the one hand, I wrote a paper together with Professor Donald Gillies on a Handbook of Philosophy of Science, the first volume on general issues, called precisely Logical, Historical, and Computational Approaches. And although it's not in the title, it meant to philosophy of science. But more in particular, the paper is connected to this talk, is the other one, that is, what is a logical system? So this is a question that is going on in the area of logic, more in particular in metalogic, and the exercise that I want to do for today is to explain that to you, hopefully in a very intuitive manner, and then try to take some of the things from there and see if they could apply to some extent to the context of this conference. However, I just wanted to mention that I am not doing that type of work right now, and rather, let me see if this works. Yes, I repeated the same thing in the down part, but now I am more interested, I am taking a sabbatical and really trying to get into another topic that it's been my interest for almost 10 years now. And I am in a health sciences school in one university in Mexico, and also attending clinical sessions at the Cancer Institute of Jalisco. So I'm trying to see to what extent I could apply my logical models into the way clinicians make up their diagnosis. So I'm very much interested in applying abstract research into the real world, so to speak. But of course, this is not into physics. And this, as I said, was just an idea of letting you know what is the kind of things I am interested on. But for today, the outline is, well, I would like to tell you what is my motivation through several questions, then concentrate, the core of my talk is really the second part, concentrate of what makes a formal or a system in logical, even though this may sound to you surprising. Not even logicians agree on what is really a logical system. And especially now with computer science, this is a question that we also like to do, because computer scientists, of course, also use formal systems or symbolic systems. We want to talk about this more generally. So I will do this from, first of all, I think that it's important to take, in order to talk about this issue and then translate it into physical systems or physical models, we need always a frame of reference. And in logic is classical logic. So even though people like me that we do non-classical logics, in order to be able to talk to other logicians doing other kinds of logic, our frame of reference is always classical logic. I will talk a little bit about the proliferation of logics, different logics, and more in particular, I will concentrate on a particular framework in which what we try is to use it to compare different systems and then to go to the question if we could talk about a universal or a schema valid for all of them to some extent. And as I already said, then I will try to transport part of this question, of course not the whole thing, into what makes and what about physical systems. And when I read the abstracts of all the talks, then I realized from there that energy here is very important, in particular the energy principle or conservation principle, so I will try to do some things related to that. I'm also interested in theory evaluation, but although it's in the outline, I decided not to talk about that, and instead making a section to go back to logic and mathematics and try to make some more connections to the physical systems, and then perhaps draw some conclusions. So what are my motivational questions? So the first is, well, what is it? What are the elements and the concepts that make up a logical system? And moreover, the question if there are any rules or schemas or principles or constants, that this seems to be also very important for physical systems, valid across all logical or physical systems. And as I said, I'm also interested, of course, what counts as a good logical or a physical theory, although I won't go into much detail in the case of physics in this respect. So let me turn to classical logic first. So, well, first of all, it's almost impossible to talk about logic without putting symbols, but please don't be put off by all the symbols. I will definitely give you what the intuitive idea is behind. So in classical logic, we have two approaches. One is proof theory, the other one is semantics, and then we have a meta level, a level that talks about the relationship between these two approaches. The first one is proof theory. The one person, of course, there are many researchers, but that is related to this one is David Hilbert, and he is the one who formalized the notion of what a derivation means, what is a proof, a mathematical proof. Although this idea comes from Euclid, and it's already been mentioned in this conference, the more formal approach was devised by Hilbert. Then we, on the other hand, we have semantics. Professor Ninilotto already mentioned Tarski as the one proposing the truth correspondence theory. And this, here, the notion of truth and the notion of models is very important. But then the question, the meta-theoretical question, or at the level of meta-theory, means that in some logical systems, actually these two approaches are equivalent, and it seems that it's just a matter of convenience or of preference, which one you like. Nowadays, researchers in logic, they either are proof theorists or work in the theory of models, which is the part of semantics. But the next level, as I said, tries to relate these two approaches, the semantic and the theoretical one. And there are very important results of which I will not mention, only the name given by Kurt Gödel, both for completeness and also for incompleteness, only meaning how these two concepts in logic, or these two approaches rather, are related. So, a little bit more about proof theory. Well, the words in blue are some of the key concepts in the proof theoretical approach. This is the notion, the very notion of what is a proof, the notion of derivation, the notion of axiom, and the notion of inference rule. And all these make up an axiomatic system. So in this type of approach, intuitively, basically, what we try to characterize is what a derivation is. So here, this symbol, sigma, let's think of it as a set of formula or premises. We want to know what follows. In this case, phi follows from the premises given a proof. A bit more formally, the way of characterizing this idea is to say that phi follows from a set of premises in axiomatic system S, if and only if there is a formal derivation. Hilbert presents in a very precise way what is a derivation of the conclusion from its premises. That is a list of formula from alpha 1 through alpha n greater than 1, such that in each step of the derivation of the proof, the last line will be precisely phi, because this is what we want to prove. And for all of them, we have either an axiom, something that could also be seen as a postulate, something that we take as true within the theory, is a premise, something that we are assuming for that particular derivation, or it is obtained by an application of an inferential rule. Inferential rules are ways of combining the different formulas of the system in a rule-like system, so that we can tell what follows from what. So this is very intuitive, I hope, the notion of proof. So, and given the dates that I already gave you, Euclid was the one in his Elements work who talked first about this, and also in modern logic, this type of approach was developed first. Now, when we come to semantics, or what is better known now as model theory, here the person to talk about, as I said, is Tarski. And the key words here are the notion of logical consequence, the notion of truth, the notion of models, and another one that is more technical, but still I needed to write it down, the notion of what does it mean that the formula is satisfiable in one interpretation. But what does this mean? This reads as phi is a logical consequence of sigma if and only if all models of the premises are models of the conclusion. Basically, this only means intuitively that phi is true in everywhere in which the set of premises are true. Or more technically, if we can prove that the premises plus the negation of the formula, it's not satisfiable, which is another way of saying that it doesn't have a model. So all these, I know they're very technical things, but what it interests us most for the purposes of this talk again is to get into the next level of analysis and then be able to try to see to what extent both approaches relate to each other. So there are very important theorems. One of them is called the soundness theorem, which basically says, and let me say it in English, I won't go into the symbols anymore at this point, that every formal derivation is a logical consequence. Or more informally, and I hope this is more understandable, that all theorems are valid truth. Anything we can derive in our theory is actually something that is true. Or the other direction of this theorem is that all truths are probable. And this is perhaps much more interesting, more difficult to prove, but also more interesting relating this to science in general. We want in science to have ideally axiomatic systems in which we can prove that whatever is true there, it's also derivable. It's probable in the way that we can make a proof of it. So, given this, this picture, I have given you, I hope not very, well, it is complicated, but I hope I have given you at least a taste, because this is no more than a taste, of what the two approaches of logic are about. And now I would like to go into another level of analysis, which is called the logical structural analysis. And what does this mean? This means, well, maybe it's so difficult or not even interesting to go into such depth into the details. There's a lot of mathematics and things, but let's try to see what are the intrinsic properties, here are called structural rules, of the notion of inference. After all, what we like to characterize is what does it mean that a formula that expresses some statement follows from something. So in this respect, Tarski himself worked on this issue from an algebraic point of view very deeply. There's also some work on Gensen, and what follows, it will be based on Gensen. And he talked about natural deduction, and there's a whole field called substructural logics. But the basic idea is to try to find out what makes this, let me now put it even more intuitively, I hope, this law of association in logic. What we try to characterize is how to connect some group of set of information with another one, and then say that the second one follows from the first set. So going back to philosophers like Hume, this is basically the question of how humans, in this case doing logic, but in general how humans relate ideas in such a way that you can say that one idea follows from a set of other ideas. But of course we want to characterize how is that done in a logical way, and the structural analysis tries to do that. And then, before reading what the characterization is, this work has also been very important in computer science, as I said at the beginning. In particular, this was performed by Dana Scott in '71. He even devised a computer language based on these ideas. And more recently, in the area both of natural language interpretation and artificial intelligence, there are many, many systems divided by these people and many others. But like the pioneers or the fathers of this approach are Dov Gabay, Krauss, and Johann van Bentem. So what is this thing about? So they say, well, an inferential notion, such as the notion of classical logic or any other one, may be characterized by its combinatorial properties expressed as structural rules. So how do structural rules look like? I'm not going, as I said at the beginning, to go into all details, but I have to show you, I have to be able to show them to you. So these are the structural rules for classical logic. I'm not showing the semantics or the proof theory. I don't need to do that. In fact, I'm not showing you the logical language. I'm just telling you what is the, so to speak, a skeleton or the very bare bones of this notion of inference. Since this slide, I imported it from my book, didn't look so well. I have a better one, but it is in Spanish, only the names of the rules. So let me turn into that one, because I think that I didn't know how big the auditorium was going to be. So I can translate this to you. So what does it mean? This is only saying the relationship between premises and conclusion follows all these rules. One of these rules is reflexivity. So think of this arrow. This arrow is not one of the symbols I showed you before is not committed to proof theory or is not committed to semantics. Just think of it of a notion of association between set of premises on the left-hand side and a conclusion on the right. So reflexivity only says that everything follows from itself. From C, I can always derive C. I can always find a proof of C. In fact, that is its own proof. Contraction. What does contraction mean? By the way, this presentation is what's called a Gensen rule. It only means that think of X, Y, and Z as sets of formula. So those letters want to express that there are several things there. And then the letters A, B, and C are just single formula. So, and then the format of the rule only says from what it's over the line, what's under the line is what follows. So the law of contraction in classical logic only means intuitively that repeated information can't be ruled out. A bit more formally, but it's the same idea, it only says C follows, a conclusion follows. If a conclusion follows, from all this information with A repeated, we can delete one A because it's just repeated information. Another essential rule in classical logic is permutation. It doesn't matter, the notion of proof in classical logic is so static that the order doesn't matter. So the order of presentation, you can, if C follows from some set of premises, then A and B and another set of premises, the same thing would follow. C as a conclusion will remain valid if we change the order of A and B into B, A. Then there's another rule, which is more or less in this area famous, which is a monotonic rule. So this means that a conclusion will remain valid if a conclusion follows from X and Y, from sets of premises. This conclusion will remain valid even if we add more information. And just to advance you some idea, not all logics follow this rule. So you may have heard in artificial intelligence of non-monotonic logics. Basically, this only means that they don't follow this particular rule. And finally, we have the rule that in Spanish it's a corte, but in English is the cut rule. So basically, this is a rule that tells us how to make shortcuts or how to chain arguments, meaning what? If C follows from X, A, and Y, C will also follow, for sure, it will remain valid from X, Z, and Y, given that A follows from Z. So it's called cut because it means that we are cutting A. We are just, here we had like two premises, and here we will have just one. As it turns out, I will not show you the theorem, of course not the proof, but as it turns out, given these structural rules, meaning I would like to stress, this is not the logic of classical logic per se, but it is indeed the way classical logic behaves as thinking of it from a metalogical point of view, only from its structural levels. If somebody here knows logic, you can tell that I use no connectives, there is no logical language there. In fact, this form of characterizing classical logic includes extensions of classical logic. There are some logics that are called modal logics, epistemic logics. I mentioned particularly epistemic logic because this was devised here in Finland by Jaakko Hintikka, and is a very important logic.